the Distributed Consensus with Cellular Automata and Related Systems Research Conference. It's great to be here. I'm Jon Woodard, CEO of Wolfram Blockchain Labs, a subsidiary of Wolfram Research. Now, I've known Yilun, Bruce, and Yambo and Alan of NKN for quite some time, beginning with our work in 2018. It's great to see NKN really flourish, and it's certainly really exciting to be doing this conference with them. Without further ado, I'll introduce someone who really doesn't need a long introduction at all, Stephen Wolfram, CEO and founder of Wolfram Research.
Hi there. Well, it's great to be here this morning. So I'm going to talk a bit about kind of the background to the problem of distributed consensus. I would say that kind of in many ways, my life has been a story of sort of alternation between doing basic science and doing practical technology. And it's always great when they come into very close intersection. And that's been what's happened here with this problem of distributed consensus with cellular automata and related systems. So about 19 years ago, I published this book here, which was the result of many years of research, 10 years actually spent writing the book itself. Then years later, March 2018, people started pointing me to this thing called NKN. And so I look at the white paper and I was very interested to see that of the first 4 references, reference number 3 was to Satoshi Nakamoto, reference number 4 was to Vitalik Buterin, references 1 and 2 were to my work on cellular automata and my book, New Kind of Science. So I thought, that's really cool. I have to actually understand this. And the more I understood, the neater it seemed to be. And that caused us to start working with NKN. And that kind of brings us to today. So I'm pleased to welcome you all here also to this research conference that we're putting on with NKN about distributed consensus with cellular automata and related systems. So let me start giving you kind of an introduction to this problem. It's sort of a great example of what one might call new kind of technology, using ideas from things like NKS to make in this case a new kind of network. And I'll talk about some of those intellectual connections. A great example of what one might call new. I'll also talk a bit about the history of this field. And we're very pleased today to have a whole bunch of the actual primary contributors to that history here. So it's always very nerve-wracking to talk about history when in front of the people who created it. And they'll no doubt give me all kinds of corrections later. By the way, I wrote up about a week or so ago many of the things that I'll be saying here today in a post that I put out, which is linked to the homepage of this conference. Okay, well, so as I say, this is a story of sort of blockchain meets basic science. And we've been involved in blockchain for quite a while. First, because Wolfram Alpha has become the world's main provider of kind of computational facts. And secondly, because oops, I think we have some echo here. Perhaps somebody could take care of that. Also because our Wolfram language, which is this full-scale computational language that I've been building now for close to 40 years, is sort of a unique, has unique capabilities for creating computational contracts, for representing the things that we would usually represent in legalese in a computational language that is executable automatically by machines and so on. And also that language has provided a powerful platform for analytics for blockchain and so on. And as John mentioned, we created Wolfram Blockchain Labs to work on these kinds of things, and Blockchain Labs is what's responsible for putting on this conference. So in another part of my life, as I say, I've sort of been involved in alternating between doing basic science and doing practical technology. Another part of my science my life in the last couple of years has been huge progress with fundamental physics, and really, I think, successfully cracking the problem of finding sort of the formalism, at least for understanding how the physical world actually works. And in the sort of pattern of science and technology alternation, it's going to turn out that some of what we're doing with the Fundamental Physics Project is deeply related to a bunch of technological questions about distributed computing and about blockchain and the future of blockchain. And I'll talk a little bit about that maybe here today. All right, so let's talk about distributed consensus. First of all, sort of what's the basic problem we're trying to solve? So let's imagine we just have a collection of nodes, say 2 possible colors, and we just want to determine what the majority or consensus color of these nodes is, i.e., which color is more common among these nodes. So one obvious method to do this is just sequentially visit each node and then tally up all the colors that we get. But it's potentially in that sort of a sequential way of finding consensus, so to speak. But it's potentially much more efficient if we can use a distributed algorithm where we're running computations in parallel across all these various nodes. And so one possible algorithm for that would be the following. Connect each node to some number of neighbors. And for now, we'll just sort of pick neighbors that are according to the particular spatial layout that we have of the nodes here. And then in a series of steps, just look at each node and say, let's make the color, let's update the color of each node according to the majority color of its neighboring nodes. So at each step here, if we pick one of these nodes, we can see this one here, this red one here, got updated on the next step to yellow because the majority of nodes in its neighborhood, as defined by connections to that node, the majority of nodes in its neighborhood were yellow, so it was turned yellow on the next step. So the and what happens in this case is after some number of steps, the whole network of nodes, all the nodes end up being the consensus color, the majority color. So that's kind of the idea. We want to have something where even though where we have a bunch of these nodes that are distributed around, and in a distributed way, we want to determine what the consensus color, what the global consensus color of this of the network is. So the challenge is to find the most efficient and robust methods for actually doing this in practice. And this is a problem that shows up in lots of places. I mean, sort of in any decentralized system with computers, people, databases, measuring devices, whatever, one can end up with different values or results at different nodes. And for all sorts of reasons, one potentially wants to agree on a consensus value that one can, for example, take a decision on the basis of to sort of move on to the next step. And blockchains are one big example of systems that need this kind of consensus to kind of finish each block. And traditional blockchains tend to achieve that consensus through what amounts to a centralized mechanism, even though there are decentralized copies of the blockchain that's produced. But now the thing we're interested in is to start creating distributed analogs of that kind of blockchain idea, and those need distributed consensus algorithms. And it's the main inspiration for the algorithms that have been developed so far is Cellular Automata, which is what brings us to this conference. So what I showed you so far can be thought of as a cellular automaton on a graph. Let's start off talking about kind of ordinary cellular automata. So this is a typical example of an ordinary cellular automaton of a kind that I've spent. Why isn't that doing what it should do? Who knows? That's an example of kind of an ordinary cellular automaton. Let me show you here. Well, here, let me. When in doubt, actually use code to generate it. Okay, here we go. All right, so here's kind of oops. Okay, so in kind of the simplest version of an ordinary cellular automaton, you have a line of cells. Each cell is black or white. And there's a rule that defines what the color of the next cell should be based on the colors of the cells before. And in this particular case, we can we could just run this and see what it does. So let's say we run it for 40 steps. I'm about to get that wrong. This is what I get for trying to generate slides in real time. There we go. Okay, there we go. So I should perhaps explain how I got involved in studying cellular automata, but I'm going to talk about cellular automata and how they can be used for distributed consensus. What first got me interested in cellular automata about 40 years ago now, a little bit more than 40 years ago now, was the following thing. I had been studying lots of kinds of systems in physics and in nature, and I was interested in what's the best way to model these kinds of systems. And the sort of traditional approach has always been, for about 300 years, was this idea of use mathematical equations to work out what these systems in nature will do. And I realized that there were lots of systems where there was all kinds of complex behavior that occurred, which was not easy to find things like mathematical equations, and it wasn't easy to solve those mathematical equations. So I got interested in sort of what was the alternative to mathematical equations? How could you generalize this idea of making models on the basis of mathematical equations? And that got me to thinking about programs as models for things. And as I thought about that, kind of the simplest possible programs that I could come up with were these cellular automata. And that got me interested in a sort of a basic science question of, if you pick these programs, if you just pick simple programs, let's say at random, what do those simple programs typically do? And so this is one example where we're just defining, there's a cellular automaton where we're defining the new color of a cell based on the color of the cells above it and to its left and right. And this is a case where sort of things happen as we might expect. There's a very simple rule. The behavior is somehow correspondingly simple. If we pick a different rule, we'll find somewhat different behavior. But the thing that I then did was to try and do sort of the obvious computer experiment, which is just look at all possible rules of this general type and see what they actually do. So let's just do that here. Let's say we look at the first 64 rules that are of this type. Okay, so what we can see is each one of these pictures corresponds to a different rule, each one starting off from just one black cell. Most of the time, what we see is quite simple behavior, but the big surprise happened when we got to rule 30 here. And if we run this particular rule, we'll find, again, it has a very simple rule for it. If we run it, we'll get this thing that looks, let's say we run it for 400 steps, we'll get this very complicated pattern. And there's some regularity in the pattern, let's say over on the left, but many aspects of this pattern are basically completely random. In fact, this is a really good source of random numbers that if you look at the center column here, it's something we've used as a random sequence generator for a very long time. And so it's sort of this remarkable result that even though the rule is very simple, the actual behavior that's generated is very complicated. And that's something that I got very excited about as a way of understanding complexity in the natural world, and found out that, yes, this does seem to be sort of the secret that nature uses in lots of places to make complexity. Then many years later realized that one could sort of take the intuition from that and apply it in fundamental physics to make models for how the universe fundamentally works. But in a sense, what this is doing is to go from simplicity, from just the simple single black cell to complexity here. In a sense, what we're trying to do I should say that, you can just go out. One thing to realize is in this sort of computational universe of possible programs, it's remarkably easy to go out there and find great complexity and so on. And so for example, you can kind of find remarkable things from that. I don't know. We can let's just try generating sort of a random collection of behavior in the computational universe, and no doubt these kinds of things you can pluck from the computational universe will turn into fine NFTs, and we'll probably be giving out some of these NFTs based on cellular automata in the not too distant future. But the thing that's happening here is going from sort of a simple rule, a simple initial condition, to complicated behavior. In a sense, in the problem of consensus, we want to do the exact opposite. We want to go from that complicated collection of different kinds of initial values, initial cells, to something which is a simple result. Is it predominantly yellow or predominantly red? And so it's in the simplest case, we might say, let's try and use a cellular automaton to do that. And let's say here's a cellular automaton which is setting up the majority rule. So it's saying if the majority of cells in this 3-cell neighborhood are red, then make the result red and correspondingly with yellow. So let's say we then start off with a random collection of some fraction of cells being yellow and some fraction of cells being red. It doesn't work that well. Locally, it manages to come to consensus, but globally, things get stuck and we don't get the kind of single consensus value out of the system. So the question then is, can one in fact make a rule, let's say for a one-dimensional cellular automaton, which does have the feature that it can determine the consensus value of its initial condition? Well, in 1978, this rule was suggested by Peter Gacs, who's with us here today, Kadumov, and Leonid Levin. And this is a particular cellular automaton rule operating not just on a cell and its 2 neighbors, but a cell and its 3 neighbors on each side. And if we run that particular rule, let's say we run it with predominantly red initial conditions, after a little while, all the yellow will disappear and we will get just pure red. Similarly, if we run it with predominantly yellow initial conditions, after a little while, all the red will disappear and we will get pure yellow. So if we run this a bunch of times with a bunch of different initial conditions, what we'll see is something like this. Here's the initial density of red cells, and this is showing as a function of the number of steps. This is showing that eventually it will go to density 1 of red cells if it was above 50% red initially, and density 0 if it was below 50%. At least that's the most obvious kind of statistical result. And this looks very much like a phase transition of the kind that's been studied in physics for a long time. You know, the typical phase transition is something like you increase the temperature of water above 100 degrees centigrade, and it turns, and you get something where sort of every part of the system turns from being liquid to being a gas. And similarly here, as you make a continuous change, in this case of the initial density, you go from a final density of 0 to a final density of 1. At least that's the idea. And so one thing you might ask is, well, what happens right at 50%? What happens when, here's what happens, and it's kind of interesting and characteristic of what happens in phase transitions in physics, and particularly in critical phenomena in physical systems. The system sort of can't decide, is it going to turn yellow or is it going to turn red? And so what you see is this kind of nested pattern of larger and larger regions of all yellow, all red, and so on, all nested within each other. And that's something much studied in statistical physics, particularly with the renormalization group, this process of exactly what happens at this point, at this critical point, where a system sort of can't decide whether to go all in one direction or all in another direction. By the way, for a long time, it was thought that people would say, oh, you can't have phase transitions like this in one dimension. That turns out to be a consequence of some assumptions in statistical mechanics about microscopic reversibility, which are not true for these cellular automata. And it is possible. It was not, I'll talk about the sort of history of the finding of phase transitions in cellular automata, but it is not impossible to find such a thing as people had sort of thought from physics. Well, you can you could just ask the question, if you search possible rules for cellular automata, can you just find a rule that behaves like this without having to construct it? And when I was working on that NKS book, I did big search for such things. Other people, some of them here, have done bigger and better searches probably than I've ever done. But this is an example of the kind of thing that you find among not cellular automata with 3 neighbors on each side, but cellular automata with just 2 neighbors on each side. This is one of the winning examples of a rule that one can say does density classification, in the sense that if it is less than 50% 1 density, it will go to 0. If it's more, it will go to 1. That's a sort of equivalent way of stating the problem of solving, of making a rule that achieves kind of consensus in the end. I might mention that one example of this that is very close at hand is actually a nearest neighbor cellular automata. This is rule 184. It doesn't classify density. It doesn't work out the overall number of black and white cells at the beginning, but it does figure out, in a sense, whether there are more right-moving or left-moving stripes. And actually, this particular rule has been widely used in studying traffic flow, where one thinks about kind of waves and traffic jams corresponding to these kinds of, these are cars sort of free streaming forwards, and these are cars that have been jammed up and so on. And so it's interesting to see that correspondence. Okay, well, so there's a question of how do you, for example, achieve how do you achieve consensus sort of faster, better, and so on? Here's an example of this is the original GKL rule here. This is a rule that was found by genetic programming methods in the 1990s. That's a slightly faster version of sort of the same kind of idea for how to achieve consensus. One can go ahead and do searches. I just did a few more, actually, a couple of weeks ago, for these kinds of rules. And what's sort of interesting to realize is some of these rules achieve their consensus, so to speak, in a way that seems very systematic and very organized. Some of them have all kinds of ornate extra things going on, which might just slow things down, but might turn out to make things sort of more robust and so on. And it turns out this sort of trade-off between human-engineered rules that work in kind of easy to understand ways and rules that can achieve their objectives in a more efficient way, but are not necessarily set up to be understandable. That's a general trade-off that shows up in all sorts of places. For example, even if you're looking at, let's say, sorting networks, the question of what's the optimal sorting network for a given number of elements, the ones that are kind of systematic and engineered ultimately end up being not the most efficient, and the ones that are the most efficient sort of look like kind of random sorting networks. And so it's likely to be, although we don't yet know the final results, it's likely to be with things like cellular automata that can find the consensus in an optimal way. I think one can expect that the actual optimal algorithm, so to speak, will not be something that has sort of the simplicity of human engineering and is built to be understandable, but is instead something which one can just sort of pluck from the computational universe to find out what it does, but and then just use it for the particular purpose one has. So, okay, let's talk about the question of so we have something like this GKL rule. One question is, does it always work? If you have a big if you have a big system and it has millions of cells and it's just a few cells over in one direction or the other, is it actually going to successfully find consensus? So one way one can sort of explore that is to make a state transition diagram, to just take something with a finite number of cells and just represent every complete configuration of the system, every complete collection of n cells by a single node in this diagram. And then we're coloring these nodes based on what the sort of true majority, the true consensus value in that particular configuration is. So in this particular case, with a rather small number of nodes, it so happens that this particular rule has the feature that it has these two attractors, collections of states that are majority red, all evolve finally to this state here, which is majority red, and similarly with yellow. But if we look at slightly larger initial condition, we start seeing some trouble here. So this is something where most of the initial conditions do successfully evolve to their consensus red and yellow values, but there are a bunch of stragglers here of initial conditions that don't evolve to, that just stay fixed and don't evolve to that final consensus form. And we can look at larger examples here. Here's a larger example with the GKL rule. And this is one where there are some configurations that just sort of freeze and don't do anything. And then over here, most of the configurations here do successfully evolve to their consensus values, but we see a few sort of rogue configurations here. In this big sort of attractor basin for the red final state, we see a few majority yellow initial conditions. So there's a few sort of mistakes that are going on there. So there's a sort of a question, can you set up any rule that is just a simple one-dimensional cellular automaton rule that will always work? Well, on a finite number of cells, the answer is no, you can't make it always work. There will always be some exceptions, some things that go the wrong way. What's true for an infinite initial condition, it's not clear. It's much more likely one can get something that sort of works with probability 1 there, even though there might be some, let's say, even just finite number of possible sort of bad initial configurations with probability 1. If one just samples initial conditions at random, one would get something which successfully goes to consensus. So this is sort of what happens in the case of one dimension. If we go, let's say, to 2 dimensions, we can ask what happens there. Now we have a rule, let's say we have a majority rule that operates on this 2-dimensional cross configuration. We started off from a random configuration of cells with, in this case, predominantly yellow. And once again, just like in the 1-dimensional case for the pure local majority rule, things get stuck here. You end up with pieces that get left over which do not successfully go to consensus. And you can make sort of a 3D picture of that. You're seeing here these pieces that kind of get stuck and don't go to consensus. Now you can change the rule a bit. Here's another rule that operates on the same collection of initial same local neighborhoods. This particular rule is a bit more complicated and ends up with these. If we've kind of take a slice, imagine taking this picture here and imagine sort of making the part that is here blank is really yellow cells. And imagine that you make kind of a yellow fog out of that, but you slice this picture somewhere in the middle, then you can make something like this, which is showing kind of at the position of the slice, what is the configuration. And what you see here is this kind of diffusive behavior where you see kind of random walks going on, but with it seems that in this particular rule, not something that's rigorously proved, but it seems that with this particular rule, it is the case that eventually and diffusively, it successfully goes to kind of a consensus behavior. And so then you can ask the question, are there kind of better versions of this? Well, it turns out a person called Andre Toom figured out when was it? I guess in the 1960s. I'll go through the history a bit later. That if you just pick, instead of picking a configuration of cells where you're looking at a cell and it's a sort of a cross of neighbors, so to speak, you just pick these neighbors and you say, let's work out the majority on those neighbors. It turns out this is the 3-dimensional picture that you get. And it turns out that if you look at the slice here, this is something which again appears to go successfully to consensus in this rather curious way. And so you can see that if you look at these slices, starting off with different initial configurations that have, let's say, 30% red cells versus 70% red cells, that's the kind of behavior you get. This turns out to be something pretty generic. If you look at different local configurations here, where you're taking majority on on these kind of irregular asymmetric kinds of initial conditions, I'm not sure exactly why it works that way, but it seems to be the case that essentially any asymmetric choice of majority like this successfully produces the result that it empirically, at least successfully, generates something which correctly shows consensus behavior. And you can go on and look at a bunch of these. It's this one. That one is the direct analog of the GKL rule in 2 dimensions, also showing this kind of behavior. So, okay, that's so one feature of all these rules that I'm showing you is they're all completely deterministic. That given the initial condition, the behavior that you get is completely determined just by this rule, and you'll either get consensus or you won't. In many practical situations, one's interested in the case where there is some kind of external source of randomness in the system, some kind of noise that is that's imposing itself on the system. And so you can ask the question, what happens if you randomly flip bits in the evolution of the system? So this is the case of the plain majority rule for a one-dimensional cellular automaton. You'll see that sometimes you'll get slightly different behavior here, but the result that you just get regions that get stuck still remains. Let's look, for example, at this GKL rule. As we add a small amount of noise, the rule in the case of the small amount of noise seems to be robust and resilient to this noise, and still seems to successfully reach consensus even in the presence of a small amount of noise. At least that's what appears empirically to happen. If we add more noise, eventually the thing just loses it, and we no longer get the correct consensus value. It's just been overwhelmed by noise. And we can make what in physics would be called a phase diagram, where we're just plotting as a function of the initial, as a function of noise level here and initial density, we're plotting what is the final density. And this is based just on a particular ensemble of initial conditions, a particular run that I just did a couple of weeks ago. What we see here is, for low noise levels, we successfully classify things, and when density is less than 0.5, more or less, most of the time we're getting to all 0. Above 0.5, most of the time we're getting to all 1. As we increase the noise level, eventually it loses it, and we get this kind of phase transition-like behavior, and everything no longer is able to go to that consensus value. So one of the things that maybe I'll talk about a little bit in the history here is this question of well, actually, let me skip this for now. Peter is Gacs, who was responsible for inventing this rule, points out that in 2 dimensions he has a rule that always works, and that they proved that if the noise is biased, then however small the noise is, there can be exceptional cases. Okay, interesting. All right,
this is about the GKL rule.
Oh, okay. Oh, I'm sorry. This was back to the GKL rule, and I wasn't noticing that. All right. Well, we get to hear more about this later, I hope. But let's talk about if we wanted to make a very principled approach to the problem of noise. One of the things that we might consider doing is looking at, given this particular, is looking essentially at something like those state transition diagrams, but looking at what in the context of, for example, our modern physics project, we would call multi-way graphs. So in our physics project, we have defined certain rules, in that case for hypergraphs rather than for arrays of cells. But the idea is there's a particular rule, and there are multiple places that rule can get applied, or multiple ways that rule can get applied to our particular hypergraph. And we can kind of make these diagrams that represent kind of the all possible histories of the system, given all possible rule applications. And in the case of physics, one of the important things that comes out is that possibility of multiple possible histories is what leads to quantum mechanics in our models of physics. And we now have a pretty good understanding of how that all works, kind of leveraging the 100 years or so of work that's been done on theory of quantum mechanics to our systems. But we can imagine making these kind of multi-way graphs that represent sort of the all possible transitions, even in the presence of noise. And we can then start looking at sort of the combinatorics of what are the more likely transitions with different, when we've added the possibility that some rules are noise rules. And so we can start asking questions about what is the kind of average consensus behavior, and we can think about this in statistical mechanics terms, in terms of partition functions and things like that. But this is sort of a framework for thinking about kind of the general problem of noise and sort of what the aggregate behavior tends to be. And you can imagine proving things about sort of the structure of this kind of discrete mathematical object and what kinds of connections can exist on it and not, and so on. Okay, so one thing I might mention, well, okay, so there's one issue with sort of noise that is just randomly flipping bits. Another kind of noise we can consider is intentional noise, where somebody is intentionally trying to mess the system up. Like, let's say we have something where we have, this is a particular one-dimensional cellular automaton where mostly its behavior just shows this checkerboard pattern, but there is a particular kind of seed that you can insert in the initial condition, which will blow up that checkerboard pattern and lead to this kind of completely different behavior. And so a question might be, if you are, this is an example, I think this is the GKL rule, this is an example of an initial condition which is sort of specifically set up to blow up the consensus possibilities for this particular rule. And you can ask the question both, what kinds of sort of adversarial examples can you give for the initial conditions, and what kind of what in cryptography tends to be called Byzantine attack, what kind of sort of coordinated intentional attack can you make where you're specifically deciding which bits to flip in the evolution of the system to cause it to get to the wrong consensus value. So those are questions that I think other people will address here today. Those are questions that come up, and the question is sort of, when is one robust against what kinds of attacks like that? Okay, well, so what I've been talking about here so far is mostly ordinary cellular automata. We can also define cellular automata on graphs. In this case, there's a question of what we can set up a graph, and we can say the neighbors, we can, instead of putting cells in a rigid array where we just look at the sort of geometrical neighbors, we're now just looking at the graph neighbors, what cells are connected to a particular cell. And in the most obvious way of doing this, where if the connections to a particular node are not in any way ordered, we basically just have to set up what I call totalistic cellular automaton rules, where the color of a cell is determined just by something about the total of the number of colors of cells in the neighborhood of that cell, where neighborhood is defined as being the cells to the nodes which are directly connected to this node. So the most obvious way of setting up cellular automata on graphs is just to look at these totalistic rules. One could do things that are a bit more complicated. One can look at sort of geodesic balls around a particular node in the graph going progressively larger graph distances away. And one could say one's having a totalistic rule that has things that sort of have different weightings for different layers of that onion and so on. One can also think about defining directions on graphs. In fact, in our physics project, this is something that is a very important part of the story, because in the physics project, the whole structure of space is just a hypergraph defined by connections. And the way one has to sort of imagine setting up all sorts of things that end up with metric tensors and things like this. And for that, one has to use kind of the structure of the graph to define directions. And one could do that here as well, to define a more complicated set of rules than the most obvious kind of totalistic rules for cellular automata on a graph. But we can ask all the same kinds of questions that we've been asking before. This is, let's say, this is a particular graph. We're going to use a majority totalistic cellular automaton rule on that. We can ask for the state transition diagram from that. And what we'll see is that for most initial configurations of cells, we successfully evolve to the consensus value, but there are plenty of exceptions here. One thing one might ask, if one's just sort of trying to understand the mathematical structure of what's going on, is what is the continuum limit of something like one of these graph cellular automata? I think that's a complicated story, and I'm not quite sure what that continuum limit is. In the case of our physics project, we've been very concerned with what the continuum limit of our graph rewriting process is, because that's what corresponds to general relativity and the structure of space and so on. But in this case, I kind of think that you can start thinking about sort of a continuum limit in terms of even what the continuum limit of a majority cellular automaton in one dimension is not so obvious. And I think it's some kind of complicated integral differential algebraic equation where sort of the continuum values are given by you're getting these continuum values and you're sort of progressively computing these local integrals to see what the result is. But I think this is sort of an interesting undetermined mathematical problem. At least I'm not aware of a solution to that, but I think it's something be interesting to understand as a way to understand sort of the continuum limit of this consensus behavior. It might be said that when you look at cellular automata on graphs or whatever, if the local rule corresponds to essentially a Laplace operator, where you're just taking the average of the cells in the neighborhood, that has a very nice continuum limit, and it's basically just the diffusion equation. But in this case, where you're taking the majority of the cells in the neighborhood, it's not so clear what the continuum limit is. Well, okay, so other things that one can think about here. Another thing one can think about is asynchronous updating. So in the cellular automata we've been talking about so far, all the cells are just sort of, it's a parallel computation system, and all the cells are kind of updated in lockstep and parallel at every step. What happens if we don't do that? What happens if we just say, we've got these rules and just we apply them whenever we feel like applying them? What happens in that case? By the way, that's the situation in our physics project, and that leads to a lot of very interesting structure in physics, and we understand quite a bit from sort of leveraging the results in physics to understand that sort of distributed computing problem. But let me show you one kind of thing that can happen with asynchronous updating. Consider these rules. These rules are essentially just local sorting rules. Whenever yellow appears after red, it's flipped around and it's sorted into the right order. Let's say we start off with different initial conditions there. What we'll find is these are all different initial conditions, but they all have the property that in the end, I'm sorry, these are the same initial condition, but we're applying that rule asynchronously in different places and different sequences of applications of that rule. What we see happen in this particular case is that even though the rule is being applied in different places, in the end, the answer is the same. In the end, we'll just get a sorted result. So this is an example in the theory of term rewriting or mathematical logic of a confluent rewriting system, something which satisfies this Church-Rosser property, which can be generalized in sort of the infinite case to this property we call causal invariance in our physics project. There is an eventual consistency to the results you get here. So even though the updatings may be in different orders, eventually the result will be the same. And so that's something that can happen in different systems. And that's a case where the asynchronicity doesn't matter, in a sense, to the final result. You can make this multi-way graph of the kind that I mentioned in connection with noise here. This is the multi-way graph for the sorting system, which is showing that even though there are different possible branches that are made by applying the rule in different places, in the end, all those branches merge and you get a single sort of consensus result. Well, so you might ask, well, what about all these rules that we might use to actually find consensus for the values of initial cells? Do they have this causal invariance property or not? The answer is, so far as I can tell, at least the most obvious examples, they don't have it. So this is a case which doesn't have causal invariance, and where you see this is the initial condition. These are all the possible asynchronous updatings, and there are different final results that you can get in those cases. So we can just look at what happens when you do asynchronous updating in these particular systems. When you do it for, let's see, where's a good example here? When you do it, I think that's just the majority rule. This is the, I think this is the GKL rule. What is this one? Sorry. This is, let's see, I mean, this in this case basically destroys this asynchronous updating destroys kind of the nice consensus properties of these particular rules. I did a bit of a search for rules that would, even with asynchronous updating, would successfully preserve consensus. This is the best out of about 2 million, what was it? A million range 2 rules. The results are pretty crummy. There probably are, there no doubt is a best asynchronous updating rule, but I don't know what it is. So that's, and by the way, those are the kind of the curves that if there was a correct phase transition, it would just be a step function of a half here. You can see that these best rules out of that first million were pretty crummy in terms of successfully achieving consensus. They kind of got to it down here, but there was a large region where they weren't sure what was going on. I might say that there's a lot of stuff one can do once one's looking at asynchronous updating. There's a lot one can do with the formalism from our physics project. This is an example of a causal graph that represents kind of the causal relationships between updating events in one of these kind of majority rule systems, and there's a lot one can study there. By the way, I might mention that in addition to the question of updating, of picking updatings asynchronously, one can also go even more extreme, and one can imagine that the very structure of the network is also being dynamically updated. And that problem is incredibly close to the problem that we have in our physics project. And in fact, there we're looking at we're considering updating rules on hypergraphs and so on. And so one question is, can you compile essentially something like a majority rule, an asynchronous majority rule, into updating rules for hypergraphs? And this is an example of such a compilation where we're basically representing ones and zeros by the presence or absence of these self loops in our hypergraph. And we can have something where we're looking at where we're starting to actually do evolution, in this case, of essentially a pure asynchronous graph, cellular automaton-like thing, but implemented using these hypergraphs. But now we can do things where, for example, in addition to the pure majority rule for the self loops on the hypergraph, we also have another rule that actually changes the structure of the hypergraph. So we're essentially dynamically updating the connectivity of our network. And then we can start studying what happens in those cases. And I just started doing this, and it's a great project for somebody to go look at this in more detail. But this is the case where we're sort of asynchronous and we're dynamic in terms of the underlying structure of the connectivity of the graph. And we're asking what happens to sort of consensus in a case like that. Okay, well, so that's so that's kind of the problem to figure out is, what are the best algorithms, what are the best procedures in these cases where you have things like dynamic updating of the network, where perhaps you have malicious attacks on the network? How can you successfully preserve the result that you can correctly determine what the sort of consensus value from the initial conditions is? So that's kind of the challenge there. All right, let me talk a little bit now about kind of the historical background of this problem. Why did people ever start looking at this? What was kind of the story? So there's I think a big part of the beginning of the story was at the beginning of the 1950s, when people were interested, well, actually probably arose even earlier than that. People were starting to build complicated electromechanical systems. And the problem was there were components in those systems that were unreliable, yet you wanted to make the whole system be reliable. How could you make the whole system be reliable even when some of the underlying components were unreliable? And so the obvious idea was to use redundancy, to have more components there than you were actually going to use, and to kind of take a vote between those systems. And that was kind of the first way, was to use this kind of majority rule type approach, to just sort of use redundancy, take a vote, figure out what, and use that to overcome the unreliability of components. And that particular methodology is widely used, particularly in aerospace world, of, you have three systems and you pick the majority of those three to determine what you're actually going to, which way the plane is actually going to go or whatever. So at the beginning of the 1950s, there was more and more interest in moving sort of this process of voting down to the level of smaller and smaller components. And so one contribution to that was in 1952, John von Neumann wrote a paper called Probabilistic Logics and the Synthesis of Reliable Organisms from Unreliable Components. And his idea was to sort of move this down to the level of individual components and to have, as he called them, different kinds of organs. We'd probably call them gates now. He was thinking in a much more brain-like biological metaphor. And so he had a thing he called the majority organ, which is basically the majority function, Boolean majority function. He also had things he called Sheffer organs, which are what we would now call NAND gates. But so he was trying to ask the question, could you make a sort of reliable computer even when there was a certain unreliability of its components by, for example, adding the appropriate number of majority organs, so to speak? And he wrote one piece here. He tried to estimate how much redundancy you'd need. He said, consider a computing machine with 2,500 vacuum tubes, each actuated on average every 5 microseconds. Assume a mean-free path, physics terminology, of 8 hours between errors as desired. And for some reason, which I completely don't understand, he picked the error rate, the every vacuum tube running error rate as 0.005. And that means that to operate reliably, the system should be multiplexed, as he called it, 14,000 times. The computer should have 14,000 times level redundancy in order to operate reliably in this case. I think von Neumann was thinking more about brains because he talks about how this is really kind of similar to what happens in brains, and he's counting neurons and so on. And he has a rather bizarre claim that errors are not ordinarily observed in the operation of brains, which I think is a curious claim. But in any case, sort of fortunately for the history of computing, von Neumann's example error rate turned out to be very wide of the mark. And as soon as vacuum tubes were replaced by solid-state devices, the problem of individual component failures in computer systems more or less disappeared, although it reappears in modern thinking about molecular scale computing. In communication systems, and to a lesser extent storage devices, errors were always still important, and that led by the 1960s to all sorts of work on error correcting codes. But, and this is sort of speculation on my part, perhaps because the transition to solid-state electronics happened more slowly in the Soviet Union than in the US, for example, the interest in getting reliable results from unreliable components lasted much longer there. And another feature was, while in the West, the issue of sort of getting reliability from unreliable components was thought of as being a sort of a problem of applied engineering. In the Soviet Union, it was much more considered a matter of pure mathematics. By the way, in the West, particularly, there was sort of in the 1950s, this kind of idea of cybernetics, which was initially considered, I think, ideologically inappropriate in the Soviet Union, but was later quite adopted there and turned in a much more mathematical direction that also sort of fed into this. So there was this sort of idea of how do you make reliable systems with unreliable components, particularly getting investigated in the Soviet Union. There was sort of a quite different strand that was coming from physics, which was the question of phase transitions. I mentioned earlier, how do all the molecules in the water that you're heating up all decide together to make a transition from liquid to gas? And the sort of more subtle version of that is what happens in a magnetic material like iron, where below a certain temperature, the electron spins all tend to get lined up, and you get this ferromagnetic material. But the question is, when they line up, in what direction would they line up? For example, somehow a consensus direction is selected that defines the macroscopic direction of the magnetic field. And in the 1920s, Lenz suggested this thing called the Ising model as a model for that. But there's sort of a whole question about, as one starts to ask these questions about how do sort of large-scale effects get produced from small-scale things in physics, one of the most basic versions of that is the generation of thermodynamic equilibrium. When there are all these molecules bouncing around in a gas, how does it end up coming to equilibrium and having definite values of things like pressure? That was a question that got investigated starting in the late 1800s and much in the early 1900s, and it led to the question of ergodicity. which was this one idea for sort of how you would explain what was going on is, well, the gas behaves sort of randomly because it can visit all possible configurations of the gas. That's the property of ergodicity. And there was the question of did particular rules for the underlying molecules lead to ergodicity or not? Did it lead to the idea that you should visit everywhere or not? Now, one of the things is there's sort of an inconsistency between phase transitions and ergodicity. If this gas is eventually going to visit all possible configurations, there's no, if both the gas and the liquid are possible configurations, how come it doesn't visit all of those? And you have to kind of explain how ergodicity is broken in the case of a phase transition. And that was something that in the 1950s slowly got understood as a matter of physics. Well, in the beginning of the 60s, there was sort of a convergence in Moscow of a considerable number of sort of top Soviet mathematicians who were working on statistical mechanics, ergodic theory, dynamical systems, and some of the mathematical consequences of cybernetics and questions about the operation of machines. And a notable member of that, the sort of leading member of that group was Andrei Kolmogorov, a well-known Soviet mathematician. But one of the pieces that emerged from that work in 1968, there was a young kind of math competition winning mathematician named Andrei Thum, who wrote a paper called A Family of Uniform Nets of Formal Neurons. And the paper is written in sort of formal probability theory and study of Markov chains and so on. But basically, it's the construction of what amounts to a probabilistic cellular automaton and a proof that even though this is cellular automaton is probabilistic, certain aspects of its behavior are non-ergodic and effectively deterministic. Actually, Thum, before that, had done another construction of what's now called the Thum-Cook algorithm for fast multiplication of digits. So I need to speed up a bit here with the history, but should be able to get to the end fairly soon here. So in any case, one of the things that was true in traditional statistical mechanics, which was distinct from ergodic theory, distinct from this question of do you visit all possible configurations. Statistical mechanics was mostly concerned with what is the equilibrium configuration? What is the sort of most probable configuration that you end up getting to, for example, in the Ising model? And in the 1950s, there was the first sort of computer simulations of these kinds of things were done. The Monte Carlo method was invented. The Monte Carlo method was something where you're sequentially sampling configurations. Roy Glauber, for example, who I knew in 1963, suggested a way of making actual dynamics for the Ising model in terms of sequential probabilistic updating of spins. Effectively, that's a probabilistic cellular automaton that was being used to sort of explore this question of the configuration of systems. Well, there was a slightly separate branch led by people like an American mathematician named Frank Spitzer of probability theory applied to random walks. So I showed some of those cellular automata where there are these kind of diffusive behavior of random walks that eventually annihilate. There was a whole probability theory of collections of random walks, often called interacting particle systems. And the question of what would happen if you started off these random walkers, would they annihilate, would they not annihilate? And one of the main results was that as soon as non-zero probabilities were involved, ergodicity was typically found in those systems. So the apparently independent of those kinds of results, 1969, the group in Moscow produced a paper called Modeling of Voting with Random Error. So it featured a computation done on an electronic computing machine of the probabilistic evolution of a majority model. Quite possibly the machine used was the nicely exotic base 3 computer that had been built at that time in Moscow. But anyway, this is a computer simulation of the results of a majority rule probabilistic cellular automaton model. And the paper concluded that in one dimension, the model was probably always ergodic, but in 2 dimensions for sufficiently small noise level, it might not be. 1971, Roland Dobrushin, who was a student of Kolmogorov's, sort of connected the investigation of ergodicity in networks with phase transitions and Ising models. So connecting kind of the physics strand with this kind of more cybernetic strand. And he then sort of organized this program of research at his laboratory of multi-component random systems at the Institute for Problems of Information Transmission in Moscow. It sort of brought together the Soviet cybernetics tradition with its work on things like neural nets and Markov chains and formal computability theory with more international work on mathematical physics and ergodic theory. So a typical sort of example, I was kind of charmed by this, and there was a 1976 conference. I happened to have a copy of its proceedings. Actually, strangely enough, I bought it from a used bookstore, and I just looked a few days ago in the at the front of the book, and it turns out it was owned by Frank Spitzer, who I just mentioned, that particular copy of this proceedings. But anyway, it was a proceedings of a conference organized by Debrushin along with Toom and some others. It was nominally called Locally Interacting Systems and Their Applications in Biology. Actually, there's essentially no biology in this book, but it's sort of steeped in statistical, in sophisticated mathematics and things like Markov chains and Gibbs measures and algorithmic unsolvability and so on. So a key question that had emerged was whether any homogeneous array of probabilistic elements, like a probabilistic cellular automaton, could consistently and deterministically store information, or whether there would inevitably be ergodicity, that is, that the thing would inevitably just visit all states and destroy that information. So in 1974, Toom showed that there was a multidimensional probabilistic cellular automaton that could do this, essentially that majority rule in a non-symmetric neighborhood that I showed before. But the question still remained of whether anything was similar was possible in one dimension. 1976, a person called Boris Cyrulson showed that at least with a sufficiently hierarchical arrangement of elements, one could achieve sort of long-range order in a probabilistic one-dimensional system. And then Georgy Kadumov, having first sort of discussed the undecidability of ergodicity in the one-dimensional case, argued that there should be a pure cellular automaton, not a hierarchically organized thing that would work. And that brings us to 1978, when Peter Gacs, Georgy Kadumov, and Leonid Levin, all of whom had been in the Kolmogorov orbit, wrote a short paper entitled One-Dimensional Uniform Arrays That Wash Out Finite Islands. And that introduced this GKL rule that I talked about earlier, and showed a computer simulation very similar to the one that I showed earlier, that even when a certain amount of noise was added to the system, the consensus states would be reached. However, what had become known as the positive probability conjecture that had come out of the theory of interactive particle systems and so on, implied that there couldn't, in the end, be actual non-ergodicity in the one-dimensional case. Then in 1983, Peter Gacs came up with what he claimed was a counterexample based on a very elaborate construction described in many, many pages of pseudocode. That really is a very sort of computeristic, things sending mail to each other type system. So it took many years for this proof to clarify. Eventually, Peter Gacs published a final version of it in 2001, establishing that, yes, indeed, there was, at least in principle, some very complicated cellular automaton that could achieve this sort of deterministic result, even in the presence of a certain amount of noise. There's sort of a question, well, let me not go into that, of sort of how simple that can be made. And one of the things that was believed about cellular automata is that actually you would always need a complicated cellular automaton to achieve something like computation universality. I found that that was not the case. And even sort of among the very simplest possible cellular automata, there are examples of the examples which have been proved to be actually universal. Okay, so just going on a little bit here, and I'm almost finished. So I started working on cellular automata back in the early 1980s, and I think that made physicists much more aware of deterministic cellular automata. I really worked only on deterministic cellular automata. I had just a few comments in papers that I wrote about probabilistic cellular automata. And actually, I think it was at a conference, Peter Gacs can correct me if I'm wrong, it was at a conference that I organized in 1983 in Los Alamos that Peter Gacs first announced his result about deterministic behavior in probabilistic cellular automata. I think that conference was also the very first one ever to be devoted to cellular automata. So anyway, by the end of the 1980s, there was sort of a burst of activity in probabilistic cellular automata by a bunch of leading mathematical physicists applying sort of methods from statistical mechanics and particularly directed percolation theory, which is kind of a particular case of a probabilistic cellular automata, to the analysis of these systems. And there was awareness among those people of Toom's work and people started studying PDEs for the aggregate behavior of boundaries and things like the KPZ equation and so on, all these kinds of things. There was a burst of activity there. So then sort of somewhat independently of that, I think the problem of density classification came to the fore. And starting in the 1990s, density classification in 1D deterministic cellular automata was used as a prime example of a place where algorithms might be sort of discovered by things like genetic or other search techniques. So that was another strand of development that led to a bunch of investigation, and several people who worked on that are here today. So different direction, cryptographic protocols in the 1980s, people had started thinking about models for achieving consensus between agents, even in the presence of sort of adversarial efforts. And there was sort of increasing interest in kind of formal methods of parallel computation and their computational complexity and their fault tolerance. So by the early 2000s, there was work being done by people like Nick Pippinger on connections between these things and probabilistic cellular automata and sort of the possibility of deterministic computation in that. Yet another branch that I just became aware of a few days ago was people studying synchronization of fireflies and much beyond, people like Steve Strogatz and Duncan Watts. And they too had knew about actually the GKL rule and started studying this question of consensus for them is not going to one value, but synchronizing a collection of phases. All right, well, that pretty much takes us to the present time. And the interest in sort of new applications of this distributed consensus problem in blockchain-like systems. And it's interesting to see that there these rather different intellectual lineages have led to sort of the same place. And so, for example, with Sergei Popov, who's here today at IOTA, coming from kind of the probability theory and stochastic process direction, I believe he's a great grand student of Kolmogorov's. That's sort of one direction that has led to this. And another direction, Yilun Zhang at NKN, coming to this from a sort of statistical physics, computational neuroscience, information theory tradition. You know, I was interested, as I was doing history research about this, I found Yilun's, sorry, let me just, I had found Yilun's PhD thesis, and I discovered that my old friend Terry Sinofsky, who's a computational neuroscientist and a pioneer of deep learning kinds of things, was on his thesis committee. And so I mentioned that to Terry, and he said that he remembered that thesis defense well, and that he had, as he always does at these things, he'd asked Yilun what he was going to do next. And sort of he was expecting, because that was usually the answer, you know, I'm going to be a postdoc in lab XYZ. And Yilun said, well, actually, I have a startup. Well, that startup was NKN, and it's been a terrific story. And I think here to sort of tell us about it himself is our next speaker, Yilun Zhang, who's the co-founder and CTO of NKN Labs. So over to Yilun.
One sec. Thanks, Stephen, for your introduction. And hello, everyone. My name is Yilun Zhang, the co-founder and CTO of NKN. And let me, one sec, let me add the spotlight so you can see it better. So hello, everyone. I'm Yilun Zhang, the co-founder and CTO of NKN Labs. Sorry to say that twice. So today I'm going to talk about how we designed a cellular automata-based consensus algorithm for large-scale blockchain systems. So first of all, a bit of background for blockchain. So a blockchain network is basically a replicated state machine. It has a lot of nodes in the network, which is peer running the same running the same code or implementing the same protocol. Each node will store a history of blocks. Here, the block is a backward linked data structure. So when you know a latest block, you basically know all the you can uniquely identify all the prior blocks prior to that. You can uniquely identify all the block history prior to that block. So a basic operation that the blockchain network needs to do is to reach consensus about what is the current or the correct blockchain history. This can often be reduced to a binary consensus problem. That is, given the current block history, should we accept a new block proposal or not? One important property of the blockchain network is that we don't trust anyone. Actually, we will always assume that in the network, there are a constant fraction of malicious nodes. They try to perform Byzantine attack and break the consensus. And the consensus algorithm, whatever it is, should be able to tolerate such bad actors and still reach consensus under such attack. So currently, the most typical way of achieving strong consistency in the blockchain is to use a practical Byzantine fault-tolerance algorithm, also known as PBFT. So in PBFT, every node needs to capture the vote of every other node in the network. So from the information flows perspective, it is essentially a fully connected graph here. So the complexity is ON, which is not quite scalable to a large scale network. It might work well for, let's say, hundreds of nodes, but when there are thousands of more nodes or more, the algorithm might fail to work. And as we know that in blockchain network, the network size is very important. The larger the network is, the more secure it is, the more decentralized it is. And specifically for NKN, because it is a decentralized data transmission network, the higher throughput the network can provide. So we really want a scalable consensus algorithm that can scale to a larger network and satisfy our demand. So naturally, we will turn our eyes into CA if we want scalability, because that's kind of the natural advantage of cellular automata. If we look at some of the natural systems, such as like the biological neural network or the brain, or the swarm behavior, or like the spontaneous magnetization in physics, we can see that they all fit well into this graph cellular automata framework, and they can all achieve consensus in a very secure, reliable, and efficient way. So we know that it's definitely possible to find a CA-based consensus algorithm for blockchain. The problem for us is to find the correct topology. How are we going to generate the initial condition distribution, and what kind of updating rule should we use? So before we dive into the algorithm, let's first take a look at what is a good blockchain algorithm? What kind of metric do we have? So there are a few important metrics that we want to maintain. So the most important one is a consistency. That is, all the good nodes should eventually converge to the same state. And the second one is correctness. That we not only want it to converge, but also want it to converge to the majority of its initial state. And also we want the convergence time to be as short as possible. And as well, we also want the algorithm to be fault tolerant to attackers. And finally, we want the algorithm to be scalable to a large network size. So let's look at the basic one-dimensional GKL rule. As you have seen in Stephen's talk, the one-dimensional GKL rule will converge to the consensus state most of the times. But as we can see in this spatial temporal graph, there are some linear structure here. That means although it converges, but the convergence time is ON, where N is a number of nodes, or in this case, the number of cells in the networks. Well, ON is not quite satisfying. In a practical large network with, let's say, with tens of thousands of nodes and a regular communication delay, that would take hours to reach a single round of consensus, which is kind of too low, right? What if we go to two-dimensional? Well, if we have a two-dimensional space and still using the nearest neighbor rule, then the convergence time becomes O square root of N. This is a lot better than 1D, but still not enough. If we further go to D-dimensional space, the convergence time will be OD times N to the 1 over D. Eventually, when the dimension is approaching O log N, the convergence time is O log N as well. Well, that's a lot better and actually acceptable. The computer scientists will be happy about it. So as we can see that when we have higher dimensionality, we got faster convergence time. So what kind of topology we choose, it should have very high effective dimension to achieve faster convergence. Actually, there is a more fundamental relationship between the topology and the convergence time. If we look at the topology of the information flow graph, not the actual embedding topology, let's say there is a connection from A to B if and only if the state of B depends on the previous state of A. In such a topology, all rules are nearest neighbor rule by definition. There is no long-range rule. And, in such a diagram, the speed of the light is 1, and the diameter of the graph determines the information spread time. And the consensus convergence time on such topology should be OD, where D is the diameter of the graph, because consensus requires information to be spread. So when we have higher dimension, we are effectively reducing the diameter of the graph, and that's why we can get faster convergence time. So actually, there is a better topology than the high dimensional grid topology we have been looking at. That is a sparse random graph. If we look at the sparse random graph with average degree k being proportional to log n, where n is the number of nodes in the network, and the coefficient should be larger than 1 for it to be connected. The diameter of such graph is about log n over log k. In this case, it's log n over log n. So the diameter is quite small, smaller than the grid topology with the same degree. So it has very high effective dimension, and it is a very good topology for consensus because it has very fast convergence time. The protocol itself is very simple, much simpler than the high dimensional grid. And as we will see later, the topology itself, the random topology is very robust to attacks. One might ask whether there is a better topology than the random topology. Well, probably not. As we know that for a graph whose degree is no greater than k, the diameter of the graph should be no less than log n over log k minus 1. So in this case, we can just ignore the -1, and we can see that the random graph already achieved this diameter lower bound at scaling. Same for random regular graph. So that means there shouldn't be any graph that can have a lower diameter with same amount of connections. And the random graph is probably the topology we want to use for consensus. So we have chosen the topology, but what about initial condition distribution? Before the consensus start, each node in the network will have its own initial state. That initial state might be dependent on its local ledger or like local timestamp or other information. As we know that if we handpick some certain initial condition distribution, we might end up with incorrect or inconsistent consensus result. But luckily for the random topology, if the topology is really random, we can assume all those initial conditions, they are shuffled. And thus we will get a random initial condition distribution. All that matters will be what's a fraction of the node that are in one state and what's a fraction of the node that are in the other state. There is one important caveat though. We must make sure that the topology is independent of the initial condition distribution. A common incorrect example is that if we use the same topology for block propagation and consensus, then if there's something went wrong during the block propagation, we might get up the initial condition distribution that is somehow correlated with the rule, with updating topology, and we might end up with having some trouble. That's something we definitely want to avoid. So now let's take a look at the rules. So with random topology, we're kind of lack of any spatial structure, and the majority rule is probably the best rule we can do in such topology. It remains to be an open question whether there is any better rule for random topology to achieve consensus, but I would be very excited if there is. So now we have the basic component and to form up a basic version of the consensus algorithm. So we have a sparse random topology with O log n degree, and we have some shuffled random initial condition distribution, and we have the simple plain majority rule to update. So actually one can as we have shown in the white paper, one can like create energy function in the same form of ISO model in this case, and as the network up itself, the energy will be minimized and eventually go to the global consensus state, which has the lowest energy. So by using the random topology, we can kind of getting rid of all the local minimum and go straight to the consensus state. So as we can see in some of the simulation results, on the left side, we have like 1 million nodes in the network, and each node has around 10 neighbors. And each line shows a simulation run with different initial condition. We can see that whatever initial condition we choose, the network will converge to the consensus state in just a few time steps. Even if it's initially at 50-50 initial condition, it will still converge to one of the two states because the topology is random that can break the symmetry in the initial condition distribution. On the right side, we can see that when we increase the degree from 10 to 100, we are effectively reducing the diameter of the graph by half. And indeed, as we can see in the simulation, the convergence time is indeed about half compared to when we have 10 neighbors. So now we can introduce a malicious node into the system. So the malicious node, they are coordinated and purpose for attackers trying to break the consensus. So what they will do is that they will try to break one of the consensus property. They might try to break the consistency, making the network not converging at all, or they can try to break the correctness, making the network converging to the wrong state, or they can break the convergence time and making the network very slow to converge. Here we will assume that the attacker has a control of constant fraction of the nodes in the network. And all those nodes have shared information. They can perform coordinated action, and they can establish connections to any node they want, and they can send arbitrary message and reply to those nodes. So one thing to note is that the malicious node has no well-defined intrinsic state because they can send whatever state to different state to different neighbors. So classically, we can the binary voting can be considered as a density classification problem. But in this case, the density classification and the correctness can only be defined on those honest nodes, but not on the malicious node. We should also mention that the noisy or the unreliable node can be modeled as a weaker version of the malicious node. So as long as the consensus algorithm can deal with attackers, they should be able to deal with the noisy or unreliable node without any modifications. So there are attackers will try to attack on one of the three potential attack vectors in the consensus algorithm. That is, they could try to attack the topology, or trying to like change the initial condition, or trying to attack on the rules. So let's first take a look at attack on the topology. So one possible attack on the topology is that if the attacker can choose where they are in the graph, they can try to form a graph cut by the malicious node and cause the network to separate into multiple different components. For one dimension, the attacker only needs 2 malicious nodes in order to form a graph cut. In general, for D dimension, if those components are balanced, the attacker needs n to the d-1 over d malicious nodes, which is the number of nodes for a d-1 dimensional hypersurface. But if the components can be unbalanced, then the attacker only needs as few as OD malicious nodes, which is pretty easy to achieve. So that means the high dimension is helpful in mitigating the attack, but it's not enough to just stop the attack. But luckily, with random topology, we can make ourselves safe from topology attack pretty easily by effectively making the topology unknown to attackers. So what we want to do is that we want each node to get neighbor's state only using outbound connections. And also we want the node to choose another set of neighbors with 0 weight. So this is kind of like the dropout idea in the neural network. So for each consensus, we are effectively just using half of the topology, and those half are actually randomly selected every time. Another thing we can do is that we can that every node to keep their neighbor selection private and not exposing them to other nodes. And also we can ask them to change the neighbors frequently, so the topology is dynamic instead of static. So by doing this, the topology is not only random, but also private and dynamic. And we should also note that by having the private and dynamic random topology, we are not only safe from topology-related attack, but also we are safe from the initial condition attack, because handpicking the initial condition will require a knowledge of the global topology. If the topology is unknown, then then it is very hard to perform such attack. So with random and private topology, we can further simplify the attack models. Now we can assume the attacker has a constant fraction of the random malicious node in the network. And what they can do is that they can send different states to different honest node and try to break one of the consensus property here. In this case, whether the consensus is secure or not depends on two statistical factors. The first one is the fraction of malicious nodes in the network. Well, this is kind of easy to understand, but the next one is the next factor is the initial condition distribution among those honest nodes. This is not quite easy to understand, but you can think of it this way. If the initial condition among those honest nodes are pretty close to 50-50, then what the malicious node can do is that they can just set their initial state to the minority of the honest node, and then push the network to the minority to the wrong side, and the consensus result will be the minority of the initial condition. This will break the correctness of the consensus algorithm. So actually, the number of malicious nodes in the network must be smaller than the number of honest nodes in the difference of number of honest nodes in two different states. If this condition is broken, that means the malicious node can can successfully attack the correctness 100% of the chance just by setting their initial condition to the wrong state. We can see this by a simple example. So assuming there are like 9 honest nodes in red state and 7 in yellow state, and there are 4 malicious nodes. If they set their initial condition to red, then the red is the majority. But if they set it to yellow, then the yellow becomes majority. So they can pick their side and push the network to whatever side they want, thus breaking the correctness of the consensus. But on the other hand, if the initial condition of the honest node are more consistent, like in this case, we have 12 in red and 4 in yellow, then whatever initial condition the attacker set there to, the red will always be the majority and the correctness will not be affected. So with the random topology, actually the most effective way to attack the system is to attack on rules that is not following the regular updating rule of the cellular automaton. So the most effective way to attack the correctness of the system is to use something I call flip side attack. The attack is pretty simple. The attacker will set all their malicious nodes' initial state to the minority state of the network, and they will not change their malicious node state during the consensus, no matter what. The attack is considered to be successful if the honest node will converge to the minority state, thus breaking the correctness of the consensus. We can see that if the attack is successful, then the attacker can push the network to whichever side they want. And actually, they can do something even worse. They can carefully design their response such that they push the network to different sides at different time, such that the network will never ever converge to the same state. Thus, it will break the consistency of the consensus. Or they can try to hold the network for arbitrarily long time before making it converge to one of the state, and thus breaking the convergence time. So that means as long as the flip side attack is successful, all the correctness, consistency, and convergence time will be broken. On the other hand, if the flip side attack is unsuccessful, that means both the consistency and the correctness can be safe. So in order to check whether the consensus is secure or not, We just need to check whether the flip side attack is successful or not. So we can run the simulation for the flip side attack with perfect initial condition first. In the perfect initial condition case, all the honest nodes are in the correct state, while all the malicious nodes are set themselves into the incorrect state and does not change their state during the consensus. Each line shows a different run with different fraction of malicious node. And as we can see that when we increase the fraction of malicious node, eventually there will be a phase transition where all the honest node will converge to the incorrect state. On the right side, if we increase the number of neighbors or the degree of the graph, we can see that the phase transition still exists, but the transition point requires a more malicious node. So the attack is harder to do. If we consider all different fraction of initial conditions, then we can get this fault tolerance diagram. So the x-axis here is the ratio of malicious nodes, and the y-axis here is a ratio of honest nodes that are in state 1. So we can see that there are two regions here where the consensus can achieve both correctness and consistency. While in the middle region, this is a region where there is a way for the attacker to break both the correctness and the consistency of the consensus algorithm. So whatever we decide to do, we should definitely put ourselves in these two safe regions here in order for the consensus to be safe. We can compare the result with PBFT here. On the right side, we have the diagram for PBFT. One important difference for PBFT is that as the PBFT can guarantee consistency as long as the ratio of malicious node is less than 1/3. So it means it has this middle region where the consistency can be guaranteed, but not the correctness. That means all the good nodes or all the honest nodes will eventually converge to one state, but that state does not necessarily is not necessarily the majority of the initial condition. So far we have been assuming the synchronized update, but in the real world system, almost everything is asynchronous and all the communication has some non-trivial time delay. But in our case, because we are using the random topology and just the plain majority rule, we are not utilizing any spatial structure or information. Therefore, the asynchronous update is not a problem for us, but the time delay might cause some trouble. In the case where the initial condition of the network is close to 50-50, some of the nodes might enter the state oscillation and does not converge to the consensus state. What happens here is that a node might send out a state update to its neighbors. Before that information arrives at its neighbors, it changes to a new state and send out the new update. It can do it with very high frequency and not converging at all. So this would cause some trouble for the convergence. But the solution is actually quite simple. We just need to learn from the biological neurons. So in the neurons, whatever input it gets, it always has some sort of like minimum spiking interval between two adjacent fires. So that interval is actually much longer than the time required for the signal to arrive at its neighbors. So we can actually do the same thing in our system by adding that enforcement that a node cannot, a node has some sort of like minimum state update interval. That interval should be much longer than the time delay for the typical communication. So in this limit, we can essentially like ignore the communication delay in the time scale of the state update, and thus having the same behavior as the synchronous, as a network without any delay. So finally, we are coming to the consensus termination. So if we know that the consensus will eventually be reached, but how does a node in a network know when the global consensus of the network has already been reached using only its local and neighbors information. In addition, we also want all nodes in the network to make the conclusion or make the same conclusion as closely in time as possible. Well, this turned out to be a very hard problem. The working solution we use is that we just use a fixed delay since the consensus start. As long as the delay is much longer than the consensus convergence time, which is typically less than 1 second, then we know that after the delay, the global consensus should have already been reached. But this is definitely not an elegant solution. Whether there is a better or more elegant solution remains to be an open question here. So now we have got all the components we need in order to design and implement the algorithm. We have implemented this consensus algorithm and named it MOCA, short for Majority Vote Cellular Automata. We open sourced it on GitHub as part of our full node implementation, so you can check it out if you're interested. And the consensus, MOCA has been live on public network for 3 years, and it is now powering NKN's mainnet, which has around 100,000 consensus nodes globally, which is the world's largest blockchain network. So on the right side, you can see geographical distribution of the NKN nodes in the world. So with this beautiful graph, it is end of my talk. And if you're interested, you can download the open source code and contribute one more node to the network. And thanks for everyone for your time.
Thank you, Yilun. Hello, everyone. I'm Christian Pasquel. I'm Director of Connectivity at Wolfram Blockchain Labs. And I'm here to introduce our next speaker. We now have Pedro Paulo Balbi. He's a professor at the School of Computing and Informatics, Mackenzie University, Brazil. So thank you for being here, Pedro.
Thank you, Christian, for the introduction. Thanks, Stephen, for inviting me to this very nice meeting. I need to share my screen. Okay, so what I'm going to talk about today is I'll give 2 very short reviews about 2 well-known benchmark problems related to cellular automata in the context of achieving consensus. One of them has already been introduced by Stephen, which is the density classification task. And the other one is the parity problem, in which instead of willing to know which is the state with the more largest occurrence in the configuration, you want to find out in a binary configuration whether the number of ones is an odd or an even number. So I'll try to make my time here half in each of these, although the density classification task, there will be a lot more to talk. So first problem, just to set the ground here, when we refer to density classification in its standard formulation, its original formulation, we are talking about the one-dimensional case in which the configuration is fixed and cyclic. And we want the convergence to go to either zeros or ones, depending on the state in the initial configuration, which is the prevalent. So you can, this same standard formulation, you can have it in other dimensions, but the whole start of the problem was based on this. As Stephen mentioned, there are bad news about this problem. As he said, it has been proven that no single rule can solve this problem. And further to the original proof in 95, there was also a proof that you could extend the problem to the k-ary case beyond the binary case. And the k-ary case cannot be solved either. And the same guys who proved this, they also put forward arguments that the k-ary d-dimensional case couldn't be solved either with a single rule in this fixed finite configurations in cyclic boundaries. So these results are all about the original formulation. So what happens if we relax some of these elements, some of the elements that make up the original formulation? That's what we're going to look at now, of some of these relaxations. The first one is by using Rule 184, which happens to be a number conserving rule, as mentioned earlier, meaning that the number of ones just go around during time evolution, but they do not change. So if you relax the periodic boundary condition and have a fixed boundary condition, then you can solve it with just this rule. And the way you do this, you on the right-hand side of the configuration, you set 1 bit, and on the left-hand side, you set a 0 bit. If you do this, it suffices to look at the center cell, and then you can decide what is the prevalent state in the initial configuration. Of course, when you do this, you let go of the consensus kind of situation, but it is a solution to the problem. So in fact, it can solve it even with a configuration with n even, where the configuration size is even, in which case you have to look at the 2 center cells in the configuration. Okay, another possibility. Instead of using a single rule, now you would allow a change of the rule during the temporal evolution. In fact, the first one that people came up was this one. In fact, it was by Henryk Fukś, who's going to talk later today, in which you first apply Rule 184, which kind of rearranges the ones, and then you use 232, which is the local majority. So if you do this, you can always solve the problem with, and there are various other solutions. I worked in this problem later on after Henryk's results, and we found various other solutions with 2 rules, with 3 rules. And everything, in fact, boils down to this graph, where if you start here with one of these 2 rules, 184 is symmetrical to 226. They are both naturally number conserving. And if you start with either of them and follow any path in this graph, then you would have a solution. This possibility of sequencing rules or changing the rules along the evolution can be further extended, and it was further extended to allow solution of any rational density instead of just the one half. And also you can use this for the K-area DCT. So it's a very powerful approach to allow changing the rule along the way. Okay, now instead of having a deterministic update, so we're back to the original formulation, but now we are allowing the state transitions to be stochastic. And this is it's a proposal by Nazim Fates, who is also here with us today. And the way it's a radius 1 rule, and the way we read this is as follows: if the position is black and the right-hand side is white and the left-hand side neighbor is black, then with probability P3, the central cell continues in the black state. So we see that there are two stochastic state transitions here, and the other ones are deterministic. And if you do this, everything happens as if there was this stochastic mix between the traffic rule, which is 184, with the local majority rule 232. So it's a nice result in the sense also that it brings us back to the original solution of changing the rule along the way. In fact, the situation here, the solution, so to speak, that is achieved here is, you don't get it actually. What you get is that you get a solution as good as you're willing to wait for. So that's the whole point. So it's a very nice approach to this problem. Back to the original formulation. Now we are relaxing we are allowing different rules in different positions of the configuration. So we had two sets of configuration here, the ones on the right-hand side and it's analogous on the left-hand side. And in order to convey what's going on here, let's consider that the positions are being named from x1 to xn. And if we assign rule 184 to all the positions from x2 to xn minus 1, we fix these have a fixed rule. But what happens is that to the positions in the end of the configuration, then we can we alternate as you wish different rules depending on one extreme sees as the neighbor on the other extreme, and here as it sees the neighbor on the other extreme. So because we have four possibilities of these two, seeing zeros and ones in the other extremes, then we can we have all these possibilities of rules. And the nice thing about this is that you can pick any rule from each of the columns. So there's a bunch of all these combinations of rules that would allow the solution of this problem. These people also generalize the solution in 2 dimensions, and so it's a very nice result. This is another possibility that you would, in a sense, allow more states to solve the binary problem. The construction here is actually based on two tracks, so to speak. So in one track, which receives the initial configuration, again, rule 184 is run. And then you have this other track running a very simple rule, local rule F2, which is very simple, but it's linked to what's happening in on the other track. And as you do this, it works all the time, and everything happens as if you would have 4 states. So in a sense, you increase the number of possible states in order to solve the binary states. There is, just to mention, people in the University of Chile also have a solution with the continuous number of states from 0 to 1. So this is another possibility. Okay. Back to the original formulation, we know we cannot solve it, but we can ask which would be the best possible imperfect rules. And so along the years, many rules have been found by various means, mostly by searching the space of possible rules. And just to don't trust these numbers very much because they depend, since you have to sample the space of possible configurations, there is a high dependency on the size of the sample, the distribution of the sample, the actual size of the configuration. So, but to give you a feeling, currently, apparently, the best rules we have an efficacy. They can guess right what's going on in the initial configuration for about 89% of the configurations. So this is some results we found some years ago, also doing an evolution research in the space of possible rules. Okay, these are the landmarks that I wanted to set for about density. And now let's turn to parity determination. So parity is simpler. And in fact, it can be solved. This is a radius 4 rule that we found some years ago, and there was a glitch that we recently corrected, and it works. It's radius 4. We know parity cannot be solved with radius 2, and we don't know yet whether it can be solved with radius 3. So this is an open question. We can also solve the parity problem, but also by sequencing, changing the rules and elementary rules once again. And this result was put forward in 2001. Later on, we managed to simplify these results. You see that various rules are involved, including 184 once again. And with this scheme, we even managed to generalize even further this problem beyond the parity, because you can think of parity as being the mod 2 problem in a sense. And so we came up with a solution for an arbitrary mod n solution, also based on this changing of rules as you perform the computation. More recently, with a work with Eurico Ruivo, he's a colleague of mine at the university, and we've been working close together recently, and this is a solution based on asynchrony. So the kind of asynchrony we are referring here is a deterministic, so-called block sequential asynchronism, which is basically you take all the cells or the positions of the cells and you create a partition of these sets of positions, and you assign a priority to these positions so that the cells will be updated in different times, but all deterministically. And the way we solve parity here is based on the following. It's rule 150, which is actually the local parity rule. And we update first the cells in even positions and then in odd positions and go on changing like this. What I find particularly neat about this solution is that it's a way of solving the global problem, the parity global problem, with the local parity rule. And in addition, changing the updates from even to odd, even, odd, and so on. So it's I find this very, very nice. The way this works is first, if we have here this initial configuration, the first thing that happens in the proof is the convergence of the center cell. Then some time goes on, and then the whole configuration becomes symmetrical. We see here, taking the center cell as a reference, the configuration on the left-hand side is reflected on the right-hand side. And then after some time, then the convergence starts to spread out over the lattice. Okay, this is another solution of the parity. It's an asynchronous solution based on it's a non-homogeneous CA. In fact, in different positions you have the local parity, and in other positions you have the local parity of radius 1 and the local parity of radius 2. And what happens here is for different sizes, these are the graphs. These are non-regular graphs, of course, because it's you have different rules in different positions, but they have a well-defined way of being defined. The way we do this, it goes like this. We represent the graph like a CA linear kind of representation, and which I'm depicting here. And each point here represents one node of the graph. And what we see is that there is this, the graph that is made, it has this symmetrical. It is symmetrical as we see on the left-hand side, the representation here, it's reflected on the right-hand side. And the way we represent the two positions is based on the relative position of for instance here, node 1 receives an influence of a node that is a distance P1 from the left-hand side and distance P1, red P1, from the right-hand side. So these relative positions, these pairs of relative positions, they follow a specific set of possibilities. And this is the situation. In fact, there are two solutions for this problem. The first one is based on when the size of the configuration follows this form, 4k+1, in which you would have graphs like this, and the other possibility is when you have 4k+3, this form, the size of the lattice. So it's possible to visually see this kind of symmetry in the graph, and but this is well characterized. It's just to give you a glimpse of what happens. So this is the kind of graph, the temporal evolution we see, and the way it works. One solution is like this. First, the center cell is, which is even position, in this case, for k+1. The center cell gets converged to the parity. Then this convergence spreads to the two neighboring positions after 2 time steps, and then it goes on spreading along the configuration. At this point, all the positions in odd, which have an odd index, converge, and after that, then the positions in the even positions are converged. In fact, the even positions don't have to wait for all the odd positions to converge, but this is the way this proof is made. For the other case, the 4k+3, it's a little bit different because the nature of the graph is different. So the center cell converges, and then the extreme, the end cells converge. This is then passed after 2 time steps to the neighboring position, and then you would see again this situation of the convergence to the odd positions, and then the even positions. Okay, this is a pretty new result. We're still preparing the paper, but this is the whole idea. So, okay, we have these landmarks that there would be a lot more to talk, but which would be the lessons that we would have from this? So first of all, parity is easier than density, and I like to think about this is that in terms of automata theory, in order to recognize parity, all you need is a finite automaton, whereas you need a push-down automaton, which is a more complex machine that encompasses the finite automata, in order to be able to process and to recognize the difference of quantities. So it's probably this. A very important thing to bear in mind is that the solution depends on the formulation, as we see in all these results. And so, even though we have this, and we may have further bad news about new problems we come up with, we should always try to change the formulation in order to be able to solve the problem. Fixed boundary is easier to handle than periodic because it's more constrained. Composition of rules has been shown to be very effective. because you can combine different aspects of different rules, which is one in terms of the DCT, density classification task. Right. In terms of density, it's interesting that number conserving rules usually tend to play a role. And in fact, if you analyze good, though imperfect rules in DCT, and it's possible to define a degree of conservation of these rules. What we see is that good rules, imperfect rules have this high degree of conservation. And so all this issue here of number conserving rules playing a role in this problem, this has to do with the possibility that you would have to wait some time for information to process, and so that what the situation in the initial configuration would be shared among the cells, and then only then take a decision. So this is the kind of situation behind. And of course, there are still various unknown results on the CT, and we could define others in parity as well. Like I tried to come up with a solution of density in terms of asynchronous, the kind of deterministic asynchronous block sequential updates that I mentioned. And I have results showing that there's no solution with radius 1 and neither with radius 1.5. But the whole problem remains open. Also, non-uniform CA with cyclic configurations. I also have some computational experiments pointing at the impossibility, but it's still open. And you can think of many other things like CA with memory. There are results in trying to add memory to number conserving rules, and you get very good results, but apparently there's no solution so far. So, okay, that's it. That's what I wanted to convey, and we can, so that we can discuss these points later on. Thank you very much for listening.
Great. Well, these were two very interesting talks. I think now we have some time for questions. And I see we have a whole bunch of questions here that have come in, and maybe I can be the one to at least distribute the questions, because I'm not going to be able to answer most of these. There's a question here from Gabriel. I think this is probably mostly for Yilun, but maybe for all of us. Could cellular automata be employed to attack the problem of finding a potentially superior topology paradigm? What would that endeavor look like? What resources will be required? Yilun, do you want to try taking that one?
Sure, I can try. So I would say definitely yes, but I would say it's possible, but it should probably be hard, because as we can see, finding the topology, I think that for the topology, there is a trade-off. On the one end, we can probably find the topology and some kind of a rule with very like kind of tricky structure, and it could be highly effective. But on the other hand, those effective rule or topology might not be fault tolerant enough in the sense of the attackers. So it's kind of like the GAN framework. You have a system try to optimize for a goal, but you have another attacker or adversarial effort trying to fight against that system, and eventually you probably have two sides evolve mutually and at the same time, and both attacker and the system itself will get stronger. So probably the proper way to find such rules is to have a framework that can have both attacker and have the system design evolve at the same time, and finding the optimal both the optimal structure, optimal topology, optimal rule, and the optimal attacker for this problem. Yeah, that's kind of what I was thinking, but that's kind of just the idea, and I've never done anything related to that yet.
You know, one comment I might make, this is very related to what we have been studying in our physics project, because in our physics project, the whole structure of space in the universe is thought of as a hypergraph, and all the kind of communication is happening through updates of this hypergraph. And in fact, one of the things, to give an example of something vaguely related to this question of how do you adapt the topology, how do you adapt the graph based on sort of what's happening in the universe, so to speak. I'll give you an example, which we found recently. So when you solve partial differential equations, for example, the Einstein equations for gravity, the usual way of doing it is you start from the partial differential equations, and then you make a kind of computational discretization, and then you sort of from the outside kind of adapt that computational discretization, making a finer mesh in places where there's rapid variation, things like that. But you do that from the outside. What's really interesting in our models of physics is that the actual structure of the network that we believe underlies actual physics, in a sense, adapts itself. In a sense, the very process of in this particular case, increasing curvature of space-time is associated with essentially adding nodes in this hypergraph. And so what usually you would think of doing from the outside, of saying, I've got to just make an adaptive mesh where I'm changing the structure of the network from the outside as a sort of algorithmic thing. In the case of our physics project, we can see that process of kind of progressively refining the mesh is happening just as a matter of the dynamics of the system. And we can apply the same kinds of things. It looks like we can apply the same kind of methodology to solving a bunch of partial differential equations. So the thing that I think about here is you've got this network, and the question is, can one have rules that not only change the configurations of the cells, so to speak, the configurations of the nodes, the colors of the nodes, however you characterize it, but also actually by virtue of what's going on in the network, change the structure of the network. And we have a great example of that in the physics project, both for physics, initially for gravitation theory. We also looks like we can solve stress equations that way also. But so I think the thing here would be to think about as things are happening in the network, and potentially as there are sort of intentional events being injected into the network through people potentially attacking the network or whatever else, how can one have local dynamics of the network itself, local graph rewriting of the network that can deal with those kinds of things? That's the way I would think about it. Now, I don't have any results about that, but that's I think it's a actually really interesting problem that is potentially, what we've been doing in our physics project, looking at all these hypergraph rewriting kinds of processes and things, is for the sake of essentially doing natural science. It's not for the sake of doing engineering. That's a kind of an engineering application of that kind of methodology. And that's what I would hope for is something which sort of locally can adapt the network topology based on the actual sort of on what's actually going on in the network. That would be my thought about that. But we don't know how to do that yet. That's a interesting thing to explore in my view. Let's see. We had another question here from Elias. The question here, maybe this is also for Yilun. There's faster convergence with distributed consensus, but at what cost? More network resources are consumed to retrieve the values. I don't think that's true, actually, but Yilun, maybe you can say something about that.
Yeah, actually on the opposite, it used far less. Well, let me share the slides again, maybe. Let's see. So if we compare the consensus algorithm with, let's say, PBFT, then we get far less communication overhead. Actually, it's kind of the when the network size goes to infinity, the ratio that our communication, the communication we use compared to PBFT goes to zero. But actually the cost is, as you can see, this center region, where in PBFT you have this consistency guarantee that even though the correctness cannot be guaranteed, the consistency can still be guaranteed. But in CA-based like consensus algorithm, you kind of lost that middle region. So in this region, as long as the correctness can be attacked, the consistency can be attacked as well. That's kind of the price you pay for having this scalability and efficiency.
Interesting. Okay, so we have another question here from Matthew Blumberg. The question, I think, is also for Yilun, is can you comment on the electricity requirements of the NKN consensus mechanism versus other blockchains such as Bitcoin and Ethereum? I have to say, it is one of the strange phenomena of my life. You know, I started in the 1980s talking about this phenomenon I call computational irreducibility, the fact that you can sort of have to do an irreducible amount of computational work to get results. That kind of idea, it's sort of deeply rooted in computation theory and lots of other kinds of things. But I have some considerable reason to believe that in the original invention of Bitcoin by Satoshi Nakamoto, that he was aware of my whole effort in computational irreducibility. And if I had imagined how would computational irreducibility be used in the world, I had thought of it as kind of this theoretical thing related to limitations on kind of what one can make predictions of scientifically and so on. I never would have imagined that a few decades would go by and pretty soon there'd be giant amounts of electricity being used, essentially burning computational irreducibility to for purposes of Bitcoin and so on. But with that preamble, perhaps Yilun can comment on the NKN consensus mechanism and its kind of electricity requirements and so on.
Yeah, so I would say it's not specific to NKN, but any CA-related consensus algorithm. Compared to Bitcoin, I would say it's literally zero electricity usage, the ratio. Well, you know, Bitcoin used kind of a proof of work to reach consensus, and it used just massive amount of electricity, and it can saturate what kind of, no matter what, like, no matter how many computational resources you have, you can just saturate all of them just to reach a consensus. But for any like CA-based consensus algorithm, you just need a few state update or a few like communication between your neighbors in order to reach a single round of consensus. That use almost no CPU, no memory, almost no network communication compared to the proof of work. So, well, compared to Bitcoin, it's almost just zero electricity cost. And actually, for those like 100,000 nodes, many of them are pretty lightweighted nodes, such as like a Raspberry Pi or smart router, and it just takes a tiny amount of resources for them to reach consensus globally.
So we had another question here from Senri, asking about whether we've all looked at the avalanche consensus approach to consensus. I think if we haven't looked at it so far, we have a speaker this afternoon, Emin Gün Sirer, who is I think going to talk about, is one of the creators of that idea and is going to talk about it. So we'll learn about it then. There's a question here about, is it possible for cellular automata to achieve reliable consensus under non-deterministic noise and pernicious attacks? I think we talked a little bit about that and about the results that exist so far on that. The answer is, we don't know the optimal way to do it, but we certainly know the beginnings of how to do that. And as a practical matter, you know, NKN has the actual instantiation of these ideas up and running and able to make use of that. But there's still, the reason for this conference is there's still lots of interesting and important research questions that have to be answered about those kinds of issues. And that's kind of what we're talking about here today. So let's see, we had another question here from Anders. This is also a Yilun question. Is NKN efficient for distributed computing?
So I would say what we have been talking about is efficient for reaching the consensus, but distributed computing is more like off-chain stuff that it doesn't require consensus, right? If you want to compute something, you don't want every node in the network to do the same computation, just like Ethereum or other on-chain computation does. The more efficient way is that you should distribute that amount of work to one or a few nodes in the network and does that. So that thing has nothing to do with the consensus. Yeah, so I would say it's probably not quite related to consensus, but it's more like how do you efficiently distribute work to the off-chain node and let it does it.
I think it's an interesting question. I mean, the Ethereum world's slowest computer approach of, execute the smart contract with every single node having to agree on the result. I think, consensus is kind of case zero for this question of, can everybody agree on can you get reliable results from the computation? I think there's probably a bunch of interesting things to be done in understanding, given the NKN network, for example, what would be needed to have believable results from smart contracts that were executed on some number of nodes and had some way of combining things and so on. I think that's probably, perhaps some of Peter Gacs's work on reliable computing might be relevant to that. I don't know, so in other words, what's the, consensus is sort of the minimal computation that you might do. What can you do if you're doing, and again, Pedro's conversations about parity, that's another example. What if the smart contract you wanted to execute was trying to execute a parity operation? Then you would have a similar, then you'd be using sort of the second part of Pedro's talk to try and address that. But what if you had different kinds of functions you were trying to compute? What are the optimal ways of doing that in sort of this distributed fashion? We don't know that, at least I don't know that yet. But that seems like a very interesting thing, which is a potential sort of overlay of sort of smart contracts meets kind of the distributed blockchain idea.
I have some comment on this. So typically there are two ways to do this like computation without everyone do it again. So one way is to use some kind of like trusted hardware such that you can get a proof showing that the result you get, whatever it is trusted as long as the hardware is not broken. And another idea is that you can, if the computation fits into certain framework, then it can kind of, you can kind of verify the result using a tiny amount of resources without recomputing it again, but not, of course, it's kind of not universal. So as long as you can fit into this result and you just need a tiny amount of resources to verify the result, then you can use a consensus framework to let everyone reach consensus about the result that one node or just a few node compute. But otherwise, there might be, you kind of have to find another way to do that.
See, I think it's analogous, sort of a similar problem. People have studied error correcting codes forever for just you're storing data, how can you check for errors? The next level of question is error correcting CPUs, so to speak, where you're doing actual operations and somehow you have a way of doing error correction on the computation that's happening. And I think there's these are fairly, I think they're fairly sort of deep questions, but I think there are things that can be, I'm expecting there will be things that can be figured out from that. Now, let's see, we've got a couple more things here, and I think we should try to wrap up soon for this Q&A period. We'll have another Q&A period later. Let's see, Elias is commenting on, might not noise help reduce the risk of Byzantine attacks, since you probably need a very specific scenario for it to be pathological? Yilun, do you want to comment on that one?
So am I right that it's about noise and the Byzantine attack? Right?
Yeah, the point being made is if there's noise in the system as well, it's going to blow up whatever devious scheme the Byzantine attacker would have had.
So I typically don't consider them separately. I consider them together as an attacker. So as I said earlier in the talk, you can just think of noise as attacker. It's just like not that smarter attack. It's kind of like a random attack, but it's still an attack. So if the framework or like whatever you're studying can handle the Byzantine attack well, then you can just, let's say, you can handle 30% of the attack, right? And now if you can think of that 30% of attacker as 10% of the noise plus 20% of the actual attacker. So it's kind of, as long as you can handle the Byzantine attack, you kind of can handle everything else because it's the worst of the case.
I think the comment there was that if you imagine a space of Byzantine attacks that involve particular algorithms being used, many of those algorithms would themselves not be immune to noise. That is, the algorithm, if you imagine not sort of the arbitrary Byzantine attacker, but an actual algorithm of a Byzantine attacker, that their algorithm is likely to be blown up by noise, I think is the...
Oh, okay. I see. So my intuition is that any almost algorithm that is not immune to noise would probably not immune to Byzantine attack.
Yeah, I'm sure that's true, right? I mean, okay, let's see, we have a couple more comments here. Oh gosh, from Suvik, rules like Rule 232, the pure majority rule, manages to achieve a little local consensus, but ultimately not successful global consensus. Can we break the situation by using non-local neighborhood conditions? The answer, I think, maybe Pedro can comment on that in more detail, but I believe the answer is there isn't a fixed configuration of neighbors that can succeed in doing that. But the whole point of these the whole point of these graph things and dynamic graphs and so on is to change that story. But maybe Pedro, can you comment on that with the pure majority rule? Is there a way of sort of reconnecting it at different points to achieve global consensus, even just with that rule?
Well, we a few years ago we ran some experiments trying to using the local majority rule, but in different topologies, particularly over small world type networks. And we could see that there was an improvement. There were certain, there is a parameter that you can use to define a range of small world type networks, a family of them. And we could show that within this range, the local majority rule performs better than in arbitrary situations, in particular, the CA type networks. So
interesting.
Yeah.
So let's see, Sukanta Das is commenting that under asynchronous updates, a cellular automaton may reach consensus for a class of initial conditions, but not another class of initial conditions. The system may reach consensus with some probability. Maybe a small set of configurations for which it will not reach consensus. So I think the point here is for asynchronous updating that can we comment on sort of the probabilistic results for asynchronous updating? That is, given with asynchronous updates, can one simply say that in the deterministic case, we know, given a particular initial condition, whether it will reach consensus or not. But for the asynchronous case, we don't have a deterministic result for a given initial condition. We only have a probabilistic result. I guess there's a question here about how that set of probabilities would change in what we know about the evolution of that set of probabilities. Maybe Pedro has a comment on that.
Well, I think that this makes all much sense. In fact, I think one student of Sukanta approached this right problem, showing that this kind of situation happens, if I'm not wrong. So I agree with depending on the rule, you can have these situations that some configurations converge and some others don't, and some others within certain probability. I think this makes a lot of sense. And it's probably, you can model this in specific case. That's the point.
Interesting. Okay, Suvik has another question. I'm also curious about this for Pedro. are there solutions for the leader election problem in elementary cellular automata? And the comment is, people have solved this for D-state complex cellular automata. Can you maybe just say what the leader election problem is, and maybe comment on that?
Well, I don't know which is this problem. I know it exists, but I don't remember which problem is it. Maybe Suvik could tell us.
Fair enough. Is Suvik here on our internal session? I think they are. So
yeah, the problem is that starting from initial configuration, there are a lot of ones and zeros. Suppose we are considering one-dimensional binary elementary cellular automata. So at the convergence point, there will be only one cell in state 1 and the rest of the cells are in state 0. So we can think about such as converging situation. So at the converging point, there is only one state in state 1 and the rest states are 0. So finding out a leader out of many ones.
But in other words, you're picking that leader. It can be any cell that is that leader. Is that right? I mean, I think there's a set of other problems. Another one is the so-called firing squad synchronization problem of, you start the cellular automaton off and you want all the cells to reach a particular state at the same time. That has a bunch of interesting solutions that involve typically very nested patterns where you're kind of building up this nested structure, and then you'll finally get agreement. So that's a question of, for example, in the NKN network, if one wanted something where all the nodes were somehow synchronized at some particular time, how would one achieve that? That would be an example where you would need this kind of firing squad synchronization problem. And I don't know of results. The solutions to the firing squad synchronization problem are quite fragile, to my knowledge. They're not things where people don't yet know kind of a robust solution to that problem. All right, we should wrap up here very soon. Let's see. Let's see. There's a question here from Dylan. Cellular automata may reach consensus for some initial configurations. Let's see, but modifying n as iterations continue change the results. So I'm not sure. Oh, I see. This is again questions about dynamic networks and what effect dynamic networks have on reaching consensus, which I think is an interesting problem that is still kind of out there as a research problem. Maybe we can wrap up here with one last question. And I noticed one here from, I noticed one, hold on, from Ku, asking for the dummies guide to NKN. And asking for kind of maybe Yilun can say a few things about kind of the importance of NKN and kind of the significance of what's being done with the whole NKN distributed system and so on.
Okay, let me try to summarize it really short. So the first thing that is most relevant to this conference, of course, is that we have a extremely scalable consensus algorithm that can essentially reach consensus for any arbitrary practical number of nodes within very short amount of time with very minimum resource usage. That's the first thing. And the second thing is that as the NKN itself is a decentralized data transmission network, it enables any peer to send or receive data from another peer without relying on any centralized like server or like infrastructure. And that essentially what is the value that NKN provides to this decentralized ecosystem. Yeah, I would say that's two, if summarizing 2 sentences.
Maybe you can say, what are your favorite applications so far that you or other people have found for the NKN network?
So it's okay. I have probably 3 favorite apps here. The first one is Mobile. So it's kind of like decentralized instant messenger, like a Signal, but decentralized, no server. We use it for our internal communication between like developers. And the second thing is like Nconnect. So if like when you are outside your home, you can use Nconnect to connect to your device at home or like your computer at home and work as if you are in the same local network. And it makes things like so much easier. And we use it daily. And the third thing is probably is something called Surge. Surge is kind of like a decentralized BitTorrent. It's built by the community. You can share like files on it. It's an awesome like application.
Okay, I'm just curious if you can sort of draw the line between, you know, what if BitTorrent had used distributed consensus, so to speak? I mean, what is the, you know, when you think about kind of the BitTorrent-like application, where's the place where you can kind of immediately see the high value of kind of a distributed consensus approach?
Okay, so I would say in my opinion, what really the distributed consensus really adds when you're considering incentive, because without incentive, you're kind of assuming everything is like not malicious, everything is friendly, you're just doing everything on voluntary base. But when you add consensus, you kind of have it has like token or money involved. Then you kind of has a way to reach agreement on how to distribute the incentive, which person should get kind of the reward for doing what kind of thing. Those things are typically the real that needs to reach a consensus globally, and that cannot be done easily without an efficient consensus algorithm.
Which is what we're talking about here today,
yes.
Finding the most efficient consensus, distributed consensus algorithms. All right, we should wrap up this Q&A and continue on to our next speaker. And I think Christian is going to introduce our next speaker.
Yes, thank you all for the questions and answers. So our next speaker is Vero Estrada-Galiñanes, Associate Professor of Science and Technology, University of Stavanger, Norway. I hope I got the pronunciation correct. Thanks, Vero, for joining us today.
Thank you for the introduction. Let me share the screen. Okay. So, okay, I think now it's working. So thank you for having me. Today I will talk about towards dependability in decentralized storage systems. As Christian introduced, I'm at University of Stavanger, Norway, although I'm giving the talk in Switzerland because actually I'm relocating to Switzerland. Dependability. So what is dependability? Well, the quality of being able to be relied on or trustworthiness. So what is trustworthiness? I like the definition given by Schneider, which is trustworthy is a holistic property, so encompassing security, correctness, reliability, privacy, safety, and survivability.
I think you might be sharing a different screen from the one you think you're sharing. I just wanted to point that out. Maybe you're sharing the correct screen. I'm just concerned.
Okay.
Your presenter notes were showing.
Yeah, sorry for the problem. Is it now working?
Looking
Yes.
good.
Sorry?
Yes, looking good. Yeah.
Okay, sorry. So I was talking about trustworthiness. So it involves a lot of properties: security, correctness, reliability, privacy, survivability. And we all know the difference between centralized, decentralized, and distributed systems. Otherwise, we will not be here in this conference. And so the question is about designing a decentralized system that includes mechanisms that protect data. So it includes either data redundancy mechanisms and incentivization to provide a dependable system. So I have been working in resilience, so in doing the design of error correcting codes that increase the redundancy of a system. And most recently, I have been working on integrity and the intersection between integrity and availability. And also we are starting a new work with a new PhD students on fairness, basically on the study of how the incentive mechanisms work in a decentralized systems, and we are planning to do some work with cellular automata in that area too. We stand on the shoulders of giants. So the giants of modern crypto was Alan Turing and Claude Shannon in information theory. Now, for the young people in the audience, I want to highlight what was the context of them when they were working in measuring information and in developing coding and decoding methods. This was a storage system. This huge hard disk could store only 3.75 megabytes. Now, we are 70 years later, so we could say, can we store 1 megabyte on the Ethereum blockchain? Well, actually not. Doing some numbers with the current price of the gas and the current price of Ethereum, so it gives us a price of almost $50,000. So yeah, this is not possible. So what we actually do is to develop reliable, decentralized peer-to-peer networks where we store data in what we say like is off-chain. So that was part of my work. Actually, I have been working since my PhD in protecting data and different ways of protecting data, and against what? Well, against many things. It could be errors, human errors, it could be negligence, it could be censorship, it could be malicious attacks. So when I started with this work, I thought, okay, let's think about 6 impossible things before breakfast, and why not to double? So my list of which properties or features for error correcting system or erasure code that protects data in the current storage system was too huge. So immediately I got advices that I should be shorten this list of properties, but I insist, and that was the motivation that led me into the study of entanglement codes. So I have been working mostly 5 years on the development of these codes that are mostly based on graph theory, on the design of graphs. And yeah, there's a list of publications for those who want to check later on. And now let's go back to current storage system. So what happened in a system that works like still BitTorrent? So if you have some popular content there, the content will be replicated because everyone will be downloading it. But if I store something in the data that is not popular, my data will not be replicated. So what can I do? What is the best way to protect this data? Well, what you can do is to give the user some resources, something to control the redundancy of this data, or to store this data multiple times, or in current systems like now incentivized systems like Filecoin or other systems that are being developing, we use incentivization. That means that paying the nodes to store the data, no, because the storage is not free. So let me summarize in a slide what are the main ways of doing the protection, the data protection. One is replication. And replication, we can see it if we see it in a way of a graph, as to have these blocks in parallel. So basically, if we think in the system as a black box and we are asking to the system, give me this data, and we expect that the system gives the chunk or the file that we are asking for. If we have the data replicated multiple times, that means that the system, inside the system there will be multiple paths to read this data. In the case of erasure coding techniques, is a combination of serial. So in the previous case, it was an equivalent to have this data in parallel path. In the case of erasure code, we have serial and parallel path. Why serial? Because in erasure code, basically what happens in a system is that if somebody is uploading a file to a system, the file is first is split in small chunks, and then is expanded with some data, some redundant data that is computed with this encoded algorithm. And to recover this data, if this data is missing, we need a minimum quantity of chunks. That is why these chunks are in serial. In this example, we need a minimum of 6 chunks always. So if there is a failure, I will need to download 6 blocks instead of 1 to repair the chunk. So we have replication, we does parallelism, we have traditional erasure coding techniques that does a combination of parallel and serial combinations of chunks. And the idea of entanglement codes is why don't we do both? We combine this in a more smart way, so we can use less bandwidth when there are no errors or there are not many errors, and we can have many more combinations of paths to recover the data when there is huge errors. So the idea is that a chunk in a system or a file that is uploaded to the system gets entangled, gets mixed with all the other files that are in the system. But obviously, this cannot be done directly with all the files, because this will not be very efficient. But there is a graph that is doing the encoding in a way that is more efficient, and I only need to have some small number of operations each time I'm encoding a new chunk or a new file. So to sum up, in replication, the replication is very straightforward. It's a very popular way of getting redundancy in a system, but it's very expensive in space requirements, because we need, every time we want to increase the redundancy in the system, we need to add copies, and it's not good for in that way, it's not very good for long-term storage, because it's also very expensive. But it's used in many systems, like in BitTorrent, in logs, in blockchain itself is a replicated distributed ledger. The Swarm Ethereum system replicates content also, and IPFS also is doing replication. Now, so if a chunk is missing, then we have the other paths, as we mentioned before. Now we have erasure coding, and erasure coding, I'm not explaining the details behind that, but it's based on arithmetics that are based with on Galois-Fields operations. So also for students, when I'm teaching this course to students, it's much more difficult, and many times I found developers that say, "Oh, I'm just treating redundancy methods as a black box. I don't want to know anything about, because it's complicated." And this is also one of the things that we want to solve by using cellular automata. I will talk about later. So the benefits of using erasure coding is that there are minimal space requirements because of these arithmetics, this magic with the Galois fields. But the problem is that it's expensive in terms of bandwidth because it requires these serial combinations of chunks. So it is still used in many systems, Dix arrays, in the HOELab's system, and there are other systems, decentralized systems that are planning maybe to use it in future. But in general, in peer-to-peer, it's not recommended because of the problems of bandwidth and repair. So if one chunk, as I said, if one chunk is missing, now we have to download all the chunks of another possible path to read the whole file that we want to read. Now we have alpha entanglement codes. In alpha entanglement codes, the operation to create a redundancy is based on XOR, an exclusive OR, bitwise exclusive OR between the data or file that we want to upload to the system and a previous block. We call it parity block or redundant block that is in the system. I will show in detail in the next slide. The storage overhead, it has the alpha entanglement code has a parameter that is called alpha, and that's basically tells the storage overhead that the system has. So if alpha is free, it means that for each block that data block that we are adding to the system, we have alpha additional blocks added. And the repair cost is constant. That means that for every single failure, we need 2 blocks to repair the failure. And we have multiple paths to recover the file. So if any of these paths are broken, we cannot reach it. We have a large number of paths that can keep growing. And it's worth to say that although these paths are larger, that means that there is a larger serial combination of blocks to do the repair. Because all the blocks are entangled together, and basically in the system, any single block can be seen as in the center of this concentric path that I'm showing. While we are doing these repairs, we are actually repairing in other blocks. So that makes the repair very efficiently in terms of bandwidth. So we are working, so this was the work in my PhD thesis, but now there are continuation of this work for the second part of this talk that I will talk in detail is the work with Racine Nigar and collaborations with Yilun Zhang. And we also have 2 master students who are working on this, but on the IPFS network. So how does entanglement works? Basically, when we are uploading a block or a file to the system, we create some redundant block. The first block can be seen as just a copy of the block, and then the green chunk is added to the system. And to create the new redundant block, this redundant block is basically the XOR of the previous 2 blocks in this chain that keeps growing. So basically, we have now in this chain of 6 elements, we have 3 data blocks, distinct blocks, and 3 redundant blocks that keep containing that keep propagating information because it contains the XOR of the previous data chunks that were in the system. Now, how do we evaluate this? If we want to compare this code with other codes, usually to evaluate the reliability of the system, a common method is to use Markov models. So we use Markov models and we compare these simple entanglements. So in simple entanglements, there is only one chain, so the parameter is alpha 1. As I said before, alpha 1 means that for each chunk, we are adding one additional chunk that is redundant. And how these Markov models work? Well, we have, in this case, in this example, we have 6 states. So one state is the complete data loss. The state 0 is the state where there's no failures. And then to do these transitions, we need actually to solve a Kolmogorov system of differential equations, and we need to also compute alpha, beta, and gamma, which will depend on the probabilities that failure patterns that we cannot recover will appear, because this alpha, beta, and gamma will actually move us towards situations where there is a single, double, 3 or 4 failures. In these systems, we assume that 5 failures cannot be recovered here. So with a single chain, this is very easy relatively easy to solve, because we have to analyze all the irrecoverable failure patterns in this chain. In this model, we create a graph, which is a simple path where the edges are the redundant blocks and the nodes are the data blocks. And these are these ones that I show are irrecoverable failure patterns. Now, with this, if we solve the Laplace transform of this Kolmogorov systems of equations that I showed before, we can calculate the mean time to data loss. And by having the mean time to data loss, we can calculate the reliability. And the reliability, it will be a number, usually we say, like, for instance, 3 nines reliability. That means that 99.9% of the time I will recover this this data, and this is computed. This is computed during a certain amount of time, in which we assume that at the initial time the system was in 0. There was no errors, was working perfectly. Now we want to have more reliability, increase the reliability. Actually, I didn't mention, but in our paper, we measure that simple entanglements with the Markov models behave much better than this mirroring, which is like the equivalent of replicating the data only one time. And in both systems, this mirroring and simple entanglement has the same storage redundancy. But we wanted to design a system that tolerates catastrophic failure. So we needed to create much more redundancy. And that comes the design of complex entanglements where alpha is greater than 1. And these complex entanglements are formed with intertwined data chains or entanglement chains. So basically, each data blocks belongs to alpha chains that are created while doing the encoding. So at each time I'm uploading a data block, instead of growing 1 chain, I'm growing 2 chains. So I'm XORing alpha times with the last element of the chain. The interesting thing of the design of entanglement codes is that the graph that can be used by the decoding is different. So we create encoding very efficiently by only having in memory having the last element of the chain and doing this XOR. But with the decoding actually can use a graph that where all the interdependent chunks form part of this concentric path, and where we can use any of these paths to read the chunk that is in the middle. So if the chunk that is in the middle is missing, we can use the closest, the paths that are close to the center, which are shorter, or if the file is very, if the failure is very large, we can use the longest path. So this is another view of the encoding graph. So basically, when we are considering all the paths of all the chains that are created by entanglements, what we have is a lattice as I'm showing here, and basically we can imagine that this lattice is on top of a cylinder, because actually the connections, the nodes that are on the top and the nodes that are on the bottom are connected by helical strands. So what happened with these complex entanglements? If we want to use Markov models are not very helpful, because we need to analyze all the kind of all the possible irrecoverable failure patterns that can appear in this structure, and this is very complex. So we have tried other approach. So basically, we tried measuring the reliability analysis based on combinatorial methods. We have said that in replication we have is equivalent to have blocks in parallel. In erasure coding we have blocks in series, and entanglements we have a combination of both. And we did these comparisons, and we also use graph transformations and Gacs methods to verify these results. The problem with this is that the result actually undersells the real reliability of entanglement codes, because of the complexity of doing this computation. We actually prune many paths, many possible paths, and this pruning actually undersells the possibilities of entanglement codes. So actually our results say that entanglement codes achieve 13 nines in comparison to Ritzel among 14 nines for the current for the current settings used in this system. However, when we did experiments and we did simulations, actually entanglement codes could protect much better the system, the data. So we try another approach, and then that brought me to cellular automata. So what is the best redundancy method to protect data? Now I'm thinking not in current storage systems, but I'm thinking in a system that is under a particular set of conditions, because usually when we think in comparing methods with traditional methods with Markov models or combinatorics, it's very difficult to start playing with characteristics of the network, like the network churning, like if there is a lot of nodes that are leaving the system, or if we have an attack, or there's a lot of dynamics, and I was attracted by cellular automata because I thought that cellular automata will allow me to play with all these dynamics, and that actually brought me to the work of Stephen Wolfram and start working on this actually as a side project. It was actually when I finished my PhD that I decided to take the summer workshop with Stephen and start working on this. So it was always at the beginning a side project. And I developed this framework that I call FARDI because it's failure repair dynamics. And it's also because I wanted to have a fair framework to compare different encoding systems. And I wanted a design that encouraged experimentation and that facilitates also the understanding of the topics to junior students or to developers, to people from computer science. They don't necessarily have all the background, the mathematics background to understand how codes behave. And I also want to have a tool that is helpful to the industry as well as to the researchers. So in this framework, a cell represents a chunk of data, a file, or a storage device. So healthy cells, in this case, are blocks. And the idea here is that I let the system decay. So I wanted to understand what happens if the system doesn't receive any maintenance. And then I start playing with another module that has the system that actually injects failure, so makes the situation worse. And the objective is like to know which mechanisms can slow down the system decay, or which mechanisms make the system decay faster. So I use different probabilities that the cell will be dead. And so this is a one-dimensional cellular automata where one line represents all blocks in the system, so all files, as I said. And I also use the concept of a bucket because in certain cases, for certain redundancy systems, we have one bucket is one file, and I look at what happened in that file. In the case of entanglement codes, I need to use various buckets to decide what's going on, how these cells do the transition to the next step. And I defined the block availability factor, which is basically the density of cells, of colors, black colors in the line. And what happened in the storage systems is that the block availability factor can be maintained. This is the ideal case, can be maintained in while. That means that all blocks, all files are readable and can oscillate at the beginning, depending on the speed of repairs, because this is also something that I can tune in this framework, how I do the repairs in the system, or it can decay very fast. So for the case of replication, the transition rules, basically, if I have 3 replicas, basically, well, it's very easy to see that replication 0 means that there is no failures. So the next line, there will not be failures. And if at least I have one cell that is black, it means that in the next level, I can recover again all the replicas by doing the replication that was missing, but I can recover the file. And in R7, I cannot recover the file. In erasure coding, like read Solomon codes, for example, in this case, I have an example of a code that can tolerate 2 failures. So as long as there are less or 2 white cells, I can put all the cells in black. But all the other cases, the system on the next step, nothing happens because I cannot recover the data. And in the case of entanglement codes, this is much more complicated. As I said, I need to use the neighborhood as far, but as I mentioned before, when repairing, I'm using only two chunks only to do the repair. So if there is one failure and certain particular chunks are available, I can do the repair. So there's different transitions rules. These are actually some of them that I'm showing, but they are all similar like this one. So with this, we build a proof of concept with transitions rules for various codes: replication, read Solomon codes, regeneration codes, pyramid codes, and entanglement codes. we play with different repair policies that can be in the systems, like lazy repair. That means like I leave the repairs as long as I can read the data with maybe not very fast, but because I lose some redundancy, but I can do the repair. So I postergate the repair. Eager repair is as long as I detect one failure, I repair, and then different other repair policies. So I built this in Wolfram notebooks. One thing is that I assume that every block is stored in a different place, but we are thinking in doing in future work include placement. So I mean, it includes that these cells can be stored in some cells can be stored in the same place. And we have random fault injection, and this can also in future work be improved with different type of failure injection. And there is a manuscript that I can share on request. And it was also presented, this work was also presented in a poster. Here we see that with Solomon codes with different toy examples, the system decay very fast, but on the right, we see that if we use, for instance, a large cellular automata with 25K stripes, it takes longer to have block loss, but anyway, all the systems anyway decays, and then that's what I'm interested is somehow having the speed of how the system decays, because that is easy to compare with other codes or with other settings with the same code. Since I don't have much more time, I think I will go faster. So the other work that we did based on this was a bachelor thesis, where the students create a web platform in Python, and they did replication, read Solomon codes, pyramid codes, and this platform allows to compare different experiments and different could be different codes or the same code with different settings. And it allows also the downloading the data to more analysis. So the takeaway of this was that the cellular automata can help in bridging the gap between the communities, because I found that most of these communities, like information theory, storage, and cryptography communities, they are doing the same, but with different angles, different perspectives. And when I try to discuss with people from different communities, it's kind of hard. So I found that cellular automata could be very helpful in this. It is also very helpful to teaching junior students these kind of topics that otherwise are left for graduate students. So on integrity and availability, so very brief, I'm working with Merkle data structures. This is the work done with a PhD student, Racine Nigar. So basically, Merkle data structures are very important in decentralized systems because they are used to verify the integrity of the data. This Merkle data structure is computed in a tree at the Lie level. We have the real data, and then to create the tree, basically we are hashing the data and then hashing again the children until we reach the parents. And it has plenty of interesting uses because we can use it for content addressing. So basically the root maps all the leaves. So we only need to share the root to then locate the content in the network. Then we can use it to random access, because once we have the root, and if the network implements the content addressing the lookup, we can also access a particular chunk. it is useful also for the storage peer, because the storage peer needs to verify that it's storing the chunk that is supposed to store. So if he has this address and the chunk that is in he has the right to store that in this address space, and this chunk belongs to this and has and the hashing corresponds to this address. Okay, it will be stored. And it can be used also for efficient chunk verification. That means if a downloader is downloading a chunk and wants to verify that this is a chunk or the file that really wants to download, it will use it will only need some nodes to verify. So that was an example of a binary Merkle tree, but actually what we use is a larger k-array Merkle tree in the network. Why? Because actually all the internal nodes in the Merkle tree are metadata, and what it interests us is not to grow the large metadata. So this example, we see a 12-array Merkle tree. And what is the problem? The problem is a cascading failure. So if we lose one of these internal nodes, we cannot locate the data. So the current solution now is high levels of replication. And as we can see in our own cluster, we measure we have 1,000 nodes of a swarm network. And we have seen that nodes applied replication, but it's a decentralized network. We cannot expect much, so the replication is uneven. So some chunks are replicated 9 times, some chunks are replicated 150 times. We also have uneven placements. That is expected that if the peer maybe is larger, that can be distributed better. But we have uneven placements. So some chunks, some peers actually, if we lose a peer, we will lose many nodes, many chunks, sorry. For instance, we have some peers that have like 12,000 chunks stored, while others are storing 200. So there is an underlying problem with the redundancy, is that we have inefficient storage utilization, because if we have a good storage utilization, we can attend more clients. We can have more files in the system with the same storage devices. So our solution was to merge redundancy methods with this Merkle tree. And the problem is that if we add redundancy methods to the Merkle tree, the redundancy will also require metadata, that this metadata needs protection too. So there is a chicken egg problem. So finally, our solution includes the design of a resilient data structure that reduces the impact of hierarchical dependencies between chunks. We also develop a prototype, which is a storage component that can use for the user to control the redundancy, to add more redundancy. And it works on top of standard decentralized systems like IPFS or Swarm. And we also demonstrate that we can improve the storage utilization of the underlying storage system. So we have done a prototype. I cannot disclose more about the solution because actually we are submitting a paper and it will be hopefully in a couple of months published. So, and the last is our ideas about using cellular automata to benchmark incentive mechanisms. So we talk about fairness. Why fairness? Because we want that peers behave well, and we can use incentive mechanisms actually to motivate the peer to behave well, but will be really a good thing to do. So actually, what incentive mechanisms provide better dependability? Or what trade-offs occur when the systems will punish free riding? Free riding is a peer that is actually not paying and is using the system. And there's also other questions that we want to answer is like, is a single incentive mechanism adequate to nodes that are providing different services? Here we can think about storing data for the long term or storing popular data. This is a completely different service. So can we use the same incentive mechanisms for providing these two services? And then the service cost, how can we measure the impact of price transparency and node reputation? So we want to understand in general, what is the impact of these token-based incentives on decentralized systems? For that, we are thinking of using cellular automata. So there have been some works on cellular automata modeling computer networks. And these networks are very simple. It's basically, the model is node cells and link cells between the nodes. So some nodes are closer to each other, to others. And okay, that's a good start, but it's not enough for us. Because in our case, we are working with complex routing algorithms, for instance, academia algorithm that uses XOR to find the distance between nodes in the network. So basically, each node has a routing table, and they use XOR to reach far peers in the system, far in the terms of XORing. So on the right here, we see a tree that represents how the nodes are jumping from one node to another until they reach the destination. And that is how, like, for instance, one node will transmit one data to another node. And so basically with this algorithm, nodes are classified in different buckets. The buckets that are some buckets are closer to nodes and some buckets are farther. And yeah, this is the final slide. What we are trying to do is to map this algorithm into cellular automata, not necessarily the traditional neighborhoods, but what we have found is that if we codify the index of the networks with grade coding, and we use as a neighboring this torus for the bucket index, so then we can kind of use this neighborhood for all of the nodes in the system. So we are working with still toy examples with 32 nodes, but yeah, these are just initial ideas that we are doing with Bahit Lakhani. So this is all for my presentation.
Thank you very much, Vero, for your talk. Now I want to introduce Henryk Fukś, Professor of Mathematics at Brock University, Canada. Henryk, thank you for being part of this event.
Okay, thank you very much for introduction. And I would like to thank Stephen Wolfram for inviting me. So let me just share my screen here. So I hope my screen is visible. Could you confirm, please?
Yes.
Good. All right. So I would like to talk about certain ideas which we already heard about in previous presentations. So please ignore my long title here. I guess it's the longest title in this conference, but I would really like to talk about two aspects of consensus problem and density classification problem. Namely, I would like to talk about density classification on infinite lattices and about solution of density classification with more than one rule. And both of those ideas were already mentioned in previous talks. So if we have any sort of classification problem with cellular automata, we want to do the following. We have certain property, and if the initial configuration satisfies property Q, then after a certain number of iterations of the cellular automaton, we should reach final state A, and otherwise we should reach final state B. So for the density classification problem, this property Q obviously is whether we have more zeros than ones, or more ones or zeros, and those two states are all zeros or ones. Now, this is typically now done for density classification on a finite lattice, and usually periodic boundary conditions are used. Although Pedro mentioned that one could use fixed boundary conditions in a modified problem. But what I would like to do is to approach this from a sort of more formal way as a mathematician. And usually what we do in mathematics, before we answer the problem, we try to set it up in the proper space, right? So what would happen if instead of such finite strings as we are typically considering, what would happen if we have somewhat nicer space, namely the space of infinite strings, infinite binary strings, let's say, extending in both directions to infinity, so by infinite strings. So let's consider that variant, such variant of the problem, of the density classification problem. So let's consider infinite lattice, and then the question is, how do we construct initial condition? What are the strings we want to classify? Well, the simplest thing we could do is to impose some sort of a measure on this set of infinitely long strings. And of course, the most obvious one would be a Bernoulli distribution, and I will do that. So I will assume that we start with Bernoulli distribution. I will denote this by mu p. What Bernoulli distribution is simply is that we set each side to 1 with probability p, p will be our parameter, or to 0 with probability 1 minus p. So p will play the role of density. And if we start with such initial configuration drawn from such distribution, density is always defined. Because if we have just a doubly infinite string extending to plus and minus infinity in space, it is easy to construct strings for which density is undefined. But here, if we do it that way, we'll always have defined density. Now, I will use the following symbol to study this problem, the following notation to study this problem. I will denote by Pn of A a probability of occurrence of a given block or word, which is just a finite sequence of symbols, after n iterations of a rule. So n is a number of iterations, and A is the block, and Pa is a probability of the block. Now, if we have Bernoulli measure, obviously, probability of 1 initially at n equals 0 is P, and probability of 0 is 1 minus P. And again, here P, which I will refer to as density, is the parameter. So for solving density classification in such setting, we would like our system to converge to all zeros or to all ones, depending on P. If P is less than half, we would like to converge to all zeros. What does it mean? Well, it means that after infinitely many iterations, probability of 1 should be 0, right? So it should be all the way up to, if I plot probability of 1 after infinitely many iterations as a function of my density, then it would be 0 all the way up to half. And then in this area, we would like our system to converge to all ones. So it should be 1. Probability of 1 should be 1, right? So what we have here is sort of a step function, as you can see, with discontinuity at half. And here's the problem. What this P infinity is, it's just a limit of Pn when n goes to infinity. But for typical cellular automaton, this Pn for finite n is a continuous function of density. But here we have a discontinuous function. So what we really would like to get, we would like to get a sequence of continuous functions which in the limit converge to something discontinuous. Now, how does it work? How does convergence work in a concrete situation? So let's say that we consider rule 232, which is a majority rule. And what I did here, I plotted probability of occurrence of 1 after n iterations for n equals 0, so the initial one. And of course, then it's just p. So it's equal to density. So it's a straight line, diagonal straight line. After 1 iteration, it's this blue line. Then after 2 iterations, it's a green line. And as you can see, it converges very quickly, and it converges to this red curve. And the red curve is a curve which has known equations. So we know it is possible to determine what exactly this curve is. Now, and that's something like that, what you see here, is a very typical situation. When you take any other cellular automaton for which this probability Pn converges, because of course, sometimes it doesn't converge, it doesn't have to converge. It might oscillate, for example. But if it converges, it's typically like that. So those Pn's, as I mentioned, as you can see it here also, they are all continuous functions, and we would like to get them to converge to something discontinuous. Now, this by itself is not a problem. In mathematics, we know examples of sequences of continuous functions which piecewise converge, and yet the limit is discontinuous. But the problem is, in cellular automata, convergence of those curves, of those functions, Pn, is typically uniform. And we have a result in basic analysis that if you have a uniform convergence of functions, then they converge to a continuous function. So in other words, we can't get something like that for cellular automata. And the reason why the convergence is typically uniform is that those Pn's, they are actually polynomials in P, and very well-behaving polynomials. I will show you some examples later. So we can't have that. But let's take a look at this again. And if you are familiar with basic ideas of statistical physics, you might think that this resembles a curve which is often presented in books on phase transition theory. And indeed, this is something what physicists would call a first-order transition. Think of the horizontal axis as, let's say, temperature, and the vertical axis as volume of water. And the transition is at 0 degrees. And we know that at 0 degrees Celsius, water abruptly changes volume because it becomes ice, right? So there is a sudden discontinuous jump in volume. And volume could be called order parameter, and this could be called control parameter. So in our problem, we would like to have first-order transition. If we wanted to have a solution of density classification, we would like to have a first-order transition where P, the density P, plays a role of control parameter. And this P infinity 1 is our order parameter. Now, something like this is not possible, as I already mentioned. So what is the next best thing? Well, if we cannot have a first-order phase transition, maybe we could have a second-order phase transition. So the second-order phase transition would look like this. So we would have here still some sort of singularity at this point, but the function would be continuous. What is discontinuous in this case is the derivative. As you can see, derivative here is 0, and here it's non-zero. So there's a jump in derivative, but the function remains continuous. Can we have something like this? Well, I have no proof of this, but I think the answer is no. For binary cellular automata, I studied them extensively. I did some search, and I don't think something like this can exist. Maybe for rules with very large radius, I don't know, but I have not seen it in rules which have reasonably small radius. So what is the next best thing then? If we cannot have this, we cannot have this, what can we have then? Well, if we replace this 1 here by some other block, longer block, let's say pair of 1s, or pair of 0s, and we ask, can we have a phase transition of the second order if the order parameter is a probability of longer block? Then the answer is yes. Indeed, we can have that. And we can actually have this already in elementary cellular automata. Here's an example of such transition occurring in Rule 184, which we already heard about in Stephen's talk and in Pedro's talk, if I plot probability of occurrence of 1-1 after any iteration against density, then initially this is a parabola, this black curve when n is equal to 0. Then it becomes the blue line, a green line after 10 iterations. And after infinitely many iterations, it converges to this piecewise linear function. So this actually is red here. It's covered by other curves, so maybe you don't see it, but it is actually something which looks like a second order phase transition. And there are some other rules like this. Among cellular automata, among elementary cellular automata, actually it's only 184 and 226, which is a reflected version of 184. So now, can we actually prove that this is the case? Because what I plotted here, I plotted exact values of this Pn, or exact curves for Pn, and this is exact curve for P infinity. How do we obtain this? So I would just like to show you how it's done, because that's something which I've been working on for many years, and I tried to obtain expressions for those block probabilities for cellular automata rules, different cellular automata rules. And it is sometimes possible for many rules. For roughly half of elementary rules, I was able to do this, and rule 184 is one of them. So let me show you how it works. Just very briefly, the idea. So how do we compute PNA? We use construction which is known in measure theory and ergodic theory as a push-forward measure or transfer measure, or sometimes it's called Ruel-Perron-Frobenius operator. And it is a very simple idea in the context of cellular automata, and I guess that the names of it sound more complicated than it really is. So if we have a space of bi-infinite binary strings, typically it's called configuration space, and a local function, which is binary function of 3 arguments, returning another binary value. So we can associate with it a global function f, and global function is simply a function which takes bi-infinite string, applies the rule, and returns another bi-infinite string. What is more important than local global function for my purpose is something what I call block evolution operator corresponding to local function. And I will show you, so here's a formal definition of it on the slide, but it really is easier to see on examples. So let me just show you an example of this. If I take a finite fragment of bi-infinite string, like this one here, and I apply the local function to all sides, I will be only able to determine values after application of a rule of those sides which are in the interior, because this one here, I don't know what's the left neighbor. This one, I don't know what's the right neighbor. So if I apply my rule, the only certain thing will be that after one iteration, I will get this fragment, and the rest is undetermined. So the operation of taking this block and returning this block, I will call block evolution. And for rule 184, if I take this, then of course I return a block which is 2 sides short. Now, pre-image of a finite block A is a block B such that f of B equals A, where f, this bold f is a block evolution operator defined as I showed you here. Pre-image of block will be denoted by f inverse A. Now, the Ruel-Frobenius-Perron equation for cellular automata is something which is almost intuitive and very obvious. Namely, it says that probability of block A at iteration n+1 can be expressed as the sum of probabilities of pre-images of A under my rule. So see here, the sum runs over all pre-images of A, and of course I say B belongs to f-1 because f-1 could be a set. There could be more than one pre-image, and indeed more often than not, there is more than one pre-image. So now this is, of course, a recursive equation. And if I iterate this all the way back to 0, I will get expression for Pn. Pn will be simply a sum of P0b, where the sum runs over all preimages of A, but not single-step preimages, but n-step preimages. So what is n-step preimage? Well, it's a preimage defined exactly like here, except that we iterate n times instead of 1. So this is a very nice formula, because if I now know what those preimages are, if I know their combinatorial structure, so to speak, then those guys here, P0, are very simple to compute. What those P0s are? Well, P0 is the probability of block at the beginning, and at the beginning we start with Bernoulli, right? So P0 of A is just P to the number of ones in A times 1 minus P to the number of zeros in A, and that's it, right? So as long as I know what to sum over, this is trivial. P0 is trivial to compute. Now, how does it work for a concrete case? Well, here's an example of such expression for P0, P1, P2, and P3 for rule 184 for block 0, 0. And as you can see, all those are polynomials of increasing degree, polynomials in P. Now, if you know something about the structure of preimages, you can often figure out what those polynomials are. And sometimes they are very nice polynomials, like Lucas polynomials, other known polynomials, but more often than not, they satisfy certain recursion equations, and often it is possible to figure out what's the general formula for Pn. Without going to details, for rule 184, we can indeed do that. So we can figure out what exactly is the formula for Pn for example, block 0, 0, and it's shown here. Those are results which are from my very old paper from 1999. In fact, only the first 3 are in that paper. This one, blue here, is something newer, which I obtained later, and I had never published this. Why do I list probabilities of 0, 0, 0, 3 zeros, and 0, 1, 0? Well, it turns out that those block probabilities are not all independent. If you know those 4, you can compute probabilities of all other blocks of length up to 3 using something what is called Kolmogorov consistency conditions. It simply means that other block probabilities are just linear combinations of those 4. And here's a little curiosity, for symmetric measures. So when we have exactly the same number or same proportion of ones as zeros, when P is half, then those equations reduce to something much simpler, where there is no longer any sum. So, having those, how do we explain the existence of phase transition? Yeah, in a very simple way. We simply take the limit of this expression when n goes to infinity. And those limits can be computed. The way it's done, one uses so-called de Moivre-Laplace theorem, which is a well-known theorem in probability theory, which allows you to basically estimate those sums occurring here by integrals, and those integrals can be evaluated. And one can actually show that, for example, for P0, 0, if P is less than half, you get something non-zero, otherwise you get 0. And the same thing happens for other block probabilities, for 1, 1, let's say, for 1, 0, for 0, 1, 0. Those probabilities all behave differently for P less than half and P greater than half. And here is an example of how it works for 0, 0, 1, 1, 1, 0, and 0, 1, 0. So as in previous graphs, the black curve is the initial probability, initial state when we have Bernoulli measure, and then it's green, blue, n equal 1 is blue, n equal 10 is green, and the limit is red. So as you can see, very nice singularity develops in all those probabilities here and here. Here also in P10, we have a singularity in the sense that derivative doesn't exist here. It's a continuous function, but it's non-differentiable at the transition point. Now, one can study this transition in great detail. This has been done. I did this with some coworkers, and indeed, it's this transition is called the kinetic phase transition. It has all signatures of phase transitions encountered in physics, except it's a little bit simpler than typical transition. So one can find scaling relations, universality, and one can find conjugate field. For those of you who know something with statistical physics, that maybe tells you something. Anyway, it's a nice second order phase transition. Okay, how do we use it then? So that seems like, at least in elementary rules, that's the best transition we can have. Transition in block probability is longer than 1. Well, in his review of density classification problem, Pedro mentioned that the first proposed solution of density classification with 2 rules involved exactly rule 184. And the reason why this construction worked is that we first use rule 184 and exploit that transition happening here at point 5. We exploit that transition, and this transition actually carries over to finite blocks. It turns out that in finite situation, if we define density to be just sum of states of cells divided by length of the lattice, I denoted this by rho. So what happens then? We get no 0,0 blocks if rho after many iterations. No 0,0 blocks if rho is greater than half, and no 1,1 blocks if rho is less than half. So once we do this, once we get rid of so-called excessive blocks 0,0 and 1,1 or 1,1, we can then apply just a plain majority rule, and it will grow 1,1 blocks in the absence of 0,0 blocks, and 0,0 blocks in the absence of 1,1 blocks. So this can be all stated in a formal way. I did this here on the slide. It comes from my paper from '97, and you can actually even give formulas for the number of iterations required for each of those rules. But you can see it on this picture much better. What happens here is that if rho is greater than 1, blocks of 0,0 are eliminated. You can see that they are all gone. They are eaten up by blocks of 1,1. And then we are left only with blocks 1,1. And then we turn rule 232 and it grows them. We get all 1s. And in this case, we get all 0s. So that's how it works. That's how we can exploit the second order phase transition theorem in cellular automata to construct 2-rule solution of density classification. Now, phase transition like this are very common in, well, I should say fairly common in cellular automata. And if you increase neighborhood size, for example, in binary rules, you will find a large number of rules exhibiting transitions like that. Sometimes there is actually more than one transition. There's an entire cascade of phase transitions. And I will show you some a little bit later. Now, also, if you increase the number of states, you can also have rules exhibiting transitions, and they could be used to construct. They could be used for the purpose of complexity engineering, to construct solutions of problems like density classification. Here's an example of this. In the case of 3 states, if we have 3 states and nearest neighbor rule as before, then we have, of course, a huge number of possible rules, so the order of 10 to 12. But interesting class among them are rules with so-called additive invariants. Again, it has been mentioned already that rule 184 is a number conserving rule, so it conserves the number of 1s. So if we want to look for transitions, interesting transitions, we better look for number conserving rules also in the case of state 3 cellular automata. And I would just like to show you some interesting ones which I found working with a student of mine, Roman Procik, trying to find some sort of generalization of density classification. We found, for example, a rule which has this long Wolfram number right here. It's a rule with 3 states, nearest neighbor, and here's the exact rule table of it. This is a rule which actually reduced to rule 184 if you restrict states to 1 and 2. This column here is exactly like in rule 184. Now, what this rule does, it is a number conserving rule. And all number conserving rules can be reformulated in so-called particle representation or Lagrangian interpretation. This is a term which comes from fluid dynamics, where we have Euler and Lagrange interpretation of the same fluid flow phenomenon. So what is the particle interpretation? Well, here what you see is a state fragment of the lattice at T and below at T plus 1. And 0 is interpreted as empty. 1, a single particle. 2 is 2 particles. And what this rule actually does, it does something very simple. If you have a single particle and it has a single particle to the left, it will move to the left. If there are 2 particles, one of them will move to the left no matter what. That's all it is. So those arrows indicate actually this dynamics. So this is a standard interpretation, and this is the particle interpretation. Now what you can do, you can plot after many iterations, you can do computer simulation and plot the flow as a function of density. What is the flow? Flow is just a number of particles crossing the boundary between neighbors on average per unit step. So that's the flow. How many of them flow through the lattice? So the flow here, as you can see, is negative because they move to the left, and my positive direction is to the right. And you can see what's happening here. There are actually 2 transitions. One happens here. Here the derivative doesn't exist, and here the derivative doesn't exist. So we have something like rule 184, except that we have 2 transition points. And actually the flow can be expressed in terms of block probability. So that's I will not go into details. Now, what this rule does after many iterations, it does something similar like rule 184, namely it eliminates some blocks. So here I listed which blocks are present after many iterations and which are not. And depending whether a row is less than 2/3, because this point here actually is 2/3 and this is 3/4. So depending where you are in this with the row, you will eliminate different blocks. And I will not go into details of this. But you can exploit it in the same way as we did for 184-232 solution. And let's see how much time I have, not much. So let me just quickly jump to the second rule, which I will need. So here is another rule which we designed to actually play the role of rule 232. And it is not really difficult to design such a rule. It just needs to grow certain blocks in the absence of other blocks. So again, skipping details, I'll just show you what happens here, because that's maybe the most interesting part. So we iterate first of those rules up to this point, and we switch the rule here. And depending when we are with raw, we get the different outcome. So here, white is all zeros, gray is ones, and blue is twos. As you can see, for different raw values, we get either all zeros or all ones or all twos. So it performs density classification, but it solves some sort of a different problem, well, sort of a generalization of the problem known from binary rule. And here's a more formal statement of this, which tells you what it does. And this can be formally proven. So it's in one of my papers a couple of years ago, we proved this result. So that's how you can use transitions like that to construct solutions. And if you study other rules which are number conserving, you'll find all kinds of transitions, fascinating transitions, and sometimes there are more than two. Like here for three-state nearest neighbor, cellular automata. Those are examples of some transitions which I found. For example, this one has 3 transition points. This noise is a result that the simulations were done on a small lattice, relatively small finite lattice. So for a larger number of iterations, this will be a nice straight line. So that's how it, so of course, what I would like to say, and I hope that that's something you might find useful, is that you could use such transitions to design solutions to other problems more complicated than just a regular density classification problem. Now, for a larger number of neighborhoods and larger number of states, we can have even more complicated cascades of transitions. And if you look at my webpage, you'll find papers pointing to some more detailed reviews of such transitions. In addition to number conserving rules, there also exist rules conserving number of other blocks. So it's not, number conservation of ones is not the only option. For example, for rule 142, you have conservation of pairs 1, 0, and that's shown here. You have 2 consecutive iterations of rule 142, and I kind of link those blocks 1, 0 to indicate that they are indeed conserved. There are 3 here and 3 here and 3 here. So this could also be used for complexity engineering, and there is a lot of potential because, as I mentioned, you can get even more complicated transitions in the case of higher order invariants. But I would like to conclude this, so I will just take 2 more minutes with some remark about dimensionality. So what about 2 dimensions? Can we find such transitions, such second order phase transitions in 2 dimensions? Now, I do not know the answer. It's not so easy to find such transition among number conserving rules. It is possible for binary rules to enumerate and actually construct all number conserving rules, let's say for nearest neighbor, for von Neumann neighborhood, and even for Moore neighborhood. But those which I have studied do not exhibit phase transitions. And I suspect that they might not exist, but that's something I'm not sure. It clearly requires more research. But let me show you something else which is possible with all of this. So since apparently, at least for small neighborhoods, it's not possible to have transitions in deterministic rules, as we already heard before, one natural generalization would be to consider probabilistic rules. And one can indeed try to construct solution, one can kind of force the rule, two-dimensional rule, to exhibit transition by adding a little bit of noise. Here's how. So we start with rule 184 and 232 sort of lifted to 2 dimensions. So basically F184 and F232 are rules 184 and 232 in the horizontal direction only. Okay, so it's effectively 1-dimensional rule. And of course, this pair will not solve this classification problem in 2 dimensions for obvious reasons, and I'm sure that you could figure out why after thinking for a few seconds about it. So one thing you can do is to inject some noise, and here's how you can do it. For rule 184, you can do something which I call random lane switching. So this one here, if it has 0 above, will jump there with probability 0.5 and stay there with probability 0.5. Well, that's for rule 184. So what you then do, you apply rule 184, and then you do this. Okay, so the effect of this is that you will have some sort of a probabilistic group. And for rule 232, what is needed is something a bit different. If you have 3 zeros, then 1 and 1 below, 1 will jump there up with probability 0.5. And if you have 3 ones and 0 above, this one will jump up. Okay, and then again, you combine rule 232 with this. And if you do that, if you repeat, this randomization of rule 184 is denoted here by fx. So if you repeat this t times, where t is relatively large, and then t times randomized 232, it actually solves density classification problem. and the efficiency is as good as you're willing to wait. If you're willing to wait a long time, it will be very good. For example, for lattice 50 by 50, if you wait 500, if t is 500 steps, you will succeed every single time, and you will have to do a lot of experiments to fail. It almost always succeeds. It's nearly 100%. So I will conclude with showing you how this works. So here I have a configuration in 2 dimensions where I have slightly large number of blues than blacks. So blues are 1s and blacks are 0s. And I will let it run. And so first we have rule 184 randomized 184. So it's a lane changing 184. As you can see, I started with configuration which is kind of hard for classification because all the ones were grouped together and all zeros together. What this rule does, it diffuses, it kind of spreads all of them. So it actually mixes them up. And if you wait long enough, it will achieve similar effect as rule 184, but in all rows. And then you switch to randomized rule 232, and this will happen in a second or right now. And what it does, it actually washes out the remaining island of zeros. And again, if you wait long enough, because this is a random process, so there is no way to tell beforehand how long, then it does the trick, so it produces a final state with all ones. So that's how you could solve this classification problem in binary case using sort of two randomized rules. Okay, so I guess that's all I wanted to say. I think I'm almost on time, so thank you very much.
Great, thank you for that talk. Hello, I'm Jon Woodard again, and CEO of Wolfram Blockchain Labs. I'd like to introduce William Sanders, Director of Research at IOTA Foundation. Thank you for joining us, William. I'm really excited to hear your talk.
There. Now I'm unmuted. Thank you for the invitation. It's a great honor to be here, and I've been really enjoy listening to all these fascinating talks, and I'm excited to give my talk as well. I'm here to talk about binary voting protocols and distributed ledger technologies. And I think to begin my talk, I'm sort of going to explain sort of my perspective on distributed ledger technologies from my organization. So the IOTA protocol is a DAG-based DLT, which is a little bit different than a lot of blockchains. So first, while we don't have blocks, what we do is we have each transaction reference to other transactions, and then the object that they form, we call it the tangle. Okay. So now I often like to point out that blockchains are DAGs. No, blockchains are actually trees, and so are just special case. And so viewing things from a DAG-based perspective recovers the usual blockchain perspective, but I think it often brings out some essential qualities and some essential questions, and sort of changes this perspective a little bit. All right, so in a DAG, and it's true with blockchains, each reference is basically an assertion that the previous history is correct, okay, or the combined history of all the transactions in its past is correct, okay. So what this means then is that the transactions which are deep in some sense are confirmed. So in here, these lighter transactions which are which are new and don't have any references, and so no one's confirming that they are correct. where these ones down here are deep in the tangle, and thus are confirmed somehow. Now, so this is kind of a very loose, this is sort of a loose definition, because of course you need to find this in a rigorous way that's Byzantine resistant. But this is sort of just the general philosophy of all DLTs. So the important thing the important question is really always where to attach new transactions. Now, this question is a little bit more, put under the rug in blockchains, because you really only have your choices are limited, because you always want to just attach at the newest, the longest chain typically. But here, you have lots of different places to connect to. And when conflicts are added into the tangle forks, and then that makes the decisions more complicated. But still, the essence is the same. That when you're deciding where to attach new transactions, you are basically trying to assert which history is correct. So what's interesting, though, about this perspective is that overall, like a DLT itself, just through the gossip protocol, is a type of cellular automata where where the instead of a binary value that's being constantly updated, you have a tag that's being constantly updated. And the changes that you make are always connected to a certain history, right? Now, this is, I think, interesting perspective. If I gave a second talk, I would talk more about that and how that informs some of our design principles. But I'm going to talk a little bit more about something else. I'm going to talk more about where we decide to attach new transactions, right? So basically, if you want to attach to a transaction, you're basically accepting it, and then in turn you're accepting its past cone. So the contrapositive of that is that if you reject a particular transaction, you're rejecting the future cone of that transaction. And so basically, this comes down to deciding where to attach is coming down to deciding which transactions to accept and reject. So this is, my picture is a little out of order with my text, but so this is an example here of the past cone of this. If we have this transaction here, we look at everything it references, and it fits in this little cone drawn by these two yellow lines. All right, so if you reference this transaction, if you accept it, you accept everything behind it. And if you reject this transaction, then you would have to reject everything that includes it, which is its future code. Okay, so there's some connections here between the cellular automata that's considered in physics, and with cones, basically the something analogous to a light cone on the cone of things that you've seen, and then the cone of things that you affect, right? And looking at how the perceptions of these cones interact, helps determine your DLT, or the behavior of your DLT. And using sort of a variant of causal invariance, the DLT should always be able to rectify all of these past and future cones, regardless of what order that they were seen in. But anyways, as I said, this is sort of I'm getting off into a different direction, but I want to focus on this question. Then, this question here of which transactions to accept and which ones to reject is inherently a binary question, right? And this binary question basically forms the basis of any DLT. Now, this is a little bit maybe harder to see in traditional blockchains and such, and it's a little bit more clear maybe in just how we implemented consensus into the IOTA protocol. But the perspective is still there. All right, so what is a binary voting protocol? So a binary voting protocol is just a protocol that nodes use to come to consensus on a binary value. Okay, so it begins with each node having an initial Boolean value. Then there are a series of rounds in which nodes exchange information, update their opinions, and then the binary voting protocol terminates in a final Boolean value. And these Boolean values we'll just call an opinion, because that's basically, what we're talking about is accept or reject, where accept is 1 or true and reject is 0 and or false. So binary voting protocols has kind of been mentioned in previous talks, but these binary voting protocols are basically a type of cellular automata, where you have each opinion configuration, and then a round changes that opinion configuration to a new opinion configuration. And so the protocol, which determines exactly how you exchange the information, with whom you exchange the information, and how you actually change your opinion, dictates, dictates a transition rule in a cellular automata. Okay, so there are, I think, 2 main classifications of binary voting protocols, which I want to talk about today. I'll sort of discuss sort of the strengths, sort of the strengths of the one and the sort of weaknesses of the other. The first is deterministic, okay? And so deterministic binary voting protocols are where the transition rule is always the same. And so you always have a fixed transition rule. And so an example is majority dynamics, where the opinion of the neighbors. You're deterministic because you do the same thing every time. Another example, I think, falls under classical consensus algorithms, where classical consensus algorithms, you decide your decision on a bit, and then you gossip on your neighbors, and then based on their opinions, you change it in a predictable way and such. And so, in this way, I think classical consensus falls under the deterministic heading. Now, probabilistic binary voting protocols include things, I think, like Nakamoto consensus that have a strong randomness in it. Now, another example is if you have a cellular automata that has some sort of temperature, right? Like if you have majority dynamics that where is sometimes, instead of adopting majority opinion of your neighbors, you go with the minority. And this fits in with things like the Ising model and such. It is used in thermodynamics, and Stephen talked about this bit in the first talk. And then something which I'm going to be talking about later is probabilistic voting with random thresholds. Okay, and I'll explain exactly what I mean by that. So these are the classifications of binary voting protocols, but what do we need them to do? Why you can't just take any binary voting protocol and just stick it into any DLT and have it work. It needs to have certain properties. So the foremost is you have to have termination agreement. The protocol has to terminate with all nodes having the same opinion, and these requirements, termination agreement, are closely related. You can take any sort of protocol, and you can just say, you can take any protocol and binary voting protocol, and you can just stop it arbitrarily after a certain number of rounds, and then if you don't have then you'll have termination. But if you do that, you might not have agreement. In the same way, what you can do is you can say, well, the protocol won't terminate until you have agreement, and then you'll never have an agreement failure, but you'll always have a termination. You might have a termination failure. So these are sort of, two sides of sort of the same coin. The next is integrity, which is a requirement that if you have an initial supermajority of nodes thinking something, that supermajority should be respected. So this means, another way of saying this is that if all the nodes see a transaction that should obviously be rejected, then the protocol needs to reject that, right? So the nodes can come on to consensus to reject. This is important so that this is an important property to keep protocol secure from certain types of double spend attacks and such. And also it keeps the protocol from being non-trivial. If you just had the protocol say always default to reject or always default to true, then those are trivially satisfied termination agreement. But do not respect this this integrity criterion. And so the last criterion, which is really important, is Byzantine resistance, that these things, that integrity and termination agreement must hold during any sort of attack, or at least an attack with a a sufficiently weak adversary. All right, so the enemy of these agreements, particularly the enemy of the termination agreement failures, is metastability. Okay, so a metastable state is a state that metastable states are stable but not uniform, right? It's they're positions where people are, where all the nodes, the nodes don't agree, but there's some sort of cycle that forms in the opinions, and that they never converge. So and so these are the root cause of termination agreement failures. If your binary voting protocol falls into a metastable state, then this criterion will fail. Now attackers can try now a goal of a certain style attacks, of course, is to try to maintain metastable states. And so now what's interesting is that what's somewhat surprising is that determinism reduces Byzantine resistance by making it easier for an attacker to try to maintain a metastable state. This is this is outlined very precisely in work by my colleague Sergei Popov and Sebastian Mueller in a recent work, which I will reference in my at the end of the talk. Now, so kind of to give an idea of why we have this is kind of this example with a teeter-totter, right? So suppose that this is a binary voting protocol, right? And if the teeter-totter swings one way, then that means accept. If it swings the other way, it means reject. And the blocks here represent the number of nodes that have opinions, right? So these ones are voting for accept, and these ones are voting for reject. And then depending on which one has more weight, the teeter-totter will tip into that direction. Now, if I was to be a little bit more, if I was better at drawing, I would actually draw this more as a bottle, right? That's half full fluid. And then with a bottle that, because as the teeter-totter tips, the nodes will always go from one end will start to travel from one end to the other. Okay. So how can an attacker, so in this system, right, if it's very deterministic, what will happen is the teeter-totter will begin to tip. And notice that these blocks are fairly close in size, but regardless, a very deterministic system, this will begin to tip the one direction. Okay, and so, well, what would an attacker do then? Well, what the attacker would do is they would put their weight on the losing side. And when they do that, the teeter-totter begins to tip back, in which case they move their weight to the other side. And then they go back and forth, and they can maintain a metastable state. Okay. So this is sort of the problem here that we need to avoid. And if you have a probabilistic binary voting protocol, you actually are able to foil the attacker by making it so that they don't know where to put their weight. And so let me sort of give an example of how a situation this works. So the IOTA protocol uses fast probabilistic consensus as a binary voting protocol. Okay, so let me just go through this protocol, and in our setup, we're just assuming that the network has a random number generator, which introduces probability, the non-determinism into the system. And we also assume that we have some sort of Sybil protection system on the nodes, so that the attacker does not have an arbitrary amount of voting power. Okay, and whatever Sybil protection system you use is sort of this protocol here is agnostic to that. The general IOTA protocol takes care of that. All right, so what happens in fast probabilistic consensus is that all the nodes begin with initial opinion. And then there are a series of rounds, and in each round, the following happens. First, each node queries randomly selected nodes, other nodes which are randomly selected, and it asks what their opinion is. Then what the node does is it computes the average opinion A of those nodes which it queried. Okay. Now what happens is the round ends when a random number is released. And from that random number, we compute a random threshold in this interval, where this interval is set by this parameter beta. So this interval here is contained in unit interval, and so t is is a random number within this threshold. In this interval centered around 1/2. And so with this random threshold, we then decide what to do with our opinion. We set the opinion to be true if the threshold, if A, or the average opinion, is greater than this random threshold. If it's lower than the random threshold, if it's lower than the random threshold, then we set it to false. So we repeat this until the opinion is unchanged for some number of rounds. And then after some number of rounds for a fixed parameter R, then the protocol concludes that it's not going to be changing its opinion, and then adopts that as its final opinion. All right, so in this protocol here, here are the main attacker strategies. So the goal of an attacker, at least to maintain a metastable state, would be to maintain an average opinion of 1/2, right? They want to keep things in the center. So so there's two approaches that the attacker can do. They can be cautious, and what they could do is they query some nodes and they try to determine what the majority of opinion is. And the attacker can discover people's opinion by simply just asking them, right? So it's not unreasonable for them to be able to accurately determine what is the majority opinion. So we may as well assume in our attacker model that the attacker just knows the opinion of every node in the network. This might be a little bit strong, but it's not unreasonably strong. And then what the cautious attacker does is it simply responds with the opposite opinion. So if most of the opinion network is tending towards 0 or reject, then what they do is they start saying accept, and then trying to convince everybody else that it bring the average back up to 1/2. All right. Now, if they're being a little less cautious, they can be a little bit more adventurous, and what they can do is they can try to determine the opinion of every single individual node. And then when they're queried by that node, what they do is they respond with the opposite opinion. Okay. And so so when they respond with the opposite opinion, then what they're doing is they're trying to just confuse each node and trying to make it so that each node continuously tries to change their opinion. Now, this is a little bit more brazen of an attack because this behavior is detectable. Because if the honest nodes are communicating with each other, if they are comparing notes, then they can realize that, oh, this node said 1 to you, and it said 0 to me. Therefore, it must be attacking the protocol. So, depending on if you want to implement Berserker protection, you can decide between one of these two scenarios that you're in. All right. So what happens with the Byzantine resistance of the FPC with regards to this random threshold? Well, suppose an attacker is trying to maintain a split and is trying to keep the average opinion of every node to be 1/2. Okay, or the average opinion of the network to be approximately 1/2. Well, then what happens is that eventually, just randomly, the threshold is either going to be at some point it's going to be close to either beta or 1 minus beta, right? And depending on where A actually is, it will definitely be the average will either be definitely below A for all of the nodes or definitely above A for all of the nodes. All right. So basically, what this does is at these extremal events, it forces all the nodes to make the same decision. Okay. And so, yeah, so we have a theorem actually that Sergei Popov proved that FPC is Byzantine resistant for a large n, while only requiring a small number of queries. All right, and this actually, the second part is really important. The number of the number of queries that's required for the theorem. Right? I mean, you might be able to believe that this algorithm works, but you might need to query every node in the network. Or let me rephrase that. You might believe that the theorem is true if you query every node in the network, but that is not scalable, right? Because if you have large n, then, well, you can't just query everybody. So, all right, so I'm not going to go through the exact proof of this theorem, but I'm going to give you the basic idea because with the example of the teeter-totter. So basically what the teeter-totter does is it sets the balance that the teeter-totter are is basically the moving threshold, okay? And so what happens is if you have the attacker, wherever the attacker places their weight first, they give their responses. And then after the attacker responds, the random threshold is announced. And so regardless of where the attacker puts their weight, the random threshold can be placed in, might appear in a place that causes that doesn't cause the balancing done by the attacker to actually be true, right? If the threshold, in this case, if the threshold is very low, then everyone just goes to accept, or so yeah, so that's kind of the idea behind the theorem. And so all right, so what's important also to realize, though, is that if we have a fixed threshold t, the attacker actually can maintain a balance, right? Because the attacker can always, figure out what are the responses it needs to do to keep the system in balance, right? Because the attacker has control. All right. So in this example shows why having a probabilistic system is less resistant to Byzantine attacks rather than a deterministic binary voting protocol. Now, this is sort of maybe a general comment about this trade-off. There are systems where you can have very deterministic elements that are still Byzantine resistant, right? Like, for example, because I sort of gave the example that before, that balancing this teeter-totter is actually sort of like trying to balance a bottle of water, which is actually sort of difficult to do depending on how skilled you are. So the attacker might not actually be, depending on the system, the attacker might not physically be able to have the capabilities to maintain this balance. But in systems like so an example might be Nakamoto consensus, where, well, of course, what your actions of choosing the largest chain is deterministic, or at least choosing, if there's a tie, you choose the first one you see. But the thing is that it's connected to a highly probabilistic process about who's going to determine the next block. Similarly, if you have, actually, maybe we just consider like a hash function, right? I mean, in some ways, if you want to use a system that's using majority dynamics, it's basically, in order to prove its security, you kind of have to compare it to something like have a hash function, right? Where you can't exactly prove a hash function is secure, right? And you don't, and the hash function is deterministic, right? But the computation of the hash function is so obfuscated that it becomes probabilistic. So you can, if in systems where you could try to make majority dynamics work without having explicit determinism, by having it behave in such a chaotic way that you don't know what the attacker cannot have enough information to be able to understand how to control it, just like how it doesn't know how to actually, control the chaos of a hash function. All right, so that's kind of that's kind of a along aside, but I also want to give some simulation results for FPC. So these simulations are for nodes with 1,000. A network with 1,000 nodes, and this is assuming the berserk attack strategy, the stronger attacker. And here, this heat map takes different values of the attacker down here, and also this beta value, which determines how far the radius of the interval centered at 1/2. So the maximum value of beta is 0.5, and the minimum value is 0. And if you have 0, then this is when you actually have no randomness, right? 0 down here is where the threshold, since you don't have a wide interval for the random threshold, the random threshold will always be 1/2, right? So this bottom row here is actually where you have no randomness, and where you have 0.5, this is where you have lots of randomness. And so what shows is that the simulations show is that somewhere around 0.3 you actually have the maximum Byzantine resistance. Now, and so one other comment that I have on this graph here is that the the white is 0.8 and the dark blue is 1, and this is measuring the and this simulation is measuring anytime there's any sort of agreement failure, right? So if you have a node with 1,000 networks and you just have 2 nodes that, or say one node somewhere that comes to the wrong decision of everyone else, well, that also gets counted in here. So I think this is actually pretty good, because minute agreement failures like that aren't even so much of a problem. It's when you have egregious agreement failures where half the significant portions of the network don't agree. Anyways, this is my talk. I think I was within time. So these are my references. This first paper, this last paper here by Popov and Mueller about voting-based probabilistic consensus and their applications in distributed ledger is actually a very good treatment of this topic, and I strongly suggest you read it if you're interested in this sort of thing. So thank you.
Thank you, William. If you paste a link to that talk or that paper you just referenced into our Zoom chat, we can make sure the audience gets that as well.
All right, I can do that.
Great. Well, several very interesting talks. I think what we're supposed to do now is to do some Q&A. I see we're unfortunately running a bit behind schedule here, but let's not due to William. But let's see. Do we have some questions? If there aren't other questions, I'm going to ask a couple of questions here. Let me just see. I think Vero had a question for William. Maybe she'd like to ask that.
Yes. So my question was about actually if choosing a certain node actually makes the network more resilient, then how do you choose the nodes? Because does this scale when you have many nodes, there will be a large waiting time to choose a node?
Yes. So this is a good question. So the fact that you're randomly choosing nodes is not the this is actually just to make the system more scalable. It's not actually not really a key component of the attack strategy or of the security of the network itself. Because the attacker, even if the attacker knows if the attacker knows whom you're querying, that doesn't really help the attacker, right? Now, of course, if you query every node of the network, that's the most secure. But just taking a sample size is what allows the system to be that's just what allows it to be scalable. So what's important for the security is actually the random threshold, because the random threshold is what makes it so the attacker does not know what it should respond, right? Because if it, because let's say that you have 9 neighbors, right? 1 attacking neighbor and 8 honest neighbors, and they 4 say 0 and 4 say 1. Well, then the attacker doesn't know if it should be trying to say 1 or 0 right there, right? Because it doesn't know what the threshold is going to be exactly. So, and if the attacker does try to maintain a threshold of say 1/2 and try to always change your opinion so that your opinion is split, then eventually what will happen is, outside of the attacker's control, is the random threshold will be extreme at one point, and all the attacker's work of keeping everybody's opinion sort of close to 1/2 will be screwed up. So it's actually the basis of security is the random threshold.
Yeah, thank you.
Okay, let's see. I had a question for Henryk, actually. It was a very simple question, which was, you talked about how you could get you could get these discontinuous results for densities of pairs of blocks. Are there rules where you can actually get discontinuities and derivatives for individual block values or not?
So it depends whether you want rigorous answer or just numerical results. So there are other rules for which numerical results show that there is discontinuity in block probabilities as a function of density. Yes, so I have many examples like this. But if you want rules for which the formula exists and can be proven formally, I think it's only the one I only have is for rule 142, where something similar happens, except that in rule 142, the control parameter is not the density of ones, but density of blocks 1, 0. But then other blocks as a function of density of 1, 0 exhibit that kind of second order place transition. So for that, I have some formal results. But for other rules, no, only numerical results.
I think it's one of these things where I'm sure it's out there, but proving it may be quite difficult.
Yes, that's what it is. Yeah.
Yeah, interesting. So I'm also just curious about another thing, which is when you look at these limits, one limit is the number of time steps. The other limit is the size of the system. And in traditional statistical mechanics results, one of the things that was very confusing to people, finally resolved by Li and Yang in the 1950s, was how you got a discontinuous result as a function of a control parameter in any of these systems. And what they eventually realized is that there are these poles in the partition function in the complex plane, which as you increase the volume to infinity, gradually squeeze in on the real axis. And I'm curious whether there's a similar, any kind of similar thing that you can see here as you take the limit of infinite size versus finite size version of these systems. You would expect that the discontinuity would disappear when you make a finite size system. I'm just curious whether there's mathematics of that.
Yes. So indeed, I haven't really looked on that from such a formal point of view using, the same ideas as statistical physicists did. But indeed, if you have a finite system, then this transition becomes somewhat rounded, so it's not sharp, and you can. You see, I did for some other rules. I used my method for finding those density polynomials for finite system with periodic boundary conditions. But for cellular automata rule 184, I couldn't do this. it seems like it's a little bit too hard, like for rule 172, in which there is no transition, you can really get all those nice polynomials for arbitrary size of the system. But here you can only have, again, mostly numerical simulation. So what we did many years ago, we tried to study, behavior of such rules like 184 as a function of system size for finite ones. And we found some scaling relations similar to what you see in statistical physics. But one thing I should say here is that this transition which happens in rule 184 is rather simple. It's what we call a mean field transition. So for example, its critical exponent beta is not fractional, it's integer, it's 1. So it's rather simple transition. And all other critical exponents are also simple.
I'm just curious, in like the GKL rule, is there a, do you know what the critical exponent is there?
No, unfortunately, I don't know. I haven't really looked at that rule that much, but in that rule, you don't have sharp transitions, I suppose, right? Because you have sometimes you have configurations which do not converge to all zeros or ones.
Actually, can I make a remark on the GKR rule?
Yeah.
Because we had a paper a while ago with a student, quite a while ago, analyzing the ergodicity of the first GKR rule. And what we found is that depending on the error probability epsilon, there is a certain relaxation time, right? The time by which kind of the system loses its initial information. And what is interesting, right, that this, with ordinary, let us say, majority voting, this relaxation time, it would be just like proportional to, would be something like 1 over epsilon square or 1 over epsilon cube, right? You can write it like 2 to the log 1 over epsilon. But interestingly, for the GKR rule, it is better. It is not 2 to the log 1 over epsilon, but it will be like 2 to the log square 1 over epsilon. Well, it does relax, but there is a quantitative sense in which it relaxes slower.
Mm-hmm. Interesting. So if I could add here just one more sentence, that for rule 184, there is also, if you are exactly at density 0.5, then the relaxation to the finite state is like 1 over square root of time. And it's only at the critical point. So there is a critical slowing down. If you're away from the critical point, the relaxation is exponential, but at the critical point is like 1 over square root of t.
Okay, there's several different comments here and several different interesting things. So let's change topics a little bit. I think Aaron had a question for William. Do you want to discuss that?
So Aaron's question is, how is the randomness in the threshold generated? So, well, this is really outside the fast probabilistic consensus protocol's parameters. So you have, I guess, basically 2 options. You can try to take a centralized random number generator, like it's not like what NIST has or something like that, but then your protocol is dependent on something like this. What the decision that IOTA Foundation used was to have a decentralized random number generator created by certain nodes in the network who have a lot of mana or our version of stake. And they just employ a standard DRNG algorithm called DRAND, which just uses a BLS signature style random number generator, using elliptic curve pairing and such. So that's kind of more of a cryptographic. Yeah. So it's kind of a separate question. It's kind of doesn't really matter for the cellular automata part.
I'm surprised that you can't use something more like Rule 30 randomness. In other words, I'm surprised you can't have the actual distributed system make its own randomness for your purposes. In other words, it doesn't, I mean, you're going to a lot of trouble to have particular nodes have very high quality randomness, but I bet for your protocol, it actually doesn't matter much. You can have, Rule 30 becomes unpredictable very quickly if a single, node is changed, if a single value is changed. So I suspect you can just generate the randomness you need just by virtue of the dynamics of the system without having to sort of inject randomness with great effort from the outside, would be my guess, at least.
That sounds reasonable. I think we were just more approaching the point from, we were just trying to take the most simple perspective from the engineering point of view. The one issue, practically speaking, is that if you do something like, say, I don't know, take the hash of some transaction or something like that, is that then the people can try to mine their hash to be, some sort of value or something like that, right? Like if you took use the randomness in a blockchain, someone can try to control that, and we didn't want that to happen. So you probably could, you could probably devise a way of doing that.
Let's see, I think there were some other questions here from the live stream. Jojo is asking, to you, William, isn't obtaining obfuscation from a completely deterministic hash algorithm just an assumption? Not sure I fully understand that question. Do you understand what's being asked there?
Well, so you're commenting on sort of my comments of if you have a probabilistic voting, if you have a so if you have binary voting protocol that is deterministic, if its mechanisms are obfuscated in a certain way, then it becomes essentially probabilistic. And so, that is basically an assumption, but it's a property that you would have to be able to measure and show. And you have to then make sure that the system that is really obfuscated enough that an attacker can't get a hold of it, right? Can't figure it out. And that, proving something that is that obfuscated is difficult. It's not easy.
Fair enough. So let's see, there's a question from you, also for William. What do you think about pay-to-win type attacks on Byzantine fault-tolerant systems?
Well, I think that just falls under the general your assumptions about the attacker strength when you're creating when you're creating your Sybil protection mechanism, right? I mean, like if you have, this is something that all DLTs have to contend with, and it's, at least for the purposes of Cellular Automata, it's kind of sort of tangential, a sort of tangential question.
Fair enough. So I have a question for Vero, actually. You've heard all of these things about majority cellular automata and all these kinds of things. What can we learn from error correcting codes, things like Reed-Solomon codes and so on, about the design of a cellular automaton function that can sort of correct errors? What is the relationship between kind of the notion of error correcting codes and sort of the transition rules for a cellular automaton? I'm just curious whether that's something that you might have thought about.
Yeah, this is also related to something that you mentioned before, like the self-maintenance properties of the system. So one of the things I'm thinking is that because now I have just a model to understand how behaves the system, to decide what are actually the better settings, the better redundancy ratio, and that with the cellular automata, I'm using I can play with, different ratios of repairs, speed of repair, or different things. But if we can know, and also one of the properties that entanglement codes have is that we can do the repairs in a distributed way. With our new work that I couldn't reveal much because actually it's under review. Well, we have the deadline this Sunday. We are doing repairs without any metadata, but we are not doing yet completely distributed repairs. So is the downloader who can do the repair of any file that doesn't own. because of the metadata that is embedded in the Merkle data structure. But if we can also learn how to do these distributed repairs and understand the state of the system, like learn the locality of the nodes and how much redundancy there is about a certain chunk, then we can actually kind of like trigger repairs depending on on the state of the cells. Yeah.
Okay, let's see.
I also wanted to answer on this Reed-Solomon code thing, because at least in this complex one-dimensional cellular automaton from 2001, Reed-Solomon codes were used in order to achieve just a constant factor of redundancy. So it really, the system forever remembers like a constant number of bits per cell.
Interesting. Okay, so that's part of your very complicated rule structure is the Reed-Solomon codes. Very interesting. So let's see, just a couple of quick things here, and then maybe we take a break for a few minutes, and then Peter Gacs is going to speak. Pedro was asking here of Henryk, what happened to your attempt to solve binary density classification using 3-color cellular automata? Is there a quick answer to that question? Did it work or did it not work?
So no, I don't think it exists. Okay, at least not not for small neighborhood size which I tried. So.
Fair enough. So Goktug is commenting on Rule 184 with reverse cellular automaton update, got an Ising model as a result. I don't quite understand that. Maybe you could say, I think maybe you could say what you mean by a reverse cellular automaton update.
Hi, Stefan, can you hear me?
Yes.
All right, so what reverse update is, as a conventional cellular automaton, you have the neighborhood dictating the updated state of the cell, right? So what I did was I had the cell dictate the states of its neighbors instead. So this, when applied to a rule like 184, is giving this result. It's instead of like conventional rule 184 models like the Nagel-Streckenberg model where you're looking at the traffic from above. Now you're thinking of a cell as a driver, and now you're in the driver's seat. And when this is expanded uniaxially, this causes a strain. And from this, I could understand why Ising model was going under spontaneous magnetization under certain circumstances. And this was because the density of the neighborhood. When I increased the number of cells to state 1 from 5 to 6, the system immediately magnetizes into ferromagnetism. So this was a very surprising result, and I then expanded it and got additional interesting properties. Like, for example, the code I have, which is available at the link I shared, includes no trigonometric functions as its input, but when applied under certain transformations, it is outputting a cotangent diagram. And this, I tried looking over a lot of the law of literature review, and I couldn't find a cellular automaton that actually very accurately outputs a trigonometric diagram. And this has led me into a lot of research, which I shared on the link. But I'm curious about what would you think of possible applications or implications of such a different approach to cellular automaton model?
I don't know. For me, the traditional Ising model tends to be studied in equilibrium statistical mechanics, where you're just giving a certain weighting to different configurations. The question of what one might call the microcanonical Ising model, where you're actually looking at the evolution of the system, that's something I looked at one point and found cellular automaton rules that are microcanonical evolution, explicit time evolution rules for the Ising model, which reproduce on average the standard equilibrium results. But I'm not sure how that relates to to what you're talking about here, which I think we need to understand a little bit better. If anybody else has a quick comment, we could have it. Otherwise, I think we should go offline for a few minutes and take a short break. Maybe, okay, I think it's time. We're going to go offline for a few minutes here, and we will be back at the top of the hour in about 10 minutes. And Peter Gacs will be kicking off the next part of our conference. So to people on the live stream, thanks for joining us so far, and we'll see you again in about 10 minutes.
All right. Welcome back, everyone. I'm Christian Pasquel, Director of Connectivity at Wolfram Blockchain Labs. I want now to introduce our next speaker, Peter Gacs from Boston University. Thank you, Peter, for joining us.
Okay. So this will be, I tried to collect some topics that I studied that seem to relate to the topic of this conference. We'll have to see how it goes. Probably, actually, a number of those were already mentioned in Stevens' introduction and some other people. So anyway, maybe I should go to the presentation view again. So yeah, this will be about cellular automata, and always, essentially always subject to noise, not almost always. And only considering the simplest kind of noise model. So, which means that the noise is transient and random. So random means really the main thing it is not adversarial. Right? So it is can change whatever a cell is doing at a given time, but the probability of this happening is, and so this random event is independent of everything else that happened earlier or happening at the same time. And also the effect is transient. So what this means is that, okay, the cell may change its state to some undesirable one at a given time, but still its rule of behavior is not changed in the future, right? So damage is not permanent to the nature of any of these elements. So so of course the other kinds of noise are quite important. It's just that this simplest one leads already to interesting mathematical models that also have some physical connections. So it's worth studying these in detail. So I don't want to, of course, now cellular automata were mentioned several times. So to this audience, there is no need to go into the definitions in detail, but just in general, then the global state I may denote by the number, by the function xi, and in the whole history, space-time history of cellular automaton, I would denote by eta of x and t, where x is the position and t is the time. And the cellular automaton may, the transition of a cell at any given time may depend on some neighborhood, right? This neighborhood may vary, right? We know just, I give here just two examples. One is the von Neumann neighborhood in two dimensions, where you take just the 5 nearest neighbors, and or the Thom neighborhood, which was already mentioned, which is the center, the north, and the east neighbor, right? And then in deterministic cellular automaton would just change each cell would change its state as a function of the states in the neighborhood. The formulas are not that important now, of course. It's just the formula description. You have seen this in pictures many times. So we will consider infinite and finite versions, and if in the finite version, I always just consider periodic boundary conditions. So here is an example of a one-dimensional cellular automaton of length 17. So the right edge here is really connected to the left edge. So this is actually a ring of cells. So an example of a cellular automaton rule is the Thom rule, right, which is just the majority of north and eastern and central neighbors. But it's important to say that this simple rule, the Thom rule, you can extend it to also larger alphabets. So we can say that the majority, because we will use this, the majority, if there is a no majority, it really doesn't matter what to do. But let us say then you don't change the state. But if there is, if the northern and eastern neighbors are different from you and equal to each other, you have to change them. So one of the basic questions that was already considered here earlier is how to suppress a finite minority, right, in an infinite system. So clearly, our automaton will need to take advantage somehow of redundancy. So we want we would like, if configuration is almost constant, to be restored to constant. And it's interesting to note that that the symmetric majority rule, for example, in 2 dimensions, is not self-restoring. It doesn't even erase a 2 by 2 square. And but even though even though random errors I will introduce only later, I wanted to illustrate you the difference between the effect of Thom rule and the symmetric majority rule on a little simulation. Sorry, I want to share a different picture, a different screen, yes. So here is so actually I will be running here a cellular automaton, which is actually voting on even symmetric voting on even more neighbors than the von Neumann neighbors, voting over all 9 neighbors. But I give but noise is introduced here. The noise of turning into 0, or the probability of turning into 0 independent of this majority will be 2%, and the probability for turning into 1 is also 2%. And now if I run this rule, then what you will see is that, of course, I introduced artificially here a big island of 1s into a sea of 0s. And what you see is that, well, if you are patient enough, this island will shrink away. But actually, this is still an interesting and challenging open mathematical problem to prove that this rule with the symmetric noise does preserve majority. So if you start with from all 0s, then the probability of 0s everywhere will always be bigger than the probability, significantly bigger than the probability of 1. So this is not proven. But you see that the island is slowly shrinking. Now, but let us be a little nastier, and let us increase the probability of 1s to 3, while the probability of 0s is still only, the random ones is going to be 3%, while the probability of random 0s is still only 2%. And so as you can expect, this time the symmetric voting rule is not just helpless in shrinking the island, but actually is defeated. The island is growing. So symmetric voting is not good for any biased errors. For unbiased errors, it's still an open question. Now, okay, so let's, on the other hand, let's switch to the tone rule. Still, again, in the same noise. You see, no problem. Okay, so this was my little kind of simulation. And so let me go to a new share, back to my original share. Okay, so again, as we know, the Stone rule is eliminating all finite islands, the symmetric majority doesn't. But what is much more important that the Stone rule will do this even in noise, of course in small noise, but not too small. And Tom proved this, and the proof is highly non-trivial. Now, let me now, something that wasn't mentioned here is that in a work with John Wright, we showed how to use this behavior of Tom's rule to construct a model of reliable computation in cellular automata. This is so this is going to be a three-dimensional cellular automaton that is simulating an arbitrary one-dimensional cellular automaton reliably. So this is how it works. So take an arbitrary one-dimensional cellular automaton U, and we will create a three-dimensional cellular automaton by turning each cell of this one-dimensional cellular automaton into a whole plane in a three-dimensional cellular automaton. And
your current screen is black.
Oh, wait. How about now?
All better, perfect.
Oh, looks like when I went into presentation mode, that wasn't shared anymore. So anyway, now you see it. It's fine. So I can also make it a little bigger. Yeah. So okay. So here is a picture that is much better than this description in words. So I take the one-dimensional cellular automaton and blow up each cell of it into a whole plane and just repeat its symbol over the whole plane. And now what if this original automaton was U, then I created this new cellular automaton U prime, but I didn't say yet what the transition rule of U prime is. And it will be a combination of two rules. You can say that it's they are executed consecutively, but you can simply say that there is one rule, which is the execution or consecutive execution of two rules. One of them is apply Tom's rule within each plane, and the other one is apply the rule of the one-dimensional cellular automaton which we are simulating across the planes. Right. So this is the operation of Tom layering. Right. So it created an automaton U prime from U, and this is now we have a theorem, right, saying that that this cellular automaton is fault tolerant in just the most reasonable sense, right? So look at an arbitrary computation history of the original cellular automaton. Let's call it zeta, right? Zeta xt. And now, right now, look at the trajectory of this tomb layering, but not the original one, but an epsilon perturbation of it, which means that every cell at every time with probability epsilon can do something else. And now, right, so this, we call it eta x, y, z, t, right? The y, z are just additional coordinates for the same cell z, x of zeta, right? And now, so the question is then, so suppose that now we start this automaton from the initial, from the encoded initial configuration of zeta, right? Then we claim that at any point, at any time later, with probability essentially 1 minus epsilon, 1 minus order of epsilon, each cell of U prime will have exactly the state that zeta would have at x. Right? So in other words, the computation is of this arbitrary cellular automaton U, right? It could be a universal one, is reproduced everywhere. Okay, so this is the, and I claim that this is really by far the simplest model of reliable computation that is known. And now, okay, so let me, I will later comment on what on the finite version of this. But for the moment, let me just make a little mathematical digression. Ergodicity was mentioned already in Stephen Wolfram's talk, but so let me give the definition of ergodicity for cellular automata is important here. So if we take a probabilistic cellular automaton, then we say it's ergodic, essentially if it forgets everything about its initial configuration. And more precisely what this means is that there is some fixed measure nu such that on any finite set of cells, if you look at the probability of this finite set of cells being in a particular array of states, then this probability will converge to the corresponding new probability of this, independently of what the initial configuration was, right? So it really forgets everything about the initial configuration. So this is the property of ergodicity, and you know, it's easy to create. So we could, and okay, so I will. So there are. It's easy to construct ergodic and non-ergodic cellular automata, unless we require noise. So right, so for we will call a cellular automaton noisy if no transition, no local transition is forbidden. Every local transition probability is positive. And so on a finite space, noisy cellular automaton is always ergodic. Simply, you know, this is a classical result about finite Markov chains with positive transition probabilities. So, which already means that there is only a limit to which a finite cellular automaton can do anything reliably. Eventually, it will forget everything. But you know, there is easy to now. So let's look at infinite cellular automata. And there are some easy examples of ergodic cellular automata. Of course, just if every transition is independent of everything else, then of course this is ergodic. But also there is easy non-ergodic example. For example, any deterministic automaton the Thom rule was the first example of any noisy, non-ergodic, infinite cellular automaton. So it was non-trivial to find one, and Thom found one right around in 1974. We have seen this example. Now, for a long time, for quite a time, it was not known whether you can there is any one-dimensional non-ergodic noisy cellular automaton. Georgy Kurdyumov had an idea how to construct a hierarchical construction, then which eventually I carried out, and so that's the one-dimensional cellular automaton that was mentioned here. It's very complex, so I will not talk about that today. Also, when we talked with Kurdyumov about his proposed ideas, then we noticed that if we are not if we only interested in the deterministic deterministic property of erasing finite islands, then we can do something much simpler, and this is how the GKR rule was born. But later we have shown that this. Well, I want to mention here something anecdotic. So Georgy Kurdyumov wrote up this result, and he did some computer experiments, and they seem to indicate that no, this automaton also resists noise. But of course, it was very small scale. And then later in 1983, at the conference that Stephen already mentioned, Stephen Wolfram also brought in some Sun workstation that people could play on, and I did put in this cellular automaton rule with noise and observed its behavior. So it was, of course, I could already do it on a much larger scale than what Kurdyumov could do, and it took only a half minute or so, and I looked at the simulation to see that there is no that is not going to be non-ergodic. So you put in a large island, and essentially it is never going to go away when there is noise. So, but then later we proved that indeed this cellular automaton rule is ergodic, at least in strongly biased noise. We proved this with Ki-Hong Park. But the symmetric noise case is technically it's still open. So what are the consequences of these infinite results for finite cellular automaton? Well, as I mentioned, the finite cellular automaton is always ergodic. But what does this mean then? Well, we need to quantify then what it means for a process to be ergodic, right? We mentioned that the probabilities of certain finite segments are going to converge to some limit probability. So let's just introduce relaxation type of the simplest of these probabilities. Let us look at just the probability that cell 0 is equal to 0 and subtract it from the probability that when we start from the all 1 configuration, and let's subtract it from the probability that cell 0 is equal to 0 when we start from the all 0 configuration, right? You look at these two and look at how far do we have to go in time t so that these two probabilities will become less different than delta from each other, right? So how long, and we call this the relaxation time, right? For a given delta, right? So and we expect that, and now what is interesting, so we can view this as the time it takes for a position 0 to forget about the initial configuration, right? This is a quantification of how long it takes. And now here are two propositions. One is, first of all, it's easy to see, well, it's kind of that if the infinite system is ergodic, then how does this translate to the finite one? It translates by saying that it doesn't help to increase the size of the finite system. It will not really increase the relaxation time. So there is an upper bound on the relaxation time independent of the size of the system, right? So on the other hand, if the infinite system is non-ergodic, then there may be a chance that with increased size, the relaxation time will increase. And moreover, of course, it will never increase more than to exponential. Because in exponential time already there will be an event when simultaneously all the cells switch to some other state. So you cannot hope to have better than exponential relaxation time. But for example, for the tone rule and also all the other reliable automata that I constructed, it is true that this relaxation time is exponential. So for the perturbed tone rule, this was, I mean, in this version is proved by Berman and Simon. What we proved with John Wright was a little bit, slightly weaker than this. So, but you know, relaxation in time is exponential. But so how does this translate? It's interesting. How does this translate? What can we say? What we can say is the following. Then, suppose we want to perform some computation that takes space S and time t. Then, instead of constructing this infinite three-dimensional server automaton, we can construct a kind of sausage, a three-dimensional torus, you know, which has a length S, but diameter very small. Diameter will only be logarithmic and S times t, well, over delta. Okay, so this is then a reliable computer, right? It is, you know, on a finite size takes and really the redundancy is just logarithmic. More exactly, it's log square, right? Because L is just the diameter of the torus, but the area of the torus. But then you have to take the cross section for redundancy. There is no time delay, but as you see, the space redundancy is logarithmic. Now, here I should mention again something that was kind of missing from Stephen's introduction, that actually von Neumann's in 1953 did already more than just introduce this kind of voting gates. He actually proved a remarkable result, namely that given any Boolean circuit of size n, he constructed a Boolean circuit of size n log n that imitates the original circuit reliably. So how, in what sense do I claim that that our network is much simpler? Well, it has a little bit worse redundancy. It is log square instead of log. On the other hand, von Neumann's Boolean circuit relies on some expander-like constructions, and therefore, if you try to realize it in space, and it will have some long wires, and on these long wires, you still don't assume only a constant probability of failure. So that's a little bit physically less realistic. And anyway, so it has actually a quite complex structure, right? It has this expander-like little circuits. So cellular automaton is as simple as structure as you can imagine. Okay, so my last topic. Oh, let us see. Am I over time already? Because
nope, you still have a few minutes.
So my last topic, and kind of which leads to open problems currently, is asynchronous updating. Right, so I don't need the formal introduction. Looks like you know what it is, but imagine now that our updating times are by some kind of constant, like a Poisson process, and and we know that that both cellular automata are sensitive to update order, but actually it's important to know that that Thom's rule is not too sensitive. This particular Thom's rule, one can prove that also the asynchronous version will be noise tolerant. But it's also now but the bad news is that this Thom layering, on the other hand, this cellular automaton is by nature extremely synchronous. It really very much depends on simultaneous updating. Now, but so there is kind of an open question: are there any kind of continuous time reliable cellular automata? And the answer is yes, because in 2001, this long paper I constructed is also in continuous time. On the other hand, it's very complex. But is there something that is comparable in simplicity to this 3D model? And now we have a very strong candidate, which is based on this Thom layering, but adds a kind of universal, adds a way to imitate synchronous automaton by an asynchronous one. However, there are some mathematical challenges still open in order to prove that this rule actually is reliable. So there is a general, probably very well-known way to turn any synchronous cellular automaton, and actually much more general than cellular automaton, any kind of synchronous kind of parallel computer into an asynchronous one. We can call it modulo 3 trick. And the idea is that you introduce some additional variable to each cell that is like the time modulo 3. And also each cell will have to remember its previous state. And then it's easy to see that easy to see an update rule that will simulate the synchronous cellular automaton. Basically, you don't progress unless unless all your until any of your neighbors is still behind. And being behind time modulo T is enough to see whether somebody is ahead or behind. And then, okay, so this is I don't have time to go through the formalities, but it should be easy to see. But so the idea, so this is fine. The problem is, so we could add this complication to the Thom layering, but there is a basic, and actually this will introduce only a constant time slowdown. However, there are two important problems that arise. One of them, which seems easier but now is the harder, is that still there may be some very long chains of automata some neighbors waiting on each other, and if things are delayed too long, then because errors still happen, the area begins to rot, and the Thom rule doesn't do its work of correcting things. But there is a conjecture that these local stallings are exponentially rare. But there is an even more interesting problem, namely that faults can introduce kind of deadlocks, the circles of waiting in these modulo 3 clocks. And then, and in 2 dimensions, actually, they could introduce these circular weightings, and that become will be far from each other. And then, since everything around them seems normal, there doesn't seem to be a way to get rid of these. Interestingly, in 3 dimensions, the situation is better, and there is a clever and non-trivial rule introduced by Cook and Winfrey that eliminated all these clumps that were introduced by default. And so, but the problem still remains that even this works only as long as things don't stall too long. So the main question that still remains open is a completely probabilistic question, namely about these how frequently these long chains of waiting will appear. And this is a question for probabilists, and we'll still need to work on that, as well as some other issues. Now, I wanted to mention that here again, as if Stephen mentioned, said that actually there is no known rule that will bring a decision. Now, this is a completely different topic, just my last remark. Stephen mentioned that he thought there is no rule that brings a decision on a finite system that, for example, of course, preserves all zeros as zeros and all ones as ones. Well, it turns out there is such a system. Namely, you can do the following: take Thom's rule and combine it with an OR. So take 2 applications of Thom's rule and 1 application of OR. And this will be a cellular automaton that will always, on a torus, no matter how, on a torus will always turn every configuration into all zeros or all ones. And of course, it will not change the all ones or the all zeros. Okay, let me stop here. So I guess I am probably out of, yeah, I probably overrun in time already. So let me stop here.
Thank you.
Those aren't many. Go.
Gotcha. All right, let's continue then. Thank you, Peter, for sharing all that with us. So our next speaker is Eric Goles, Professor of Theoretical Computer Science at Adolfo Ibáñez University, Chile. Thank you for being here.
Okay, thank you very much to invite me here. I'm very proud to be here. So I will share my lecture. One moment, please. I will put the wall. Okay, so I will speak about minority networks. I was working in this kind of network in the last, 30 years, maybe. My talk will speak about majority network and some examples. The dynamic which is driven with the parallel or asynchronous or sequential, but is driven by the kind of, energy like the icing energy anyway, okay? After that, we will study a little about computational complexity of the prediction decision problem. The name is spread for prediction. The characterization for the first easy cases, in order you understand the idea, is in the freezing majority, which is equivalent to the bootstrap percolation model. After that, it's very important to take into account, in order to go to the complexity of the problem, to take into account the kind of strategy in tight cases. From that, one may prove it that in some cases spread is p-completeness, and a very simple graph in the planar graph. So of course, in non-planar graph it's trivial, but in planar graph it's more tricky. But for the majority network, we say prudent ties. We will see that this is the meaning of that. The synchronous over a 2-dimensional grid is easy. we may predict the state of the site quickly than the algorithm of the automata. Also, we will see the p-completeness of spread under two kinds of majority in the population. The name of the majorities depends on the type cases. Is the prudent one or the deviated one? And finally, we will say something about signal majority network. So when the edges of the network has plus or minus signs, okay? But the same majority operator. So, of course, during the day, several people speak about majority functions. So here for me is a graph, undirected graph. Say the number of sites is n or individuals. The number of, there are e as edges. The opinion, usually we work with 0 or 1 or -1 + 1, that is similar. We have the neighborhood. And an opinion configuration over the network is a vector, say, in the hypercube, in this case. For instance, here we have a graph, we have a configuration, and the neighborhood, and so on. So it's easy to understand. So now the majority is the usual one. The central guy in the network, in the graph, the new state will be the majority of the neighborhood. But in case of tie, there are three possibilities. The prudent behavior, say, in case of tie, the central guy remains in his opinion. In case of risky behavior, it changes to the opposite one. And the deviated behavior always take one opinion, say, for instance, 1. So we will study it. And the interesting thing is that the behavior is different from these three kind of tie cases. The kind of updated schemes, of course, we will update the network, the parallel iteration or the synchronous iteration. Also, the asynchronous ones, say, take one individual and change his opinion, and another, and so on. Or in a periodic way, sequentially, individuals are updated one by one in a given order, okay? Of course, we have cycles. F is the global function or application. We have cycles or fixed point of the iteration. We have always we will work with in the deterministic case. Here, for instance, for the parallel iteration, we have an initial configuration in the left, and the three cases. The first one is the prudent behavior. The second one is the update with the risky behavior, and the third one is update with the deviated behavior. You see that the new configuration in every case is different, okay? That's an example. Here we have an example, for instance, for the risk strategy. So risk is when the guy changes his opinion in the case of tie. For the sequential order, 1, 2, 3, 4, 5, 6, from the even in the clocks sense. So here we have some behavior like that. Finally, we arrive to the consensus. Everyone is in 1. It's a fixed point, a trivial one. And there we have several examples. For instance, here the neighborhood is an odd number of neighborhood. So there are no tie cases. It's only to prove that, for instance, in the first case, it's in parallel, everyone. The initial, the majority was red, and the final state was the consensus in red. In the middle, the majority is what happened for the parallel iteration is going in the other way. The fixed point initial, take the initial minority opinion here, okay? For this, it's a little different graph. And for the third case here with the 3, we have a 2 cycle. There are no consensus, it's a 2 cycle the world time. Here another example, which is in a 2-dimensional torus, a little one, is a deviated case, because in case of tie, he go to 1, this guy. So that's in parallel, you are going to the two cycle, sequentially. It depends what is your order. For instance, if the order is 1, 2, 3, 4, 5, 6, 7, 8, like that, you are going to a fixed point, which is a fourth individual origin opinion 1. In the other case, you are going also to a fixed point, but it's a consensus. So the behavior is very dependent on the kind of iteration that we take it. The majority operator, which is the first one, is a particular case of the threshold local rule, which is here, which is a kind of sign function, or here a sign function, 0 and 1. We take a linear argument for that. W is the weight matrix of the network. In our case, if it's the incidence matrix, is of course 0 or 1, okay? But maybe other values, negative or whatever you want. B is the threshold vector for each vertex. And it's trivial to prove that the majority networks are particular cases of threshold networks, okay? For instance, here, if I take the majority between these 5 guys here, is equivalent in this framework to this threshold local rule. That's very easy to understand. And there, long time ago, I proved with some colleagues in 2 or 3 papers that when W is symmetric in the 80s, then the parallel iteration admits only fixed point or 2 cycles. So the cycles are bounded, independent of n, the size of the network. And more or less, if W is not only symmetric, but the diagonal is non-negative, the asynchronous and sequential iteration admit only fixed point. 2 cycles disappear. But otherwise, if the diagonal is negative, you may construct non-polynomial cycles. So it's a very, very complicated behavior in this case. 3, the iteration for the good cases, so W symmetrics and diagonal non-negative, the convergence is related with the size quotes of the matrix of weights. In the case of the incidence matrix, in the size of the number of edges and sides of the network. So you are going very quickly to the attractor, okay? Of course, for the majority, it's the same case. We have the same behavior. Here, I give you one example with the, I take a ring of 6 sides, and with the sequential iteration from left to right. So for this iteration, we see that it's a kind of glider. This red one is going to the right, and since we have a ring, we will be in a cycle of lengths n, or n-1 or n, okay? From that, it's very easy to construct exponential or non-polynomial periodic behaviors, okay? And, okay, sorry. And in this case, we are taking into account the risky strategy. The risky strategy is equivalent to consider in the matrix W the negative diagonal. So it's not longer non-negative. So in this case, very big cycles appear, okay? And everything before is driven by a kind of Ising-like energy. For the parallel case is the first expression, which is a bilinear form taking into account 2 iterations, which is decreasing. If you don't have a fixed point or 2 cycles, you are going down on energy. And for the sequential iteration or the asynchronous iteration is exactly the usual Ising energy. With an external magnetic field, which is the VI XI there. For more information about two of these things, with a colleague, we published a book with neural automata networks in the 90s, where there are generalization and so on. Now I'm going to the majority network and computational complexity. Essentially, this work was done with my colleague Pedro Montalegre from the University of Ibáñez too. In this case, we consider a decision problem which the answer is yes or no, okay? From the computational theory of complexity, essentially we will work with the class of polynomial problems, P, and the class of the problem that you may solve in a parallel machine, say a PRAM, for instance, in polylogarithmic time by using polynomial number of processors. So these are the classes. What kind of decision problem we take? Okay, one moment. We say that the problem is P-complete in some way when any other problem in the class P can be reduced to it. Reduces it, say, efficiently in polynomial, not very hard to do that. The typical problem, which is P-complete, is evidently to compute a Boolean circuit, okay? Every algorithm, you may put it like a Boolean circuit anyway. So here, this is the one problem that we can modelize every other problem. Of course, the INC class, which is the parallel one, every parallel algorithm, you will put it in a sequential machine. So INC clearly is inside P, but the quality is a very, very hard open problem. So since it's very hard, that gives a sense of the complexity of the dynamic of an automata if you may reduce the dynamic to predict something in the class C very quickly than the algorithm of the automaton in a serial computer, or is a P-complete case. Our prediction problem roughly is this kind of thing. We consider two possibilities. Take the majority network over a graph and an initial condition, and you give, there are two possibilities. You ask for a specific site. You take one specific site and you ask if it initially is, say, at 0 opinion, is it this individual will change at some time in the future or before a step time t, okay? Could you answer that quickly, faster than the automata algorithm in the sequential machine? In fact, not only faster, but exponentially faster in polylogarithmic time from the size of the network, okay? That is our problem. And the first one, in order to show you the idea of the general cases that we will study, is the prediction for the bootstrap percolation or freezing majority. Here we have a graph. We consider the parallel dynamics, and in this case is the quotes prudent majority rule. In case of tie, the guys remains at the same state. And since it's a percolation problem or freezing, when a site or an individual is in opinion 1 or state 1, it remains forever. So the only possibility to change is to be in 0. So for instance, here we have an example. The red one is 1. So of course, in the diameter of the graphs, you are going to one side at each step. So it's a linear algorithm to go to an attractor. But here, for instance, in the last case, there are 3 guys here that never change opinion. They are protected. It's inside, it's a kind of, the name is an alliance, because inside the set, there are more edges than outside, okay? So more or the same number. So it doesn't change because it's the prudent type case. So that is a fixed point. but there are no consensus because there are alliances. So the alliances for the majority in the graph is a very important concept because it's the kind of wall to go that the ones, for instance, can't go to a consensus. Okay, anyway, it's important to consider. And the decision problem for us is the breadth problem. So given an initial condition and a specific node at value 0, opinion 0, does there exist a T positive such this node becomes 1? Okay, and our theorem, we prove it with Pedro Montalegre, is the following. If the maximum degree, if we take the class of graphs where the maximum degree is bigger than 5, the breadth problem is P complete. It's difficult. We can find a better algorithm. Of course, if P equal in C, it's okay, but we don't know that. And in the other cases, the maximum degree is less than 4, it's easy. Less than 4 is important because I take into account, for instance, the regular grid in 2 dimensions, okay? So the idea is very easy. In order to see that is difficult, so the P completeness for degree 5, we have to, with the configuration of the automaton, to construct circuits. It's enough to construct monotone circuits. That's the idea. We have wires, we have diode, say information flow from left to right in this case. That is the dynamic of the information in this case. And we have the OR and the AND gate. Here for the OR gate, we see the degree 5. The arrows are put there because inside there are diode. Okay, so there are 2 ones that are fixed. Remember you that one is fixed because we are looking the freezing or the booster percolation case. Okay, so for the most interesting for me case is when the degree is bounded by 4, because in this case we had to exhibit an algorithm that is better than the sequential update of the network, and we have to characterize the configuration of automaton. So, and we do that in log n to the 2. So in a parallel computer. So it's in NC2 anyway. What is the idea? Suppose in the automaton that the decision site is here in the middle. The site is in 0. So you construct the connected component related with this 0. Okay, and you may do it very quickly in a parallel computer. So you have the zeros here anyway. That is the configuration. It's an example. And after that, you take the component of zeros, which is a connected component with him. You see in this case that the degree of 0, let's see here, is we have 2 here. So this side to the left, we have an alliance there. And on the other side, we have another alliance. So since the degree is 4 and we have the prudent behavior, the central side decision, it is enough that 2 branches are fixed. Fixed because are stable. The first alliance to this side and the first alliance to the other side. That is equivalent to compute be connected component in parallel. And there are algorithms for that. So this problem is in NC2. So that is the idea. So for degree less than 4, the problem is easy to determine or to predict. For less than 5, for more than 5, it's difficult. But in the other case was kind of the one remained fixed, so it's not really a consensus problem. So now I come back to the usual case of the majority network. But of course, with the same construction that above, one is easy to prove that for arbitrary graph, say not planar graph, is P-complete. It's a direct to construct that. But we prove it that the over planar graph, we have the same behavior for the prudent strategy. And there, we have a theorem that the planar graph is P-complete. What is the problem in a planar graph? It's like the problem in a city. When we have the flow of cars in a city, we have, of course, traffic lights. How to put in the graph the traffic light to create a crossover of information? Of course, we use it. Remember that for the parallel iteration, there are two cycles. We use the two cycles, that the flip-flop, in order that information goes in one sense or in the other in the planar graph. Like here. Here we have the same kind of unit that before, but to the left, and the bottom left, we have the crossover gadget, and in the middle is the two cycle, which is the traffic light. So information came from A or B, and it's going to top to the bottom, and from the bottom to up to the other side, depending on this kind of traffic light. So the problem is P-complete in this case. And that is a resume of what happened here. In one dimension, Chris Moore, but there are several proofs anyway in this moment, but it's easy in C. And in 2 dimensions, for the parallel update in 2 dimensions for the grid, not the grid is a particular case of planar graph. We don't know what happened. It's an open problem, the complexity. But if we take the synchronous update in 2 dimensions with the von Neumann grid, the problem is in class AC. We may reduce it and to create and to with the more interesting algorithm for the asynchronous iteration. But for the parallel one, here the problem was open. Of course, in 3 dimensions, is P-complete. It's essentially the same construction that before in this case. And now consider that is one of our last results in the last month. Okay, consider now a 2-dimensional grid. Okay, with in this case the von Neumann neighborhood. Okay, and consider that at each individual is a prudent strategy in case of tie or a biased strategy, one of them. So you have the network, an individual has 2 kinds of behavior in order to change his opinion in case of tie. In this case, we prove it that the 2-dimensional grid, in the 2-dimensional grid, the parallel, consider the parallel iteration, PRED is P-complete, which is very tricky because we use it. But in a very tricky case, because we have the von Neumann neighborhood is not an arbitrary graph, this kind of traffic lights. And the idea is the following: we have, there is the Goles configuration. So that is a crossover, which information comes from one side and the other, and so on. We have the AND, the OR, and signal multiplication, every gadget necessary to create circuit, diode too. And here is the idea to create circuit. We have this, for instance, to the left, here we have a circuit. We put it in the matrix, and in the matrix after that, we put it signals going to the horizontally and vertically. And when they use crossover, and we compute every layer of the circuit. Here is the compilator of that. That's in Goles, the equivalent of the previous circuit. And there we have the dynamics. It takes a lot of time anyway in parallel. Okay, so of course. And the final thing that I would like to share with you is the signed majority. So there we take the 2-dimensional grid where people may receive the opinion of his neighborhood in a positive fashion. We are with the friends, or in the opposite one with the enemies. Okay, so you have plus and minus. in the network. And the majority, for instance, here in this case, if take into account the negation of x1 and the negation of x4 for the same operator's majority. For that, we classify every behavior from the dynamical point of view like that. We have three cases. The symmetric sign structure, like the left one, they have the three cases here. We have three cases. Every behavior we may classify in three classes of dynamics. The symmetric case, which are the 6-1 to the left, where is NC1 hard is in class P. We don't know more than that. And the limit cycles are of period 2 or fixed point, okay, in this case. In the anti-symmetric case, anti-symmetric is if you take the network, you have a plus and a minus everywhere, okay? We may construct cycles which depends on n of the size of the network, polynomial period. And in the asymmetric case, asymmetric is a mixture between symmetry and asymmetry, anti-symmetry. There is very, very complex. By p-space behavior, we have p-hard problems and limit cycle and with super polynomial period. So I was very quickly maybe, but in order to be correct, I finished here. That is a view from my campus in the Andes Mountain in a nice day in Santiago. Not every day is like that, of course. Okay, thank you very much.
Thanks. That was two great talks there. Let's see. There are many questions, but I think we're saving questions for another hour or so. Let's see. Who do we have next here?
Okay,
Yes.
thank you very much.
Hi, it might be me.
Yes, so it's Jon Woodard again. I'd like to introduce Emin Gün Sirer, founder and CEO of Ava Labs. Thank you for joining us. Excited again to hear your talk.
Thank you very much for having me. This is such a great audience for what I'm about to describe. I'm actually a professor at Cornell University in computer science. And what I want to do today is talk to you about a new family of consensus protocols inspired by cellular automata. And let me see if I can share my screen with you. Let's try this. Desktop share. I hope you can see what I'm seeing. And is it working?
Yes, but yes. We probably see more than you.
Yes,
perfect. Okay, well, so let me tell you a little bit about where we are in the space of blockchains. This work was motivated by the incredible things that we're seeing happen in the blockchain space. And my background, for those of you who might not know me, is that I've been at Cornell for about 20 years. My core background is in systems, computer systems, specifically operating systems and distributed systems. I took an early interest in cryptocurrencies and developed a proof of work-based currency in 2002. That's 6 years before Satoshi. He, of course, came in and came up with a new family of consensus protocols. This is a relatively rare event. Doesn't happen all that often. I want to give you a brief summary and synopsis of my area. And hopefully by the end of my 30 minutes, you will be in command of the entirety of, at a very high level, of course, of the developments in distributed systems relating to consensus. So let's start with the motivation. This work was all motivated by blockchains, and blockchains are very, very big. So they are a new asset class worth in total far more than $1 trillion, even as I speak. There are thousands of cryptocurrencies, more than 8,000 of them, all serving different functions. There has been more than $25 billion of venture capital invested in these startups. Not that that number matters at all, but the number that might matter is that there is more than 50 billion invested by the public. These are actual people putting their money into this area. They see some future here and a promise here. So there are some really interesting accomplishments in this time frame. So in the time that cryptocurrencies have been around, it's been about 11 years since Bitcoin's inception. There hasn't been a single person running around with a pager in his or her pocket. And yet in that time, Bitcoin has never been down. And I can name you at least half a dozen times that Amazon was down and Google was down and Facebook was down. So that's a pretty interesting scenario. These systems are inherently resilient. And something that I often use to check myself is the social movement. There are more songs written about these cryptocurrencies than there are songs about Google, Facebook, free software, and so on. So there's something here that captures the public's imagination. And what is it? Well, at a techie's point of view, I think what we're seeing is very, very simple. We're seeing the emergence of practical Byzantine fault-tolerant systems, just like we saw the practical emergence of client-server systems with the emergence of the web. We understood how to build those kinds of systems for many decades, but it took the web to come in and prove to the world that these things can actually serve a useful function for society. Now we're seeing the emergence of blockchains, and they're coming in and showing that we can build services without a single participant in charge. We can ensure strong integrity, even when there are players who are inside the system working to undermine it. We can withstand faults from within the system. We can provide auditability and transparency to participants. And a new family of applications are coming in. These are mostly financial at the moment, but they also expand beyond finance. So we're seeing new corporate structures, new business flows, new kinds of high integrity systems, new financial instruments, and new corporate structures coming in as a result of the advances in this area. So my short message for you all is going to be that there are deep scientific contributions in this space, in the burgeoning subdiscipline of computer science, and it touches multiple disciplines, and especially physics. It really touches physics, and especially what I'm about to show you is inspired very much by physical processes. So the work spans distributed systems, networking, cryptography, game theory, verification, programming languages, econ, of course. And so another second takeaway is today's protocols, the ones that preceded what I'm about to show you, are not equipped to achieve the dream that everybody is buying into, the dream that everybody is raving about online, the dream over which they're attacking Elon Musk and everybody else who dares to go speak ill of anything else. That dream cannot be achieved with today's protocols, with yesterday's protocols, I should say. And there is a protocol today that can actually do that. There's a protocol family, and that family is large enough that perhaps some of you will take the torch here and come up with new ones in the same family that are interesting. So let me give you a brief overview of consensus protocols. Let me make you into experts in Byzantine fault tolerance in the space of next 5 minutes and bring you up to speed to the level of an expert circa a few years ago. It didn't really take all that much. So what's our goal? Our goal is to create a ledger. This is going to be an append-only ledger. We would like this to be a well-ordered ledger. There's going to be a set of validity rules, and essentially we're going to be keeping track of assets on a ledger. Alice gives to Bob 10 coins. Bob gives those coins to Charlie, and later on, Charlie gives a subset of those coins to David. If Charlie tries to create some coins against the rules, then that's an invalid transition, and it will not be admitted into the ledger. At a very informal level, that's essentially what we're trying to do. Now, for us to do this effectively, we all have to check what is a valid transition, and we all have to take the same step. It would be what is called a safety violation if I were to say, Alice gives her money to Bob, and Mr. Wolfram to say, Alice gives her money to Charlie. That money should be spent at only one location. All correct nodes must agree on every single state transition. So I'm not going to belabor the definition of consensus here, but there is going to be a safety criteria that says that all correct nodes agree on the contents of every slot in this ledger. And there's going to be a liveness criteria that says if the system is able to take steps, it does take steps. And there's going to be a non-triviality clause that says a system that just sits there is useless. It should be taking steps as long as there are user inputs submitted into the system. So approximately speaking, all consensus protocols come down to at least these three properties. So how do we achieve consensus? That's the real question. And this problem presented itself 45 years ago, at the dawn of distributed systems. It's a very well-known problem. It took a little while to get extracted, to be specified clearly enough in an isolated form for people to make progress. But progress people made. The work in this area, the vast majority of the work happened in the 80s and 90s. And it happened in a framework by two pioneers that we all look up to. One of them is Leslie Lamport, the other is Barbara Liskov. They both have Turing Awards, the highest honor in computer science. Very well-deserved ones, of course, for a wide variety of work they did, including the work that they did on consensus protocols. These protocols are at the heart of every single distributed system you use. If you go to Gmail, you get directed to an instance of your mailbox. There are many computers at Google that hold your mailbox. They all agree on which messages you received and in what order. Now, because it's Google, they don't have to worry about Byzantine attacks from within. And we're going to see that when we build a blockchain, we do have to worry about that. So protocols that handle Byzantine faults, as opposed to protocols that handle more benign errors, are different. And the Byzantine ones are much harder. I'm going to go and tackle the Byzantine case because it's much more general. So what happened is 45 years ago, people started coming up with protocols, and there's been a series of work. The best of these protocols is, at the moment, is called Hot Stuff. It was the first author of that protocol is a student of mine, and he went to the West Coast for a summer. He worked on a classical protocol called Hot Stuff, came back and said, hey, I worked on something fun, but now I want to work on something even bigger. And he's currently working on the Avalanche protocol, which is what I want to get to today. Hot Stuff, incidentally, is the protocol used by Facebook's Libra project, which has been renamed to Diem now, but that is the best of its breed. That protocol scales to about 100 direct participants. So Zuckerberg wants to replace the world's finance system by himself, with himself plus his 99 best friends. So I want to show you something that scales to something far larger. So while that was happening, in 2009, Satoshi Nakamoto came along and he said, look, all the stuff that you guys did, all these academics did, it doesn't lend itself to an open, scalable, internet-wide system. And he came up with a new protocol with a brilliant insight. And let me talk about these, and let me give you the high-level insights without getting into too many details. So here is how classical consensus protocols work. So this is all work that came before me. In this framework, what they end up trying to do is duplicate what a parliament might do. And they want to make sure that this parliament is not fooled by some members of the parliament who might flip and flop, who might lie, who might engage in Byzantine activities. So at the core of these protocols is an assumption that we all understand and agree who is in the parliament. There's not going to be that many of them because you'll see why in 2 seconds. And there's going to be a read protocol and a write protocol. So when it's time to pass a law, what we have to do is we have to write to a portion of the parliament. Now we can't expect to write to everybody in the parliament. Some of them might die, some of them might be dead, some of them might be Byzantine and never respond. So it would be a folly to write to everyone. It would be a folly to write to just one of them, because if he dies, then the law that you thought you passed didn't really pass. It died with that guy that said okay to it. So what do? Well, it turns out that if you were to write to 67% of a parliament like this, and if somebody who's reading from the parliament reads from 67% of the parliament, then even if a third of the parliament was full of Byzantine people, tricksters who lie to you, tricksters who accept something and then pretend they didn't accept it, who flip and flop and do all sorts of things. Even if that were to happen, well, 67 overlapped with 67 yields an intersection set size of 34 by the pigeonhole principle. So it turns out that 45 years of work on classical consensus protocols all comes down to proofs based on this pigeonhole principle. So this intersection of 67 and 100 over 67 and 100 yields 34 people. So that means that if 33 of these people were evil and Byzantine, you still have this fellow right here who is correct. And he will retain the state from the right and transfer it to the person who read. This is the essence of a quorum. And this is used very commonly. In fact, this is the foundation of all classical consensus protocols. These protocols, I mean, if you figured out this stuff and you figured out the proofs that come with it, essentially what you have to do is to commit something, you have to typically do 2 rounds of this. You have to know that 67% of the parliament got written to, and you have to know, this is the second part, some people get this part wrong, and you have some disastrous failures afterwards. If somebody, so you have to know that 67% of the parliament got written to, and you have to know that 67% of the parliament knows that 67% of the parliament got written to. If you can get those 2 facts correct, then you can build yourself a classical consensus protocol. So that's great. This consensus protocol provides a probability 1 guarantee. That is, it's absolutely certain that you know, once a decision is made, then that decision will be transferred, will not be reverted, etc. However, efficient constructions of classical consensus protocols rely on a leader. That leader is both a bottleneck and a vulnerability. Further, they do not scale. They require n-squared information to be transmitted. So for me to know that something is committable, I need to hear from about, you know, order n of the participants in the parliament. And in fact, order n people have to hear from order n people. And therefore, n-squared messages have to fly around. N-squared bits must need to fly around. So that is the reason why the best of these protocols does not scale to more than about 100, maybe 200 someday participants. What they end up doing is, if they try to accept more than that into the system, they do sortition, they do some sub-selection, subcommittee selection. So you pretend to have a big parliament, but then for every decision, you actually consult only a small sliver of that parliament. So the security of each and every decision comes down to that small set. So these systems all existed. And Satoshi Nakamoto was well versed in them. And he, as I said before, he looked at them and said, look, these are not open. These are systems that are fragile, and they lead to permission networks. And those of you who are familiar with EOS, EOS is based on the classical consensus protocol. There are 21 validators in EOS. And shortly after EOS was launched, those 21 people turned into a cabal, and they wouldn't let other people penetrate into the cabal of 21. Okay, so I'm not going to belabor how Nakamoto consensus works, but very, very quickly, the idea is that transactions are submitted and miners collate these transactions. They solve a corresponding cryptographic puzzle in each block. They locate that block. They are rewarded for this. They get to include one magic transaction called a coin-based transaction that gives them the right to mint some coins. In the early days, it was 50 Bitcoin. These days, it's a lot less. And so they create these coins and create these blocks. Now, the nice thing about the Nakamoto consensus process is if somebody wants to attack the system and wants to fork, well, what they're going to be doing is they're going to be going back in history and trying to create an alternative blockchain. But to do that, they have to solve an alternative series of puzzles. And solving that alternative series of puzzles is hard. And if the hash power, the hashing power, the ability, the solving power, the crypto puzzle solving power of the adversary is less than the majority of the network, then he will never be able to build a chain as long as what everybody else is building. And therein lies the security guarantees and the security basis of the Bitcoin protocol. So that's Bitcoin in a nutshell in 1 minute. And so if you try to go back and rewrite, you pay somebody, you pay an exchange, you take your money out in the form of fiat cash, and then you now want to go back and take your coins back, you cannot do that unless you have majority hash power. And so this is interesting. This protocol, or this family of protocols, based on this what is called proof of work. These crypto puzzles are called proof of work. Proof of work protocols are nice, but they they're nice, but they're probabilistic. And the magic, the amazing observation that Satoshi made is that 1 minus epsilon in practice is identical to 1. So the probability of a finality here for any block is not exactly 1, like in the previous protocol. But Satoshi would say to you, look, you're doing your computation on a chip, on a hardware chip, and that chip is not the idealized Turing machine. It is not a definite, it's not a probability 1 computational device. It makes errors. The hardware engineers assume some error rate. And in fact, at scale, you occasionally see that. So he would say, look, just make the epsilon really small and much smaller than your probability of your hardware failing. And you can actually build great wealth on top of a system like this. And today we have, after 11 years, as I mentioned, we have about more than $1 trillion worth of assets on many of whom are on these proof of work blockchains. All right, I want to tell you, I want to quickly go through what's happened. Of course, we went through, this is practical. Anybody can join. It's permissionless. And it was 1 CPU, 1 vote in the early days. Quickly, people rushed to buy some FPUs and GPUs, and they end up getting more votes as a result, getting more coins as a result. They started building FPGAs. They started building these crazy ASIC farms, starting with these amateur situations to these fly-by-night operations in China, to these kinds of scenarios, sometimes going up in flames because all of that power is actually kind of hard to harness. But this was the scenario. This is an Estonian Bitcoin farm. What this person is doing is just solving a lot of these crypto puzzles, and the energy going into this is actually going in to keep other miners at bay. The throughput of the system isn't affected. You could add any number of these machines, and as you add them, Bitcoin would not speed up. So here's a much more modern Bitcoin mining farm. So right before I get into Avalanche, let me summarize the situation as of 3 years ago. Nakamoto consensus consumes immense amounts of energy. It's on par with the Netherlands right now. It's more than 2 Denmarks, it's more than 3 Irelands, it's more than 4 nuclear power plants worth of energy going into just keeping this ledger. There is no connection between the energy burned and value of the token. You can burn as much as you like, doesn't establish a price floor for your token. It's an environmental disaster. It leaks value out of the system to power companies. It melts the poles, it kills polar bears. And it shrinks the feasible envelope for the coin. So if the coin price drops precipitously, then miners, if they are, the miners can, the economically rational thing for the miners, if they don't believe in the future of this, would be to shift their mining power to another coin that uses the same hash function whose price is higher. So you can have coin debt as a result. So let me, and the throughput of these things, or the performance of these things, is abysmal. To send a Bitcoin to somebody, you have to wait 60 minutes, 6 confirmations. To send Ethereum, again, for almost equivalent to security, you have to wait around 30 minutes. And you can't just make the blocks bigger. That doesn't work. And what is all this for? Why are we spending about 1 to 2% of world's electricity production for this ephemeral thing we're going called decentralization? It's not even that decentralized. It's inherently centralizing because you need these giant farms. And you need the kind of electricity contracts that allow you to have a cable this thick coming into your installation. Only so many people have that. So it turns out that, at least the last time I did a study on this, we did a study on decentralization in these networks a few years ago. There were 19 mining pools for Bitcoin, even fewer for Ethereum, and the top 3 or 4 miners completely defined the chain. So these are, if you just want to run a chain that is determined by 4 participants, there are so many protocols that are far more efficient than what we've got here. So can we do better? And I want to tell you a little bit about what's better out there. So a few years ago, a group that's anonymous, that calls itself Team Rocket, came up with proofs of correctness for a protocol called Avalanche. My group was working on similar lightweight protocols, and we collaborated with them. And there's a paper out there that describes exactly how these protocols work. But here are their salient features. The protocols I'm about to show you combine the best of the Nakamoto family with the best of the classical family. They're based on cellular automata. They achieve quick finality. By that I mean about 1 second, slow blink of an eye, and the transactions are immutable, forever ensconced in whatever it is, in immutable blockchain. They can achieve very high throughputs. They scale to millions of nodes. They're robust, they're quiescent, they're green, they're sustainable. When there is no work to be done, they do nothing. They just sit there, don't consume any energy. When there's work to be done, they do it very efficiently, as you can see by all these numbers. They're inspired by epidemic protocols and gossip networks. So gossip is a topic that Cornell Computer Science is known for, and this is in the same category. And they're very easy to understand. I'll tell you roughly how they work, and I think anybody should be able to see approximately how they work. The core property that they're going to build on, that physicists might find very familiar, is that they view a distributed system as a physical system consisting of independent particles interacting with others. They model its level of energy, and they design protocols that seek to efficiently settle into a low energy state. And they ensure that the low energy states correspond to desired outcomes. So we'll create a metastable world, and then we'll look at how quickly we end up in a good state. There are a bunch of protocols in the family. I'm going to tell you about Slush. It's the simplest one. It's not exactly Byzantine, but you can see how it can be extended. And then there's Snowflake, Snowball, and Avalanche. And I won't have time to go into their details, but maybe in the Q&A I can answer questions. So here is how these protocols will work. And they will end up doing the same dumb thing over and over again. And for analogy purposes, I want you to imagine that we're in a giant stadium corresponding to a set of nodes, and that we don't know everybody in the stadium. It's not a parliament. In a parliament, we need to know everybody. Membership needs to be precise. If you write to 67 people out of 100 that you think is the parliament, but I believe a different parliament is in effect, then those intersections and pigeonholes will not work. So that's why those protocols are so fragile. In Avalanche, we're going to be dealing with a very large network, and we will not require precise membership. So giant stadium, I know some of the people there, you know some of the people there, but we don't know everybody in there. And we're going to make a decision. In this case, we're going to make a decision between blue and green. Okay, I'm going to abstract away the consensus protocol. So Alice pays Bob or Alice pays Charlie. We don't care which outcome happens, but we want the entire set of correct nodes to pick the same outcome. That's what's required by our safety protocol. And let's start in the worst case scenario. When we go into the stadium, half the people start out with a slight preference for blue, half the people start out with a slight preference for green. That's the core, that's the beginning state. And here is the core of the algorithm. Here's the silly, stupid thing we're going to do repeatedly to achieve consensus. Every one of us, at the same time, we will poll a small number of the people in the audience. So I look around the stadium and I say, hey, you, 5 people. 5 of you, what's your preference right now? And answers come back, blue, blue, green, blue, green. And I look at this and I go, okay, it looks like there's a preponderance inside this network based on my subsampled vote towards blue. And I'm going to flip my state to prefer blue. And you do the same and everybody else does the same all at the same time. Now, it turns out that, and you can reason at the extremes very easily. Imagine, so it turns out, here's what's going to happen. Let me just first give you where we start from the fully bivalent state. After one round of this subsampled voting, it's going to be incredibly unlikely that we are still at a 50-50 split. We could be at a 50-50 split. If we are, then the next round, we're going to take care of it. But more than likely, we're going to have a slight preponderance of one color or the other. You know, let's say just randomly, I think in my example, blue was a little bit more. So we were 50-50 blue-green at first, but now we're going to be, just because of random variation, we're going to be 51 blue, 49 green. If that's the case, then the next round, we are more likely to go to blue than we are to go to green. By how much? 51%. And so the next round, we're likely to go from 51% to 53. Then the next round, we're likely to go from 53 to something slightly larger, like 55, 59, 60 something. And suddenly we're going to find ourselves, I think, I don't know if you can see my pointer here, we're going to find ourselves descending down this path. And you can imagine that if everybody, except a few people are inside the stadium favoring the same color, then the rest of the people will convert to that color. This is the point of no return. And some people in the stadium might be Byzantine. And as long as we're in the middle, they have the ability to pull us back from the brink. So they might pull us back and forth, but there is a point that we can compute here that if we are beyond that point, then their pull becomes lesser and lesser in strength, and we're more likely to converge towards a lower energy state than to be under the control of the Byzantine adversary. All of these are Markov processes that can be analyzed precisely and can be characterized with regard to the size of the Byzantine attacker. So if you were to look at a global time counter and look at what happens, typically in the worst case, you start out in a bivalent state, and there's some polling that happens. You might kind of go up and down a tiny bit, but then once one side starts pulling away, it pulls away very quickly, and the network converges to one extreme or the other. So I don't want to go into any of these except to say that there are theorems that characterize exactly how this process plays out, and it reaches consensus in a finite number of rounds. The expected number of rounds is very, very, very quick, and sample size K is optimally very small. You don't need to sample large numbers of nodes. And now what I showed you, or what I described to you, informally, of course, was a very simplified version of the protocol. You can add bells and whistles. So I described to you a change of preference anytime a majority was sampled. Well, you don't have to do that. You can take things like you can have a confidence counter, and nodes don't have to flip and flop at every color change in their sampling, and so that will confer to the protocol a higher speed and better security. All of these are analyzed in the Avalanche paper. And so I'm not going to describe any of this. But we can go from slush, the very simple protocol I described, to a protocol that retains a little bit more state and is resilient to an even bigger attacker, Byzantine attacker. And you might say, hey, well, look, in a blockchain context, you're making so many decisions and you need to be very, very fast. Well, how do you do that? You can't be running a consensus protocol on every decision. Well, so what one can do is you can entangle the decisions. You can say, look, so I might be deciding between Alice pays Bob and Alice pays Charlie over here. And this is a consensus instance. I'm going to be doing this Avalanche thing up here, but there are other people who could build on it. There's David paying Eve over here, and so on. What one could do is one could create a graph of dependent transactions so that a vote for somebody deep in the graph, low in this picture, this is a tree-like picture here, somebody who votes here implicitly votes for everything that preceded him. So this is a cute little trick, and it allows us to be incredibly efficient and to tie decisions together. So in one fell swoop, a vote for here is a vote for its predecessor, is a vote for its predecessor. So we don't have to run separate instances of consensus protocols. We can intertwine them and make one decision at the tail here, and thereby commit a whole range of transactions into immutable memory. The expected overhead then becomes one per decision. This is a pretty big result, I think. So let me now make it practical and conclude very, very shortly. This is a very efficient protocol. It turns out, and you can show this by analysis of Markov chains. By the way, treating systems like this, treating computer science systems like they are continuous physical systems is pretty unusual. To physicists, this might be natural, but to computers, to my colleagues, it's very unnatural. And this is not something that they are used to. But you can easily do the math. And when you do, it turns out that the number of rounds is logarithmic with network size, of course, that should not be surprising. But the numbers are tiny. So it turns out that for a network of 10,000 nodes, sampling 10 nodes at a time, less than 17 rounds suffices to achieve consensus. So it's just 170 messages per node to achieve consensus among 10,000 nodes. So that's a huge reduction. If you were to try to use a classical protocol, every node would have to send 10,000 messages. The backbone of your network would have to handle 10,000 squared messages. And so that's not so good. So what does that mean in practice? Here's a dated graph. It shows the latency of a transaction. In the blockchain space, there's a lot of frauds, as you all know, and there's a lot of frauds when it comes to, in the database space, there's a lot of fraud as well. So there's a lot of lies about performance numbers, especially about transactions per second. It's a very easy metric to game. So there are all sorts of hokey claims that you hear from all sorts of people. But latency is really hard to game. So that's what I want to focus on. The Bitcoin latency is 1 hour. Okay, you have to wait for 6 confirmations for a pretty small attacker, actually, it turns out. If the attacker is bigger, you have to wait more than an hour. For Ethereum, corresponding security, it has more frequent blocks, probabilities are on its side. It's about 555 seconds. That's math that was done by a PhD student in London. There are other protocols that do sortition. So, a good protocol in the classical setting is Algorand, and it takes 50 seconds for this decision. Avalanche takes, it says 2 here. We conservatively say 2. In the current network, it's about 300 milliseconds. But as the network grows, it might be even larger. In this one, it's particularly pessimal. This was 2,000 nodes spread across the globe. Our current network is about 1,000 nodes. We're very happy to report that it's achieving consensus delays of 300 milliseconds. So security, there can be tens of thousands to millions of direct participants in Avalanche. So the decisions are strongly immutable, and this number 10,000 plus compares very well to 19 mining pools for Bitcoin, 11 mining pools for Ethereum at the time we measured it, 21 for EOS, whatever it is for Ethereum 2, and so on. Those are all very small numbers. Another fact that's kind of cute and very, very interesting is that this protocol can tolerate a large fraction of Byzantine participants. It can guarantee safety, can't guarantee liveness. That's very hard for an attacker this big, but it can guarantee safety in the presence of a Byzantine attacker larger than the majority. So somebody can come in and attack your system, but they cannot revert what happened even when they're larger than the majority of the system. That's one fact. Here's another fact that's very interesting. Classical protocols, these protocols that I talked to you about that are based on collecting signatures from a parliament, they do not degrade gracefully. They degrade the moment the attacker is bigger than 33%. It's a well-known result. So as an attacker, you know exactly when you're going to succeed. In contrast, in Avalanche and similar networks, what there is a parameterized security component. So let's say that the system designer says, look, I'm going to parameterize my system for an attacker of size, let's say 40%, to cause a problem once in 10,000 years. So what happens when the attacker is bigger than 40%? Okay, suppose he is 41%. What happens in Avalanche is, of course, because you designed it for an attacker of size 40%, problem every 10,000 years, he's bigger than what you designed for. Your guarantee goes out the door. Okay, so you can no longer make that old guarantee. But what happened? Well, he's going to be able to cause a problem more frequently than once every 10,000 years. But how frequently? Well, maybe once every 5,000 years, depending on his size. If he is only 45%, approximately speaking from the top of my head, it goes from, if it's like one in 10,000 years, goes down to 1 in 5,000 years. If he gets to 60%, it goes to 1 in 1,000 years. At some point, of course, he is going to be, at like 60s, 80%, around there. After 60%, around 80%, he's almost guaranteed to cause a problem if you parameterize for an attacker of size 40%. But he's not guaranteed to win. This is a very interesting property of the system. So classical systems are notoriously difficult to design because you have to pick these thresholds, and they're so fragile around the threshold. These systems are robust. They're kind of like physical systems. And as I said, it can handle imprecision and membership. I don't want to belabor this, so we don't need to necessarily to know everybody who's participating in the system. Oh, this is a graphical demonstration of that what I just talked about. I wish I had talked about it with this graph on. You can see that there are about 1,000 nodes. And if you parameterize your system, if you were using a classical consensus protocol, as soon as the attacker is over 33%, he wins. Well, with Avalanche, with these particular parameters, the attacker would have to be around 60-something% before he has a good chance of winning. Okay, to wrap up, I gave you a brief outline of the intuition behind this new approach to consensus. I think it is the third biggest breakthrough in my area of distributed systems. And I think this represents a very, very interesting approach to the consensus issue at large. And it brings to bear tools from other areas, from physics, from physical systems to discrete systems like computer systems. And the boundary between discrete systems and fluid continuous systems begins to blur, and we get really interesting results and can build very exciting systems. I want to wrap up by saying that there is an exciting future ahead. The blockchain dream is really amazing. That vision set forth by Satoshi Nakamoto of assets traded globally is an amazing one. And systems without centralized components, without intermediaries that are controllable easily by sending a subpoena to a single party or to a few parties are just a thing of the past. But as I said, the previous protocols in this area did not come close to fulfilling this incredibly appealing dream. But we are lucky that we have a new set of protocols that have been analyzed thoroughly and offer some hope of reaching that dream. With that, I'd like to conclude and give up the podium to whoever might come after me.
Thank you. Quite an inspiring talk there. Again, this is Jon Woodard. I'd like to introduce Aaron Schutza, Director of Research at Topple, for the next talk.
I'm Aaron Schutza. I'm the Research Director with Topple. I'm going to share my screen here. All right. Can anybody see anything? There it is. All right, so today I'm going to introduce a underlying modification, or a modification to the underlying protocol of Ouroboros. This is a modification that I was inspired to pursue while I was implementing this for our consensus layer. So Topple is an ESG and impact focused application layer 1 blockchain company, and we're integrating and developing all our own infrastructure. So a high level overview, and this is kind of the main 3 bullet points at the top. We introduced this new staking procedure, and I'm going to go over the background that's required. It's hard to understand the nuance of this new staking procedure without understanding the underlying protocol of Ouroboros prowess. We go into the security modeling. We use a Markov chain framework to model the security properties of the blockchain protocol. And then finally, I'm taking this from a different perspective. We're not interested in automata in the context of protocol design, but we're using automata to show security. So I just want to be clear about the application, the use case. So we developed this automata model to show security in this context. And this modification to the staking procedure itself induces a new block time distribution. And this is what the profile looks like. So keep this vision in your head through the top. And the prowess has this exponential profile of block time intervals. And the jump from prowess to this tacticos distribution, as we're calling it, is an important connotation for the protocol throughput, and also protocol security has really important implications for the scaling of resources and participation. So importantly, it has this feature where it converges much quicker than exponential, and then it's 0 at this origin. And think of this as a time interval distribution. So to outline and just to give a little background and timeline of the relevant works. First and foremost is the original Nakamoto paper introduced this chain selection rule, and we're in this setting of eventual consensus. And it wasn't until years later that these security papers came out, which allowed us to really, an entire line of research to flourish and develop these provably secure consensus protocols in the dynamic availability of the same security setting that the Bitcoin decentralization mechanism realized. So dynamic availability and permissionless, 2 key points. And then importantly for our work, this KRS framework, which formalized blockchain security properties in the terms of Markov chains, is really important and influential for us. My colleague Tuyet made a really beautiful insight in finding this paper, helping us apply it. So, and also relevant, and I touch on these points, it's been developed in this general context for any round-based protocol, but we have linear consistency guarantees, and that's like the common prefix property in these slot-by-slot, round-by-round protocols. And then there's new work showing consistency of the tie-breaking rule, where the honest ties can actually add security. So just to show all the pieces of the puzzle for this kind of picture that we're putting together, we have honest parties as little angels, and the adversary who's deploying any strategy to try and get and game the system and get some advantage. The distributed network of peers is permissionless. Any node only sees its nearest neighbors and isn't aware of who's on the network. And blocks cascade around this distributed network, and they're just kind of coming up in stochastically. And we have to design our consensus protocol in the face of this, in the face of some participation bound. So we have to plan for that participation bound. And then naturally, there's this kind of popular image of a trade-off between these 3 axes, and it's a trade-off between security, scale of participation, and then the speed of confirmation. So speed of confirmation in our context is what we're considering as liveness, and then that is the quality of this new transactions being uptaken by the ledger itself. And then persistence is the quality of it remaining on the dominant blockchain ledger. So, and then we have this, we're in this setting of Nakamoto style proof of stake, and this has us kind of in the same vein as Bitcoin and the underlying Nakamoto consensus. We have blocks that are pointing, and here we're a forward-directed graph model. So old blocks point to newer blocks. And in some pictures have it the reverse order, but it'll make sense why we're using this forward-directed later in the talk. And think of the adversary who's always there. He's trying to eclipse parts of the network and show them an alternative history. So that's the adversarial strategy that we're most concerned with. And otherwise, the adversary can participate honestly, or it can not participate at all. It can withhold blocks, and it can store a reserve of blocks and then diverge to no view of the network and break these unique convergence opportunities, that is, events that force the network to come all to the same node view, the same agreement, or the same like blockchain head. And then this common prefix area is guaranteed to have the same block identifier at a certain depth. And this probabilistically jumps around this depth. So in the proof of staking procedure, we have this kind of synchronous evolution of slots, and they're just increments, they're time intervals. And in this setting, we can have sort of 4 different possibilities. You can have a unique honest leader, honest ties, adversarial eligibilities, and then empty slots. And the idea is that you allow for lots of empty slots where no one's even designated to be leader, that you allow for the network to synchronize in these spaces. And the 3 main ingredients of this staking procedure are a signing routine, which tells who has what on the ledger, a VRF, which dictates what these eligibilities correspond to and to whom, and then a key evolving scheme, which importantly orders these and authenticates block headers, but also assures that honest blocks that are committed to the network can't be retroactively corrupted by some adversarial party. Now, mathematically, the staking procedure plays out like this. And this is one of the most crucial aspects of this entire analysis, this property of independent aggregation. And not only does it uniquely define the staking threshold, it also eases the analysis for calculating the probability of all these events and the distributions that play out of this process. So primarily we're concerned in Proust with this active slots coefficient, which dictates how many empty slots and how many occupied slots will be on average. And then the epoch by epoch, which is these kind of, in the modular setting, you have an epoch nonce that sets the randomness for the epoch, and then you repeat the process. And then there's an assured way of updating the epoch without any one party biasing the randomness that's going into this process. And here we're on a small scale, but in reality, it's like tens to hundreds of thousands of slots per epoch. So the staking procedure comes down to this inequality. If in a given slot you have a winning nonce that satisfies your staking threshold and your party P is a sub-index for party, then you're eligible. It doesn't mean you will be able to make a block or actually extend, and you'll see why. And this, kind of ticker tape of eligibilities translates into many different possible histories based on what happens on the network. So we're just talking about eligibilities here. And then the probability distribution of extensions and the spacing between blocks we're interested in for the purposes of this talk. And I want to just briefly show, this is the block time, this theoretical prediction for the block time interval, just assuming honest participation at 100% participation. So this gives us a distribution of the number of slots between these eligibilities. And we can think of just going up this set of eligibilities and building the maximum length. And this is what that distribution of block time intervals would look like. And incidentally, in Bitcoin, they have in the Bitcoin protocol, there is an exponential distribution of time intervals that's measured empirically. So this picture of times blockchain forks in this Ouroboros setting, tines are another synonym for forks, but they kind of also correspond to the connotation of these labels and slots. So tines have to be consistently labeled, and you can think of two tines having a common prefix. And an adversary, they're basically able to use their eligibility twice, and they can choose any history that they want. So an adversary is trying to diverge the node view. Remember the red blocks in the previous slides. They're trying to make this balanced fork and diverge the node view as long as possible. That's the game that it's playing. And this can't be reforged because the adversary can't get the private information to remake the block, right? So this constitutes a closed fork. That's what that property is called. And then we go up the string, and then forkable string analysis is the formalism that's used to describe the adversarial behavior in this context. So forks can also happen natively with just network desyncs and network delay. And you can see there's only honest eligibilities, there's no adversary, but we're still getting blockchain forks just simply because this leader hasn't heard about the most recent block. This happens over and over sporadically all the time. And in the analysis, we use what's called this delta right isolation rule. When we use capital delta, we're talking about network delay. For 1 second slots, rule of thumb, delta is about 10 for analysis. And the security properties of Proust kind of reduce just to this picture of counting the forkable events and the non-forkable events, and you get a distribution. Graphically, it looks like this. You can see this red profile with the forkable events. Anything that's below this delta of 10 is forking the network. And then we've given the adversary 25% of the resources, and it's forking 25% of the time. And now the non-forkable events are these blue curves. So no and this is the most abysmal model of network desyncs, is assuring that there's going to be a fork every time. So in the context of an adversarial setup where you, it's a safe assumption to make. It just eases the analysis and simplifies this network delay model. But you could go to more nuanced network delay models. So prowess is considered secure if the proportion of zeros in this sequence of events is greater than the proportion of ones, where 1 corresponds to a fork and 0 corresponds to a non-forking event. Now, the roadmap beyond prowess is this. Somewhat amazingly, the subsequent Ouroboros protocols are all founded on these 3 distinct crypto primitives: the key evolving scheme, the VRF scheme, and then the signing routine just for the ledger and who has what resources. And then in Genesis, they introduced a new chain selection rule, and then VRF, another domain separated VRF test for updating the epoch randomness. And then synchronization was achieved with these VRF beacons, which are elected in the same kind of vein as leader eligibilities, but they're confirmed by, like, as if they're transactions. So they're independently verified by other stakers. So that's how Chronos actually functions. It's almost akin to a ledger functionality. And then more importantly, there's going up and coming up horizon, there's likely to be an honest tie-breaking rule added into a future version. And it would be easy to implement just off the top of my mind with another domain separated VRF test, but I can only speculate at this point. But it would mitigate these network divergences and then force the network to just adopt one block over the other, right? If there's an honest tie, they have the same block number, but you can just introduce a tie-breaking rule arbitrarily and all the nodes would select one or the other by the time they heard about it. And with that tie-breaking rule, you can actually have the honest ties add to the security, and you only need a simple majority of staking power for the honest participants. So we still are this setting where we have the prowess staking procedure, and this severely limits this chain growth because of this network divergences. It still happens, and it's still not going to really aid throughput, but at least we can come to consistency with the tie-breaking rule. But also think of this: in Bitcoin, there can be hours between blocks because it has this exponential distribution. In the case of prowess, the way it's parameterized, typically, minutes will arise between blocks in the longest time intervals. But that exponential distribution, allows for these long stalls. So throughput stalls when there's no blocks. So we want to modify this staking procedure and stabilize block times. And that is the goal of Tacticos. So we take the same ingredients of crypto primitives and invent a new threshold. We introduce a new threshold. This threshold streamlines the network throughput because it spaces out blocks more evenly on times. There's blockchain forks. So the dominant blockchain will just have steady blocks all the time. And think back to the first picture where we had that distribution, it converged quicker than the exponential distribution. It means you're guaranteed basically to have a block within a certain window. So the mechanism behind this we're calling local difficulty adjustments. The mechanism is called local dynamic difficulty. So if you see LDD, that's what we're referring to. And it's just this notion of adjusting on a round by round basis what the threshold to forge a block is. And it turns out you can do it in a really efficient and simple way that doesn't modify any other aspect of the protocol. The result of this is the new distribution that we glanced at earlier. And then importantly for security properties, there's a non-trivial resource scaling regression, and we'll look at it. So the namesake is this ancient Greek term for a tactician, or something that's fit for ordering or arranging, especially in war. And to harp back, prowess corresponds to, it's a Greek word for mellow or relax. So this is kind of the staking procedure for Tacticos, and it looks pretty much similar to the prowess staking procedure, except we've introduced this block spacing. or this slot interval, as we're calling it. So this delta parameter is always corresponding to the spacing between the blocks. And we're calling this a parent block. So parent block, parent slot. So it's the slot of a block minus its parent slot. And the staking procedure executes much identically as before, except now it depends on this parent slot. So it's conditioned on the previous blocks that the nodes have heard about most recently. Now, this difficulty curve is a generalization of this active slots coefficient, and it corresponds to a mapping of positive integers to values between 0 and 1. And the quality of independent aggregation holds, which eases the analysis and importantly makes sure that malicious adversaries get no advantage from breaking their resources into multiple accounts. So we introduce a specific parameterization of this difficulty curve, and we're calling it the snowplow curve because it intuitively kind of looks like a plow. And the idea is that we have these distinct domains. One can visualize many different functions or many different profiles, but this one is particularly advantageous because we're able to make analytic predictions with it. And these domains have functional effects on the chain growth and chain quality and the ability of an adversary to bias the network in their favor. So we have a slew of parameters here. So we're calling size, slot gap, gammas, forging window cutoff. You can think of the forging window as in gamma slots, you're pretty much assured to have a block, and that loops over and over again. And the idea of this recovery phase is if it ever falls out of that loop, the system will forge at some baseline rate of blocks and then recover and then come back into the forging window. So these two situations, these two distinct types of chain growth will oscillate back and forth. And then the difficulty amplitude parameters, FA and FB, kind of dictate how often and how ergodic that process is. So Markov chain representation admits an analytic solution, and it makes very accurate predictions about chain growth. And here we're using the stationary distribution in a state space corresponding to the counting states of this slot interval. And you can see it truncates at the forging window. So this corresponds to just the constant baseline forging rate. And then when it recovers, it goes back to the forging window. And the idea is that it will preferentially stay near the origin of the forging window. But you can also attune this. You can attune based on the slot gap. You can say there's not any blocks for 3, and then it starts forging again. So this transition matrix has a super diagonal form, and it's a process to find the analytic form of the stationary distribution, but we have these normalization factors and an analytic form for the stationary distribution. And here's what it looks like. And this is kind of similar to the security plot that we made for Proust previously. And you can see a difficulty curve, just some example parameters is shown. And here we're interested in analyzing the protocol in terms of the mixing time. So in this analysis, we're using Shannon's entropy to estimate the mixing time, and these are the components of the transition matrix. But we have guaranteed exponential convergence to the stationary distribution, just based on the fact that we're modeling with a Markov chain. And then to actually calculate these profiles, the probabilities of forks in the case of a malicious adversary trying to fork every opportunity, we use a random mapping representation to translate these transition probabilities into probability profiles with respect to the slot interval. So this nonlinear resource scaling is a manifestation of what this this kind of cyclic forging between forging window and then recovery phase. And you can see this Tacticos profile is kind of dominant. And then as you reduce the net active state, that is the resources that are contributing to a time to be constructed, it kind of spills into this recovery phase region. And the idea is that you have to tune the parameters, which we have a pretty complicated parameter space now to contend with, to a participation boundary. And we're targeting 50% all the time. But also an interesting feature of this is that you can tune this so that no matter what, no matter who's forging, 100% will be in the forging window, 100% of the extensions. So there's a really delicate balance and interplay of security properties here. We have to be careful. So, and just to show that this is the real deal, we actually implemented this. This is a full protocol. This is testnet results, and you can go peruse the simulation that I implemented to analyze this. So the full protocol is actually realized. All the cryptographic primitives are going, and there's kind of an experimental test bed for testing these properties. So to choose a correct parameterization is to choose something that gives the adversary no greater advantage. We don't want to go and do surgery and do damage, right? Do no harm. So we have this way of looking, and this is what I mean when I say non-linear resource scaling. So this is a normalized measure that influence. This is like the normalized forging rate. And we're kind of using a parity constraint. There's a lot to dive into, but this parameterization gives a really effective way of visualizing curve parameterizations that give the adversary a disadvantage in their domain of less than 50% participation. And as you can see, it's mostly dependent on this baseline eligibility. And if you choose different parameters, then this can oscillate, or we can choose a bad set of parameters and it'll actually give the adversary an advantage. But we're always symmetric and chain growth, so this 51% attack just kind of is a fixed point. So what is an adversary able to do with this new degree of freedom? We've given them the ability to basically grind on slots and parent slots now. Whereas before, in Proust, you can make an extension with any eligibility you had. It didn't depend on the parent you were forging on. And now it depends on the parent. So as you can see, we still got a ticker tape of events, but now they're not corresponding to eligibilities, they're not corresponding to blocks or ones or zeros. They're corresponding to nonces that satisfy a given bin in the threshold, a given value in the threshold. And here we're increasing this, assuming that it's an increasing threshold. So here it means it's satisfied up to 1, or a slot interval of 1. But here you would need a slot, a block in a slot 5 before to unlock this. So it's like you can have a nonce that actually satisfies part of the difficulty curve, but you need input to actually unlock it and get an eligibility, make an extension. So this one, right, we waited, there's a space of 3 here, so we can make an extension. But why 7? We can't make an extension on this, but we can on another alternative history. So there's alternative histories. They don't necessarily correspond to the abstraction of tines anymore. So we're calling them branches to delineate. So tines were blockchain forks. Now branches are these kind of what's to be understood as these alternate histories that correspond to the different conditional eligibilities on all these alternate histories. So how on earth do we make sense of it all? This is a lot of conditional eligibilities. This is a very complex space to reason about from a security and modeling standpoint. So it's almost as if we need some kind of way of automatically doing it. So in this automata model, we're representing these tines as branches. And the branches are now automata, and they're indexed by what slot that they arise in. And then they keep going. They just grind on parent slots and slots, and then probe each nonce going up in each slot. And then when an extension is available, they each replicate themselves and then start at that parent slot and start at that parent slot, so on and so forth. And as you can see, they can stack up where there's many, like when you have a low nonce that satisfies most of the difficulty or all of the difficulty curve, then they can all stagger and accumulate. But naturally, there's only one path here that corresponds to a maximum length time. So it makes sense to filter them and to just manage the number of branches because the complexity just diverges if you keep them all around. So to look at this picture closer, what we're doing is we're saying, here's a block, here's this parent slot and the length, that's the block number. And then the child branch just increments the block number and then adds this difficulty, the slot interval. And then we're going to think about things in terms of this axis of slot, parent slot. It's kind of the phase space diagram of this adversarial grinding attack. So then there's just these numerical pairs of numbers. And we have a set of rules. So we already went through how they're updated. They're testing these eligibilities with that staking threshold function. But we have a set of rules for filtering them. And that keeps around the most advantageous branches because we're looking for maximum length. We're trying to maximally extend a set of nonces. Duplicates are filtered, they're redundant. We can fork and make alternative histories if we're the adversary all the time. If you have an eligibility in a branch with a parent slot, all the other branches with a lesser block number are less viable. So you want to keep the maximum block number around. And then otherwise the other eligibilities in the same parent slot are just redundant. And additionally, we filter branches that have a lagging block number relative to a maximum block number. And then we parameterize that with the branch depth. So the branch depth of a branch depth of 1 would mean we only keep one branch around. So this one would be eliminated. But a branch depth of 2 means there'd be like 2 generations of branches kept around. So we'll quickly look at the situation for Prouse, and this is the branching diagram. This is the automata that are going up the ticker tape of nonces. And as you can see, the maximum number of extensions is 6. And the dots here are corresponding to the values of the nonces, normalized from 0 to 1. And I've highlighted the eligible nonces here. So they're uniquely predictable, but they're locally predictable. Prouse is a locally predictable protocol. And then the perps, the empty slots, are just nonces that didn't satisfy the threshold. So let's look at the branch depth and increase it. So the maximum number of extensions is still constant. No advantage is provided, but we end up with this kind of interesting spiderweb diagram. And keep going. So the branch depth is increasing. We're keeping more branches around. And now in 100 slots, we have every branch present. Now let's look at with local difficulty adjustments. And now think of the colors here mapped to the bins of the threshold. Now Ys that satisfy low, that satisfy a really hard threshold, they're kind of emboldened and highlighted in purple. And then nonces that satisfy the end of the forging window, that is like the highest point on that difficulty amplitude, they're red. And then the idea is that most of the time we'll be able to make extensions with these. Most of the time we may not be. And you can see there's lots of highlighted nonces that there's no extensions being made at all. So this is a property I'm calling pseudo predictability instead of like local predictability. If you have a given nonce, then there's no guarantee it's going to be eligible until you have the most recent blockchain history. So the local difficulty adjustments are highlighted on a rainbow axis here. And then let's increase the branch depth and see what happens. And let's increase it further and see what happens. Okay, we're still at a maximum number of 10 relative to the branch depth of 1. You can see there's a high degree of complexity here. And these eligibilities that bring it out of the recovery phase activate a lot of branches simultaneously. So there's a lot of activity that's being filtered there. And look at this on a movie, and it just procedurally goes. So there's a trend here in the terms of the block number that I want to point out. And I'm close to time. Okay, notice that. That's staggering. It starts to occur. So there's an interesting feature that sporadically happens sometimes. It means there's a block number with a parent slot that's greater with a higher block number. So it's that staggering that enables alternate extensions to sometimes overtake the honest activity of only making the earliest extension possible. So with a branch depth of 1, that corresponds to honest behavior, and then only the earliest extensions. So our security model can make analytic predictions for this, and this is the numerical data, the automata model. This is our analytic prediction. So this is a profile we're calling a Tacticos distribution. So depending on how we parameterize this snowplow curve, it changes the security properties and also changes the distribution of branching events. So this is distribution of extensions between different branch depths. And you can see it's reminiscent to this resource scaling profile. So these are newer results we haven't had a chance to look at yet. So this is a profile of chain growth showing how it scales at different participation. And then we found a set of parameters that actually provide an advantage at a branch depth of 2. So the honest activity isn't won't maximally extend necessarily. So we have to come up with a way of quantifying this. What is the advantage of this nothing extinct branching? And notice that the branch number, the total output number of branches, scales linearly with the branch depth. But the advantage stops at 2 and just plateaus. All right, so the advantage we're calling is this difference between the number of extensions that can be made with this adversarial activity and then the honest activity. Set the branch depth of 10 and set it to 1. Take the difference. And that's what we're going to look at. So this shows at 100% state, 50%, 40%, 25%. This is an unexpected trend, and we're not exactly sure how to analyze it. It just emerges from this automata model. But I think it has something to do with those different distributions that we just looked at. But importantly, at 50%, since we're trying to target for that participation threshold, we have no advantage over a domain of parameters. So, and keep in mind, this is also dependent on these other parameters. So we have different profiles and different advantage plots for all of these. So somewhat ideally, we have this ocean of no advantage, so we can actually choose secure difficulty curve parameters in this context, and we're at least as secure as the underlying protocol. So there's a lot of more analysis to be done. Additionally, we have a chain selection rule that we're proposing that would accumulate and promote the earlier slots. So these network divergences would be kind of mitigated by that. And also, we have this another idea of sampling at a deeper block. And what this might do is thwart the adversary's ability to bias the network by giving different parts of the network different parent slots, which has an important connotation. So that's the end of my talk. And thank you very much.
Thank you all. Well, it was a very interesting collection of talks here. I think now we're running a bit late, but hopefully we can now spend some time doing Q&A here. And I see we have a whole bunch of questions that have come in, but perhaps I might kick off here by just asking. Let me ask what I think are very straightforward questions. So I was curious to ask Peter Gacs just a real simple historical question, which was, you mentioned that Kadumov, the K of GKL, did computer simulations back in the ancient past. I'm curious, what kind of computer did he use? You're on mute, Peter. Muted. Oh, still muted. Oh, it's still muted here. Is there any? I'm not on mute, am I?
No, you're not on mute.
Oh, sorry, I have no idea about it, but it must have been a very small scale simulation. So as I said, as soon as in '83, I had a chance to simulate on a, like, I don't know, a few hundred cells. I have just put in a big island, and I saw that it would take forever for the island to disappear. And so, yeah.
I'm pleased that Sun workstation that we got at the 1983 conference was put to good use, and I'm impressed that you were able to just take a computer in the wild and simulate something useful on it.
Well, maybe it was not, maybe Tom Toffoli was there, and I taught him the rule, and he was the one who wrote the. I don't remember who wrote the program. It was a simple thing to do.
So I have another question for you, Peter, if I might, which is when you look at the tomb rule as compared to the symmetric neighborhood rules, what is your intuition for why these tomb type rules with asymmetric neighborhoods, and I looked at recently at some other asymmetric neighborhoods, basically all asymmetric neighborhoods seem to wipe out finite islands. What is the intuition behind that?
As a matter of fact, I think McKippenger has a paper showing what kind of symmetric or asymmetric rules works, but also in Andre Thom's big paper, he characterizes exactly which monotonic rules wipe out finite islands. It's actually it's a beautiful characterization in terms of finite dimensional Euclidean geometry. It boils down to just always having to have shrinking simplexes.
I'm sorry, having to, but what's the intuition behind why the asymmetric kind of neighborhoods work and the symmetric ones do not? Is it to do with breaking ties, or
no,
what's the?
No, as I say, whatever rule it is, it's not exactly the asymmetry. It's a kind of I say simply there is an exact characterization about exactly for which monotonic 0, 1 rules will erase finite islands and which ones won't. And again, the exact characterization is this, that really one can say that there always, the rule erases finite islands if and only if there is some kind of simplex, and it could be a degenerate one, which will shrink, possibly shrink and shift at the same time. So it doesn't have to be an asymmetric simplex, but I mean, well, it has to be, but you know, it's a simplex, so it's not a bar.
But so the thing I'm curious about, when we try to take these kinds of results to the graph case, to the case where we no longer have a grid, but we have a graph, what is the, I mean, the fact that these, you know, whatever you're calling them, these kind of simplex shapes on a grid work, and the more symmetrical shapes on a grid do not work. How should we think about generalizing that to graph?
I understand your question. This is actually a question that I started to think about just today, that if you have an arbitrary graph, however simple, right? Somehow, yeah, if you have a problem. So if you don't have some kind of local senses or local directions that correspond to some kind of global senses of directions, right? Then I don't know whether you could formulate anything that would guarantee this sort of shrinking all the time. So I wonder, so indeed but there might be some interesting generalization of these tone conditions for other not so regular structures, but I don't know. It's a tough question. Right immediately I don't have any good answer. Somehow, you know, as a minimum, probably the edges need to have some labels that correspond to directions, but even, you know, how those directions correspond to global directions and what those global directions would mean even in an arbitrary graph. So I don't know. As I say,
seems like a good problem, right?
It seems like a good, but you know, good but not so well-defined problem. So it is you know, you need to be kind of creative to try to come up with an answer.
So now I'm curious to ask Eric, actually, whether he knows anything about the answer to that question. That was sort of the first thing I was going to ask Eric. And the second thing I was going to ask Eric was sort of your kind of computational complexity results. I'm curious whether there are applications of those in the wild that can tell us things about the minimum consensus times for some of these kind of simple cellular automaton rules and so on.
You know, you listen me? It's okay?
Yes, we hear you.
Okay. So, you know, the majority functions in regular grids, you have a lot of alliances, so it's difficult. There are not too much configuration that's going like that in parallel or synchronously to the consensus. So I was thinking about today, so maybe is we take the majority rule over, say, an arbitrary graph and an undirected graph. And we change the topology every 2 times for another graph related with neighborhood. I think that in this case, maybe we may do something about consensus, theoretically. I was thinking today, okay, that's new for me, okay? So say, you take the iteration, first you take people, like you, the first example with green and yellow people in your slices. And after that, you put some graph there, relationship within them. You iterate it and you change it 2 times, over and over. I think we have, it's not sure, but we have a possibility to prove something about consensus there. It's not the same that to change only the neighborhood. For the neighborhood, it's so local, so you may change 2 or 3 or change the time sometime. But maybe that is a way to try to go to the consensus with the simple majority. Another thing that is very important is a kind of thermodynamical effect when you take the risky strategy for ties. It's kind of, you are trapped in a local minima with the prudent iteration. When you change, if there are a tie, you go to the other side, it's a kind of, you are jumping some local minima in some way. So maybe there you may go to a consensus, but we have to study. So my idea is to try to work with the general graph and to change a little topology from iteration to iteration. If you control a little that, maybe we may have some mathematical result from complexity about that. It's possible, I think, but it's new for me. I'm thinking today, it's new. I'm beginning to think after your talk, anyway.
No, it's interesting. Unfortunately, my main computer crashed, so I'm probably sounding. It's I have to figure out how to reboot this, but that's very, very unusual and surprising for me. Interesting. I mean, I'm curious if you were to pick random circuits, for example, for your constructions and so on. To what extent, when you have a random arrangement of your kinds of majority rules, can you say something about sort of the computational complexity of the typical computation with a random circuit?
A little, because maybe you know the article, this classical article from Chris Moore, where he studied the majority and the spin glasses problem.
Yes.
Say one side changes with probability. So his prediction problem there is try to determine if one side will be changed in the future with a positive probability, not zero probability. This problem, we prove it that is easy to solve. Okay, so for the kind of a spin glass iteration we prove it that we may has a faster algorithm than the iteration step by step. We may find a trajectory very quickly, okay, in this case. But for another approaches with probabilities, we didn't work anyway. That is the only one for spin glass structure. So you are taking people one by one in an arbitrary order and change it, this one. And for that, we know that in the 2-dimensional grid, the problem was open until us, before us. And we closed it because we have a strategy, which is a very nice algorithm in parallel to find a trajectory. Very easy in log of this log n to the 2, I think, where n is the size of the network.
Interesting. Let's see. Maybe somebody else can. I think there were several other questions that I had, but maybe since I'm in a challenged computer state, which is very unusual for me, maybe somebody else can relay some of the questions that.
So maybe you should use blockchain technology.
Yes. Well, right. This is.
I'll paste a few into the Zoom chat, Stephen, so it's easy.
Yeah. Okay.
First one is for Emin, if you don't mind.
Well, here, let me. Actually, I'm curious to ask something there. Let's see. I can connect with a different computer here. I'm curious to understand the sort of bigger picture of the various things that have been being talked about today with Avalanche and NKN and IOTA and so on. I mean, it seems like there is a wonderful and very interesting convergence here between sort of well, let me try to understand a little bit more about this Avalanche approach. I mean, to what extent is what you're doing a kind of graph cellular automaton where you're picking essentially random neighbors for the cellular automaton? Is that at each step, and then you're running a series of iterations on that, and then that as I understand it, that's sort of the minimal version of your protocol, where it's a simple majority or something, and then as you get to these higher levels beyond slush to snowflakes to other things, you're being more sophisticated about kind of the internal state of the oops. Okay, I'm gonna. Sorry, just a second. Let's see. Okay, hopefully I'm back here. Am I back?
Yes.
Okay, sorry about that. All right, let's see. No, I was asking, as you go to kind of higher levels of this protocol, that you essentially have more state rather than just something like a simple majority rule. Is that a correct basic understanding that you're dealing with?
That's exactly right. Slush has no state, and the snowflake, snowball, and avalanche all have success. Well, snowflake and snowball have more state, and avalanche has a different data structure that's building underneath.
So what I mean, but when you're in these approaches, as I understand it, you're picking at random the things that you're going to use as the neighbors. Correct. For each step in the cellular automaton evolution.
They're randomly sampled, exactly. The analysis is all for randomly sampling your neighbor set.
And I'm curious, I mean, in the case of what you're describing as Avalanche, you say there's a more complicated data structure for the actual sort of automata at each node have a more sophisticated memory of the past. Is that kind of the point, or is it a different kind of?
No. In Avalanche, so at the very last step, when we generalize Snowball into the Avalanche protocol, what we are doing is, instead of making a single decree, a single decision, we're building a DAG, and on the DAG, we are piggybacking multiple decrees together. So if you have a portion of a graph where vertices A, B, and C are dependent on each other, they have a parent relationship, then a vote for C implicitly votes for all of its parents. So essentially what you're trying to do by generalizing to a DAG or by going to a DAG is adding the ability to vote on multiple vertices at a time, all at once with a single vote. So it's a strict performance improvement for us. it's not actually changing the underlying dynamics, the metastable approach, the consensus that's happening underneath. So the confidence, etc., it all works the same way.
But so what you're doing, let's see, when you say there's a vote, that you're not setting one single node as now being in its new state. You're also setting various previous nodes that depends on, or what? Is the other way around? And then I'm going to ask what the correspondence between that and the DAG that shows up in the IOTA protocol is.
Okay, so let me talk about that. But maybe there might be some confusion between the graph of nodes that communicate and the data structure that's being built. Those two things are distinct.
So, I understand. Which is the same with IOTA. It's the same with causal graphs in our physics project.
Correct.
I think just for once, perhaps everybody is discovering the same thing, but we'll see.
Correct. So let's see. So what was the second question?
Well, so I'm trying to understand your DAG and how your DAG relates to things like the IOTA DAG, which is a separate. I'm not talking about the IOTA tangle. I'm talking about well, maybe I am talking about that. No, I'm getting myself confused.
No.
Maybe William can jump in here. Go ahead.
There are very few differences between the IOTA protocol and the Avalanche protocol. IOTA's latest protocol came after the Avalanche work. And as far as I can understand it, at least from my point of view, I believe what they did is they took the Avalanche work and they made one of the parameters that's analyzed statically in the Avalanche protocol. They suggest that parameter be varied. Otherwise, it's essentially a derived work off of the Avalanche protocol. That's at least my and my team's consensus opinion after carefully looking at IOTA. So
and you have to be careful what you mean by consensus when you're in a discussion like this.
Correct. It's a whole bunch of us read that paper very carefully, and we decided, oh, they took the Avalanche work, and instead of saying that this variable should just be set to something, they say that this should be varied. So I wish them much success, but that's just. So IOTA is essentially copying Avalanche is what we have decided is going on.
But so let me understand what it is that then, whether it's the same or different, but just what the actual idea is.
Okay.
What is the idea?
The idea behind voting.
But behind this DAG thing that you're describing, which I just hadn't understood yet, and maybe it would help other people also.
All right. So in a blockchain, you need to have a bunch of transactions that you're going to accept or reject, and you can do this on a transaction by transaction basis. You can do it on an individual basis. But if you do that, that's going to be expensive. It's going to be 17 rounds of voting on every on every conflict set. So out of every conflict set, you will pick only one transaction. So the idea in building a DAG and creating a DAG-based data structure is that as you are voting on a vertex of that DAG, what you can do is you can implicitly vote on a whole series of vertices and therefore resolve a whole series of decisions simply by making a decision at the very edge of the graph. So suppose, for example, I have Alice pays Bob and Alice pays Charlie. I need to pick one of them. And I also have David pays Eve and David pays Frank. So these are two different decisions. And if I were to go into this blindly and naively, I would have to run 17 iterations on the first conflict set and 17 iterations on the second conflict set. But if I were to create a DAG where David pays Eve is dependent on Alice pays Bob, then a vote for David pays Eve is also a vote for Alice pays Bob. So I can run 17 iterations on David pays Frank and implicitly decide two vertices of the graph, as opposed to having to separately decide those two conflict sets.
So I mean, at a naive level, if I was just doing standard blockchain, then what you would be saying is, don't vote on every single block. Wait until you've gone a few blocks in the future, and if you accept a block, multiple blocks in the future, then that is implicitly accepting the intermediate blocks because they're chained together. Is that correct?
Exactly right. Exactly right. That's one of the nice things about blockchains is that they intertwine the fates of blocks, and by making a decision towards the tail, you end up resolving a whole series at once. You amortize the decision's cost over a larger number of things that need to be resolved.
So I was also interested, by your comments about sort of the merger of different fields, because I know, computer science departments have often stopped teaching calculus because it's irrelevant. And then machine learning comes along. And now it seems that the analysis of these distributed algorithms is also requiring those same kinds of methods. But I am curious in the work that you're doing, I just, because I've tried to trace the history of these kinds of things, what's the sort of intellectual lineage? I mean, is this coming out of out of things like the Lamport? I mean, you mentioned Lamport, Liskov, and so on. Is that what's the intellectual lineage of the kind of this?
So intellectual lineage of Avalanche and related protocols, that family, skips over most of the work on classical consensus protocols, because that's very discrete and it's a very different approach. And the techniques used go back to Markovian analysis. And we're looking at mixing times. We're looking at a bunch of things that are computable from Markovian analysis. We're not doing discrete math in any. Well,
see, I mean, the problem, the Markovian analysis, a skeptic would say Markovian analysis is what caused all the epidemiology of the pandemic to be gotten wrong, because basically what happened is these SIR models are essentially a mean field Markovian type analysis, where they sort of assume that everybody is randomly meeting everybody else in the epidemic, so to speak. And I think that's one of the challenges here, is that the pure Markovian analysis, which is kind of the physicists, what physicists would call mean field theory, what probabilists would call Markov chains and so on. And by the way, that's also in physicists who do statistical mechanics would talk about molecular chaos assumptions, things like this. The difficulty is always, once there has been one round of something which is not correlated, the very fact that the things have been taken and interact causes there to be correlation. So it becomes non-trivial to do the analysis. What you think of as being Markovian doesn't end up being Markovian when you actually use the results. So I'm curious whether that's been something that's come up in this.
Absolutely, it came up in the early days, and I think if you look at some related work, you will find some concern around this topic. So it's actually very simple in computer systems. However, the main assumption made is that every node can speak to every other node. And if you can entertain that, if you can make that happen mechanistically at the network level, then assuming that there's random interactions is absolutely trivial. And that's a very easy thing to do. Our system has been in operation for 7 months now, and it's at the very lowest level. It provides incentives for everybody to open their port. If you don't open your port, you do not get the kinds of rewards that you would be otherwise entitled to. So it's very, very simple to achieve that. And once you have every node able to send a packet to every other node, which is a core function of the internet, then these elegant results that pop out of the Avalanche protocol are accessible to you. Now, if you don't have that, then you'd have to go and resort to more complicated analysis techniques, because then you can have islands and you can have lack of connectivity causing bottlenecks in information propagation. And people situated at critical junction points in the network might be able to interfere with the protocol and have undue strength in the network. So those are all problems, as you allude to, and you just have to make sure that what you're building provides the right incentives. And in computer networks, it's trivial for any node to send a message to any other node. So this is actually very easily surmountable.
Well, I mean, in a sense, what you're saying is your analysis assumes random mixing, which in the case of computer nodes is something you can simply put in. You can just say, pick a random place to get to. Whereas in the case of epidemiology, people don't get to pick the random person that they're going to interact with. So you're saying and I think William was mentioning in the IOTA situation that they're also, I mean, that there is a need in that case, and I would think in your case as well, to have or perhaps not. I mean, you can pick the random nodes. Each node can pick its random neighbors.
Yes.
And I think in the case of the NKN protocol, maybe Yilun can say something about what the picking of the neighbors is in that case. I think it's maybe Yilun can speak to that.
Oh yeah, sure. So basically, we from the Okay, so when we do the theoretical analysis and simulations, we kind of also assume it's random topology, but it's kind of static. So instead of picking a new random set of neighbors per steps, we kind of pick proper random neighbors prior to each consensus round and stick to that topology before doing the consensus. But then there's like a whole bunch of things of how to do this correctly and in a verifiable way and in a secure way. But that's kind of not part of the consensus protocol, so I didn't cover this part. But in practice, we kind of need to do it to make sure that it's well against like Sybil attack, so that a malicious attacker cannot just like, let's say, send a billion of like a false identity into the network. So whatever random node you pick, with high probability, you will pick like a malicious one. But that's kind of, because that's kind of a separate engineering or system design thing that we need to do outside the system. But that's kind of not the part of the consensus itself.
As a practical matter, when you're picking random neighbors, I mean, how does it know what neighbors are available to be picked from the kind of the random, when you pick the random ball out of the bag, so to speak? How does it know what, this is kind of a question, I suppose, for the avalanche question, you know, how do you know which ball to pick? How do you know what the set of balls is that you can pick from?
That's a very good question. It comes at, it hits at the heart of Sybil control, and every consensus protocol needs to be coupled with some Sybil control mechanism to make sure that an attacker does not have undue influence into your decision-making process. A protocol like Avalanche is generic. It can be used with any mechanism you like. So the simplest one, of course, is proof of authority. So you and I, you know, the system designers, we determine the set of participants, and that's static, let's say, and we just go with that. That's the simplest approach one could take. Second approach one could take is we couple Avalanche with proof of work. This would be not very good from my point of view, but one could do that. So to gain a ticket to be selected, you have to constantly solve a proof of work puzzle. So that's also possible. But the actual preferred embodiment, and the one that we actually use in the Avalanche system, is we use staking. So there is a linear chain on which you post your stake. And to have a say in the system, you have to post up a minimum bond. And so that naturally limits the number of tickets that anyone can purchase. So because they're limited, there's a limited resource again, and this time it's capital. It's not hash rate, it's not names, it's not individuals, but it is just access to capital. That's an open playing field. Anybody can play that game, and a very modest amount will allow anybody to enter the network and act as a validator.
Yilun, maybe you want to say something about the Sybil attack situation for NKN.
Oh, very similar. So I think it's kind of the mostly well-used forms are, just like Emin said, either proof of work or like proof of stake. So we are kind of doing the both to get like a proper registered ID on NKN system. You kind of need to solve like a mini proof of work puzzle. It's very simple, and also you have to stake some kind of minimum amount of NKN into the system in order to get an ID. And also we kind of use you can think of it like the verifiable delay function to get like a true random ID that the anyone cannot predict or control before he actually get the ID. So to make sure that he cannot pick the place he wants on the address space. Yeah.
But Yilun, may I ask something? So
yeah, sure.
If it's the case that, so is it the case that a participant need only solve that proof of work puzzle just once?
He needs to, yes, but he has to do both. He has to solve the puzzle once, and he has to stake the minimum amount of like token in order to get the ID.
I see, but couldn't he then grind through the whole space?
No, so it's like, it's kind of like a dynamic. It's kind of like a mini proof of mini Bitcoin mining problem. For each ID he generates, he kind of has to solve a new problem.
Right. I understand that, but since it's not continuous, so the limiting resource is not CPU. That you're just slowing him down a little bit once, but because you're not constantly forcing him to constantly solve the puzzles, it's not exactly like Bitcoin. So what one could do is come to corner a portion of the space by just going through a whole bunch of IDs. I try to solve it. I work on the problem for some time. If I don't like where I ended up, I solve it again until I end up where I want to be, until I cover the attacked node.
Oh, that's a very good question. So actually we have several ways to do that. First of all, for each ID he generates, he kind of have to stake beforehand. So basically he generates a transaction. Before he generates transaction, he has to attach a proof that he has already done the hash problem. And then at the time he submits that transaction, amount of token is deducted from his account. So that's kind of the token he has to pay just for one trial. And at that time, he cannot predict what ID he gets. He actually first has to submit that transaction to the chain. And after some block delay, there is a way to compute his ID after several block delay. Well, let's just say it's a verifiable delay function. Then after like a few blocks delayed, since he submitted that transaction, the ID is generated. And that ID depends on the transaction hash is submitted. It depends on like the block hash is submitted. It depends on everyone who produced block during that delay function. And after that delay, he get that ID. So that means in order to get a random ID into the system, he not only needs to like pay some CPU power, he also needs to pay some like financial token into it. And after that, he get a random ID. If he don't like it, well, he can't get the money back.
But so when you're doing that, you said this is your scheme for generating the random ID is based, you said, on the series of blocks that were made, but you have a very decentralized, you have a very distributed system. So how does when a new node is coming online, how much of the network has to be consulted to accept or to reject the new node? I mean, in other words, if you're getting the ID from, how much of the network has to be involved in determining the new ID?
We actually don't have a way to reject the block. As long as someone are willing to pay the money, he will get the ID. It's just a matter of how that ID is computed. So basically, each block has some sort of like random beacon computed using like verifiable random function. And it's also linked to the previous random beacon in the previous blocks. So it's kind of like you have to precisely predict who is the next block proposer for a long time in order to predict what is an ID that I will get, which is basically an impossible thing.
No, it's nice. So let's see, we had a question on a live stream here, I think from iDude, saying it's not clear to me how much topology is stable in these protocols, NK and Avalanche and so on. Is there a stable notion of distance, this person is asking, between two nodes or addresses in these networks? Is there, I mean, do you care what the notion of distance is? I'm not sure. No. I'm not sure anybody cares what the notion of distance is. Absolutely. In other words, all you need to know is who are your neighbors. You don't need to know what the absolute distance, in a sense, to a node is.
Exactly. So in the current implementation of Avalanche, it's just a fully connected mesh, essentially, a fully connected graph. And so anybody is able to select anybody else from the lineup of other nodes. And so there is no notion of distance, nor do you need one.
And then can you also expect to get from any node to any other node?
Yeah. Yes, I would say for the consensus, yes. Say we don't care about distance, but the distance is important in order to form proper peer-to-peer network, because we have like 100,000 nodes in the network. There is no way for us to get a very dense connectivity. So we are actually using the DHT we are actually using the DHT topology for those nodes to talk to each other. So when a node wants to talk to another node, they kind of use the backbone DHT topology to find to talk to the other node for the first time, and then they can establish a connection and do whatever they want directly.
But Yilun, DHTs are a topic that's been well studied, and they are very, very fragile. So yes, an attacker can do an eclipse attack on a DHT much easier than they can do an attack. They would be able to do an attack on Avalanche, let's say. In fact, DHT attacks are
That's true.
fairly easy.
Yeah, that's
You're not
that's
using the
why we
DHT
kind
for
of
consensus, right? You're using the DHT only for routing.
But I think it's talking about the DHT attacking in the peer-to-peer network layer, not in the consensus layer. That's why we are kind of using a very unusual DHT. We are using the core DHT, not Kademlia. So in core DHT, so in Kademlia you can kind of doing the Eclipse attack by kind of filling into victims like bucket, right? But in core DHT, as long as their ID is verifiable and random, the topology is also verifiable and random. So unless there is a way for attacker to pick up what kind of ID he wants on the ring, he can kind of probably do the Eclipse attack. But otherwise, there's no way for him to perform such attack. Yeah. So that's why we kind of spend a lot of effort trying to make sure that everyone has a random verifiable ID on the ring, not just the one he can pick.
Let's see. Maybe there are. I see there are some other questions here, but anybody who's in the sort of local room here, anybody want to raise questions, make comments?
I see some in the chat. I think so. One of the questions for me is: do you make any operation between the previous values to do the entanglement? I think the question here is who can create a DAG? I think I can speak for all of us, I believe. So anyone should be able to create a new vertex for the DAG. Anyone should be able to create that entanglement. So any node in the Avalanche network can create a new node. This is, I believe, true for NKN and probably should be true for IOTA's, not current IOTA, which has a centralized component that creates this, but IOTA's new version, the one that's based on the Avalanche protocol, it should have the same property.
No, my question actually was related to, you said that you keep the voting and it sends many votings at the same time. So it's kind of like you use the word entanglement also. So my question was, how do you make this entanglement? It's like kind of like a parity. If the vote is one or it's a binary decision, you just send the parity of that.
No, it's based on the topology of the DAG underneath. So if there are vertices to be decided, which every vertex contains a transaction. So a transaction simply is think of it as a payment, Alice pays Bob, and it's placed into a vertex. And when you are creating a vertex, you name his parents. So there's a particular topology that is formed. And when you are voting on the edge of the graph, it inherently votes for all the ancestors of the vertex on which you cast your vote.
Okay, yeah, thank you.
I hope that's clear.
Let's see, there's a question on our live stream here, which I'm not sure I fully understand, from Ham. How resilient are leaderless consensus algorithms such as Avalanche to MEV and Flashbot exploits, which I don't know what they are. I can guess what they are. Can consensus speed be increased by selecting which neighbors are queried in each round instead of using the client's default random node selection for each round?
Fantastic question. So just to make sure everybody's on the same page, let me define what's going on there. And this is actually really interesting. And if I have a moment, I'll tell you guys a very funny story. So the MEV is referring to minor extractable value. And minor extractable value in systems like Ethereum, where there is a chain, there's inherently a leader. The node, the miner that mines a block is the leader. He's determining what happened in the preceding block period. So he gets to determine the exact order of transactions in the block. In doing so, he's in a unique position. He can add his own transactions anywhere he likes. So if there is a transaction out there where somebody is buying something, well, the miner can come in right before that transaction, buy it from someone else and sell it to the next person, and therefore eat up the value. So if I come in and I want to buy something with a market order, and then you, Dr. Wolfram, want to jump in, you can buy it from the lowest seller, bump the price, eat up the difference, and make a tidy sum. So that's MEV, and it's been well characterized by a Cornell graduate student named Phil Dion and his colleagues. And It's a fantastic idea, and I'll tell you all about how this work came to be. So Phil Diane came to. So as I said, I'm a professor at Cornell University, and we run an initiative there for smart contracts, cryptocurrencies and smart contracts. And he said, "Hey, I have an idea for a cool research project. I want to come up with a way to buy up space on the blockchain and trade it in." It turns out that on Ethereum you can create a contract. And then when you suicide the contract, when you kill it and delete it, the system gives you back some of the gas you used to create it. So if gas costs on Ethereum are very low right now, Phil could come in, create some contracts. And when gas costs are very, very high, he can suicide his contracts and get his gas back. So this way he can, he wouldn't be able to afford very high gas fees. But if he does this, then he can sort of time trade. He could allocate the gas early and then unallocate.
You can buy futures contracts on gas.
That's exactly right. So he created something called gas token, and but to do that, he needs some money. So he came to us, the professors, and said, "Hey, I would like to do this as an experiment. Can I do this?" And so we said, "Okay, that's kind of odd. I don't know. We don't know how we're going to account for it. As you can imagine, Cornell's accounting systems are made for US dollars. If you push, they can handle euros, but they clearly cannot handle gas tokens." So we said, "How much do you need for research?" He said $30,000 or so is going to allow me to do some experiments. So we gave him $30,000, which is, we're pushing the boundary of what Cornell can do. And also for listeners, professors' budgets follow us the following trajectory. You get a grant and they go down over time. And then you get another grant and they go down over time. So Phil came by about a month later and said, we said, "How's it going? How's your research?" It's like, "Well, we have a problem." "What's your problem?" "Well, I created the gas tokens." And so that part was easy. And then I started playing around with minor extractable value, what one could do if one could sandwich transactions in between other people who are interacting with these decentralized exchanges. And so what's the problem? This sounds like really exciting stuff. We should characterize this. And he said, the problem is that one could actually make, or we are making about $3,000 per day. So you could imagine that this creates a huge accounting issue. So Cornell is not equipped for professors' budgets that actually grow on their own. And it, of course, presented quite the challenge. So long-winded story, apologize for it, but I wanted to add some color. We decided to solve this dilemma by giving the coins he made, the money he made, back to the people and so forth, so that there are no issues in the end. But okay, so minor extractable value in all of these protocols is very, very interesting and important. When there is no leader, there is not a person in a natural position to exploit their leadership position in the network. But the exact amount of minor extract or validator extractable value in Avalanche has not been characterized formally. So I'm not claiming it's zero. It definitely is not zero. And I don't know how high it is. I don't think it's as high as what it is in proof of work systems, but that's open research. It's a very exciting area.
Does William or Yilun want to comment on this in their systems?
Yeah, I can talk a little bit about this for NKN. Yeah, so NKN is a blockchain-based system, not a DAG-based. So indeed, similar to Bitcoin or Ethereum, like it could potentially have some like minor advantage. But well, yeah, we don't know, like, because we kind of the role of NKN is mostly for data transmission. So the on-chain like value part is not like as much as Ethereum or Bitcoin. So that advantage is kind of minimal. And also we kind of choose blockchain versus like DAG mostly for economic reason, because for like a leader-based system, the leader can get some additional money reward, right? That could be not ideal for some case, but for NKN, this is kind of very important in the early stage, because the reason we can grow to 100,000 nodes is because even there's no one paying for the system, paying for the relays, the system reward or like the mining reward could incentivize like miners to jump into the system, contribute to more nodes, and grow the network when the users are still have a low traffic. This is kind of extremely important for
for us in the early stage, and that's kind of the only reason why we can grow to this size without much user compared to miners.
I'm not sure if William is still on here, but
I'm here. Well, we don't have miners, so we don't have this problem. So because people are supposed to put on their own transactions and such, and so we're not having relying on access through these centralized players.
No, William, even when you don't have miners, you still have this problem.
Yeah, I think when you add things to your tangle, don't you have the person who actually gets to add it? Don't they have this potential advantage? Or maybe I'm confused.
Well, if you're adding the transaction, you don't have the ability to order the, you can just you can only attach the transaction to the available tips that you have.
So that's good, William. And so while I'm observing you try to add something, I can add my own somewhere, right?
Do you know that somebody's trying to add something? In other words, when somebody is trying to add to one tip, I think it's independent, isn't it? I mean, the validity of addition to tips depends on validating previous transactions, not some central mechanism. Is that right, William?
Exactly.
So, and what is, just for my and other people's perhaps education, what is a flashbot? You explained what an MEV is, but what is a flashbot?
Flashbot is the kind of a flashbot is a piece of software that takes advantage of tricks of the kind that we talked about. So miner extractable value or validator extractable value to sandwich transactions and make money. So they will end up putting their transactions in the middle, in between other people's, to make money. The thing that our student Phil Dion was doing is called a flashbot. It's a send off to the Flash Boys. If some people read about the financiers who were doing high frequency trading, and flashbots come in and they squeeze their transactions ahead of other people's legitimate transactions. And just to wrap everything up, I think certainly IOTA, I mean, you can call, whatever your, when people say miners, they're talking about participating nodes in the network. For proof of stake systems, there is no such thing as a miner. When I say, MEV for Avalanche, Avalanche does not have miners either. It has validators. And certainly that's the validator extractable value is something that needs to be characterized. And if any group is claiming that it's zero for them, they don't understand their own system.
If I could,
another question. Sorry,
make a little point here. The history is that Jim Simon at Berkeley years ago made a lot more money than 3,000 a day out of Renaissance technologies, if you recall. Yes. So I encourage your student to expand the horizons a bit.
Yes. No, that the student was doing a very, very tiny study. Our goal was not to make money. And we tried to dissuade him from that because it suddenly gets into dicey territory. So the amount of money that other people make today is actually pretty significant through sandwiching. If anybody has heard of Uniswap on Ethereum, almost every sizable transaction with Uniswap will be subject to flashbots on Ethereum today. So there are people doing this at industrial scales. Phil Dion was the very first person and also the very first author to write a paper on characterizing MEV. So for proof of work systems back then.
So another question from Ham here was about, can consensus speed be increased by selecting which neighbors are queried in each round? I think in your model, as I understand it, and I think this is also true for NKN, it's assumed that there's no transmission delay time. Every node can be reached in the same time. So it doesn't make any difference whether it may not be true in practice, but I think the question being asked here is, if there's presumably different ping times, different latencies for different nodes, and to what extent, you potentially end up with a less secure system if you say, I'm only going to pick nodes which have low latency to be the ones that I'm going to use to make my my local consensus. So I'm curious what the trade-off is between kind of picking, the nodes of low latency and picking sort of all possible nodes at random and so on.
Yeah, so that's very insightful. There is a trade-off. And the trade-off is between better performance and analyzability. So it's a lot easier to analyze systems where the behavior is uniform. And the moment you start adding in optimizations that are incredibly sensible, like this one, you end up giving up the nice analysis results. And so if there are interested parties that can come in and extend the avalanche results with these optimizations, this is such a fertile field. So it really opens up a whole new family of protocols. There are many, many, many different things to do. And we know, for example, that the adversaries that are assumed in the avalanche paper is not as strong as a real adversary. The adversaries assumed in the paper are too strong. Real adversaries aren't that bad. And so there are many other things that one could do to build realistic systems that are faster, but then you need to have the math to be able to analyze it, and the math in the avalanche paper is already fairly advanced. So I encourage everybody to take a look. We need to make more progress here.
So Yilun, I think you were going to make some comment about latencies of nodes and
yes. So I would say for consensus, never only pick up nodes with low latency. If I remember correctly, someone has done like some embedding analysis and showing that if the nodes can be basically embedded into a 4 or 5 dimensional space and the latency can be predicted pretty precisely by using the distance in that embedded space. That means if we are picking up only the nodes with low latency, we're essentially only using like a 4 or 5 dimensional space, and you are picking like a neighbor with within the distance. And as we have seen in my talk, that low dimensionality could cause many trouble in terms of both like consistency and the convergence time. So for consensus, the dimensionality is a very important property. And as we have seen that random topology kind of has the best lowest diameter and best convergence. So the random topology is definitely what we want to choose if possible, regardless of anything like if the latency is like low enough, or if you like the node IP or not, or something like that.
But
so,
yeah, I mean, I think one of the things that we've heard today between Peter Gacs and Eric and other people who've been talking about kind of the, how to get good consensus, even in something like a one-dimensional cellular automaton that has the most, the most restricted kind of notion of neighborness. And the thing that's interesting is it is still possible to get robust consensus, even in a system that has sort of pathetically restricted neighborhoods. And I'm curious, I understand, I think it's correct that the safest thing to do is this kind of, unbiased random topology kind of approach. But I'm curious, in optimizing that, I'm curious to what extent it's possible to use these results from that work even in the case of like a one-dimensional cellular automaton to still get consensus, even in the presence of at least noise. I don't know to what extent, and maybe Peter could comment on this. Maybe I can ask the question of Peter in particular. What happens when you have Byzantine attacks on, for example, your cellular automaton that withstands a certain level of noise? Do you know does your noise, are Byzantine attacks included in your notion of surviving noise?
No, it's very important. It's very important that the noise is assumed. It's very important that the noise is assumed random, not Byzantine. So not okay. Adversarial. I think for adversarial noise, one needs much stronger assumption about with a cellular automaton. One needs much stronger assumptions about what is allowed. So let me give, instead of talking about this one-dimensional cellular automaton, let's just look at the Thom rule again, right? And so assume that look at the Thom rule in a finite or just on the finite torus, right? Now, okay, so of course, random noise basically if you have an n times n size torus, right? In random noise in 1 second, or there appear already order of n squared, bad spots, but nevertheless the Thom rule can deal with that, right? On the other hand, an adversary could just add n spots, which form a belt around the torus, and that becomes non-destructible by the Thom rule. So it is, so instead of n squared, in one step you only need to add n. The adversary only need to add n noise of size n, but it has to be has to have the right structure, right? It is a connected belt around the torus, and then you killed it.
So I'm curious, talking about Erik's kinds of results.
Yeah, so this is, but by the way, so this is typical, right? So I think in general, right? So adversarial noise has to be probably, so like Byzantine, it has to be restricted to only a low power of the size of the system instead of a constant factor, right? So because essentially with it, for example, on the plane, right, it is able to surround completely an area and already prevent its communication from the rest, right? So you cannot have, so in order for a cellular automaton to work, you would have to prohibit even this.
So I'm curious about computational complexity kinds of results around this, and I'm curious how it relates to some of Erik's work, because I mean, basically what you're saying is, it's like playing a game of Go or something. You can, which I don't know how to play very well, but you surround the stones and then the thing is toast, so to speak. And you're saying that would be a way, an attack like that would succeed in sort of breaking the consensus thing. But what I'm curious about is whether some of what Erik is doing with computational complexity theory would tell one something about, given a configuration, how complicated is it to determine what thing you need to do to be the adversary, so to speak. What is the computational complexity needed for the adversary? And could you potentially get a result that an adversary, what would be really cool is maybe even beyond p-completeness to get some kind of result about the, some lower bound on the computational complexity necessary to make a certain kind of attack on one of these consensus systems.
Well, I let Erik answer with that. Just let me in a moment. Just let me tell you that on a torus, actually, there is an exact result saying the following: that the Thom rule will erase an island, a set of ones, if and only if it is topologic. Well, in a certain graph, it is topologically equivalent, homotopically equivalent to 0. In other words, it can be shrunk. It is not. It doesn't contain a cycle around. But
is that true for graphs as well as you're saying? Is that just on an array, or is that on a two-move?
Well, it is the grid plus little diagonal edges across the squares. So that's it. But it is this is just about the Thom rule. But Erik probably has more precise results about other cellular automata. I don't know.
It seems a nice problem. I think that we have to change the prediction problem to something related with attack. For instance, if in the network we define some theoretical malicious island like the minimum, at least to take the majority, take the minority. So what is the complexity if you take some specific guys in a regular network that it takes the minority? It's going to the consensus, always hope to compute that and so on. That's very nice problem. I don't know if it's easy. Of course, in one dimension, maybe it's easy, but in two-dimensional cellular automata with the majority is difficult.
Oh, let me give you a more precise open problem. Also, this is also from Thom. consider monotonic rules, but not with 2 states, but with 3 states, 0, 1, and 2. And the question is, which of these rules erase finite islands of non-zeros and which ones don't? This question is actually unknown, so maybe it is even undecidable. We don't know the answer.
So I mean, just to characterize for other people who might be interested, I mean, the comment that Peter just made about maybe it's undecidable, the issue would be in a proof of this, you could say, okay, we can explicitly show that an island of this size can be erased, but there's no, we can't know for all possible islands. One's trying to produce a proof for all possible islands. And that's kind of where the infinite case of that might be undecidable. It might not be possible to show that for all possible islands of arbitrarily large size, it can be erased.
Yeah,
the finite version of that might be a computational complexity kind of result.
Yeah, for example, Tom has an example of such a rule which erases all finite islands, but only in exponential time.
And is that a provable lower bound that it erases that? Because that would be an interesting from a computational complexity point of view.
It's a simple explicit example.
I see. But I mean, because that's the finite version of that would be, this. I'm curious about sort of the computational complexity of making an attack on one of these consensus algorithms, and it's that's something that
this is a very specific question about monotonic fields.
Right.
Okay. Sorry.
I'm curious now from Emin that in the world of in the world of kinds of analyses of things like your protocol, are people getting computational complexity type results, or is that something that is out? Is that a different silo of the world of theoretical computer science, so to speak?
It's a different silo. That is a different silo. Avalanche is new, and so I think currently it's the battle is really on for classical versus these new approaches, and you can imagine that there is a whole cadre of distributed systems people who've been trained classically, and so they're used to their own techniques. And when they see something that says, hey, we're going to approach consensus from a probabilistic point of view, that already is a huge setback for them. And so there's a whole lot of, this whole cellular automata type of approaches to consensus is so brand new that it's going to take the field some time to absorb. And I haven't seen the computational complexity approaches applied to it yet.
Well, I think the one thing that I might comment in terms of the literature, by the way, for people who are interested, I made this bibliography of this field, such as I know it. And if people want to add things to the bibliography, they should contact us. But you'll find that bibliography linked. But just as a bibliographic matter, Nick Pippinger, who's the creator of the NC computational complexity class, actually wrote a paper about probabilistic cellular automata. We'd hoped he was going to be able to join us for this conference, but that wasn't possible. So there is some connection. So Nick Pippinger, originator of the NC computational complexity class, wrote a paper about maybe 10 years ago or so about the question of trying to relate some aspects of computational complexity to, I guess he was interested in sort of computational complexity meets fault tolerance. So the NC complexity class is a parallel computation complexity class assuming no faults. And this was a paper attempting to cover the case of faults, but I didn't find much other. There didn't seem to be any other literature tree around that. But it seemed like that was so I would imagine, and Vero might have comments on this. I mean, this sort of connection between the error correcting codes business, which is an information theory, probabilistic analysis kind of world, that world, I think, has intersected with the world of computer systems in a pretty serious way. And so I'm surprised there hasn't been kind of a cross connection there between sort of probabilistic analysis and systems kinds of things.
There hasn't been. Let's give it some time. Let's give it 5 more years, and I'm confident that connection is going to be made.
Right. It's worth pointing out for everybody that, as my sort of historical outline indicated, the idea of cellular automata for consensus, like many good ideas, is not as new as one might think. It's an idea that's been around in some form for many, many decades. And Peter Gacs here, I think, is probably Andre Thome, unfortunately, was not in a position to join us here, but he might be I don't know whether he's the last remaining original contributor to that. But otherwise, Peter is probably our best representative.
But I do want to say something, Dr. Wolfram, that's important. In the distributed systems area.
Leonid Levin is also alive. Sorry.
What's that? Say it again.
Leonid Levin is also alive.
Oh yeah, definitely. Leonid Levin. Yes, I figured that Leonid had moved on to so many different things that this was probably not his interest right now.
He also hates Zoom.
What's that? Say that again.
He also hates Zoom.
Ah, interesting. Okay, I have not interacted with him since the time of Zoom. Please, Emin, you were going to say.
If I may add something. So if we look back at the history of consensus protocols in the classical setting, so Lamport's early work and people who were contemporaries with him, there were other people prior to him who were essentially working in that space. And there's also Barbara Liskov's work again. So those are almost contemporaneous works. And there is a lot of discussion about what it takes to have a contribution in that space. One of the most essential features is a proof of correctness. So distributed systems that need to be deployed in practical settings need to come with proofs of correctness. So insights are wonderful and characterizations are wonderful, but proofs of correctness are absolutely essential.
So I'm curious to ask something in that space. I mean, so proof assistants are a popular kind of idea for mathematicians who have proofs. Like I'm thinking if Peter Gacs had proof assistants at the time when he was trying to make sure that people actually believed his proof of the cellular automaton that can do reliable computation. I'm curious whether proof assistants have yet entered this, and automated proofs have yet entered this space. Is that a thing one's seeing at this point or not?
That's such a great question. Absolutely not. They are so far from it. Let's see. Proof assistants are good for analyzing safety properties that in simple discrete systems. So there have been groups. So Bob Constable's group working on a system called New Perl. And the Koch proof assistant from France, from INRIA, and the associated communities that have flourished, and various work on model checking has looked at these issues. Consensus protocols have been proven correct. So again, the New Perl group, for example, worked on non-Byzantine fault. No, they actually even worked on some Byzantine fault-tolerant protocols as well. But definitely not on cellular automata-based models of consensus. And the techniques that they use would not, at least as to my knowledge, as far as I know, and I'm far from an expert there, would not apply well to the kinds of analysis required, because now you're dealing in a stochastic domain, and they're used to dealing in a much more discrete domain. So yeah, well, I haven't seen it done.
I would say, I mean, a couple of comments there. I mean, I know our friends at Tezos are keen on, although I'm not sure they've really implemented yet, doing automated proof assistant kinds of proofs of protocols. I would say in terms of the use of proofs, actually in our physics project, we have, because the formalism of our physics project is remarkably close to the formalism of automated theorem proving, we've ended up both, oh gosh, I don't quite know how to unravel this in real time here, but one of the things that is a recent result of our physics project is the ability to take our physics project, compile quantum circuits to our multi-way graphs, which are the sort of foundation of parts of our physics project, then use automated theorem techniques on the multi-way graphs and optimize the quantum circuits. And I'm pretty sure that, although I can't figure it out in real time, that the noise and, the sort of all possible noise is like a multi-way graph. And I have a suspicion that some of the things that we've done just recently in the last couple of months on theorem proving for multi-way graphs might actually be useful for this. So that's an idea that at least occurs to me. I don't know how that will play out. But you were going to make a comment about Tezos, perhaps.
Yeah, I was one of the advisors to Tezos, and it's a project that I'm very fond of, and it has this wonderful property that it's written in a functional programming language that's analyzable, but it turns out it's very, very difficult to analyze the base system's correctness. And most efforts in this space have been focusing on analyzing the decentralized applications deployed on the blockchain. And it's been very difficult to take that and actually analyze the whole core foundation all the way down to the lowest elements. I believe there is one effort within Tezos actually looking at the correctness of the consensus protocol, but one would think that this should happen immediately, and no, it's not trivial at all. This is actually hard work to prove these protocols correct.
Let's see, maybe a couple more points here, and then we should probably wrap up. I think James here had a question. I think James is on a stream here and maybe can ask it himself rather than me reading it and getting it wrong. Please, James.
Sure. Thank you very much, Dr. Wolfram. Yeah, I was just on the point of MEV. I guess I was under the impression that MEV was particularly a problem in systems that don't consume state. So in that idea of like UTXOs, right, are like consumed and you output. But in like an Ethereum, the account model, you obviously don't consume state. But you can do Turing completeness, or it's been shown to do Turing completeness through like extended UTXOs, which I would assume inherit that. I mean, I know probably about that much about them, but they are addressable like normal UTXOs. So does MEV is that still a problem for extended UTXOs, or is it only a problem of like non-addressable consumption of state?
Very good point. If the underlying system is based on exactly what you said, which is shall I try to explain this for the audience? If it's based on UTXO, if it's based on the UTXO model, then it's inherent to every transaction that it's coming into the system at a particular state, and if that state has been modified, then that transaction is no longer available for inclusion in the chain. So that leaves no room for somebody to come in and front run it. And so you would think that by creating such a scheme, one could just cancel out all MEV. Well, that's all true, but there are cases where that's true. But one of the most interesting interactions in these systems is interactions with decentralized exchanges. And if you were to imagine an Ethereum type system, for example, where you and I want to interact with a decentralized exchange, and we submit transactions that assume a particular state, then suddenly the utility of the system drops tremendously, because the inclusion of any one of our transactions renders all other transactions invalid. And so suddenly the load on the system spikes up maybe 1,000-fold, maybe more, because normally those 1,000 transactions would go into a single block together, but now they conflict and only one of them can be placed in any one block. So it would be undesirable. The slower your system is, and Ethereum is a fairly slow system with 15-second blocks. The slower your system is, the less this idea is applicable. Even with Avalanche, which I think is the fastest system I know, it will still render the system fairly unusable. So imagine that you get one transaction per 300 milliseconds. That's still not very good. So there might be a funny medium, like an interesting medium there. And there is an insight there that you're pointing out that's really important. And the account model certainly opens it up. But I don't know how to really convert that to a really practical competitive system.
Yeah, so I was just thinking about it because we, in our blockchain, where our like VM that we're developing is kind of, it's a little bit like the old Qdom thing of like, it mixes the account model and the ledger and the UTXO model. So if the user wants to avoid MEV and uniquely address their state, then they can choose to do that in their transaction. And if there's someone front runs or is in front or like executes before them, obviously their transaction should fail. But maybe sometimes you don't care, so you just you go with the Ethereum style thing, so where someone could front run you. But it gives like that, it puts that option on the user to decide that. And I was just curious if what, and you answered my question exactly. So I appreciate that.
I see a comment from Grateful Tomato here on our live stream about proving correctness of implementations and the difficulty of doing that in different computer languages and so on. I just want to make one perhaps intellectual comment, which is, as we look at things like consensus protocols that are more computationally sophisticated, one of the issues is the consensus protocol itself can potentially be computation universal. So for example, I think in Peter's construction of his reliable cellular automaton, if I understand correctly, that very complicated reliable cellular automaton in one dimension is computation universal inside. And I guess whereas something like pure majority rule is certainly not computation universal, although Eric's kind of results about p-completeness and so on show that in certain cases one can achieve sort of more computational sophistication. But I guess the meta point to make is, the big risk in a sense in computer security is as soon as you have a system that is sophisticated enough to be computation universal, in principle, you can make it do anything. And that means you can make it do the things you want, and you can make it do the things you don't want. And so I think there's an interesting trade-off for computer systems, which once you make it computation universal, then there is this sort of challenging, potentially undecidable problem of determining, and that's why it's not possible to verify these things, is that once you make the thing sophisticated in what it's doing, it will tend to be computation universal. A lot of science that I've done suggests that computation universality is very ubiquitous, even among very simple systems. And that means as soon as the thing is computation universal, it's undecidably difficult to verify that it can't possibly do anything wrong. Maybe somebody wants to comment on that. See, Emin was responding a bit to that. I think it's an important point to realize that's in a sense the trade-off in computer security. In some sense, is you use a sophisticated piece of computation, you might think this thing is not sophisticated enough to be computation universal. It turns out almost everything is. Whether it's a spreadsheet, whether it's a word processor, whether it's a simple cellular automaton, almost anything with non-trivial behavior is computation universal. That's the thing I call the principle of computational equivalence. It's sort of a big result in science and for lots of other purposes. But that result right there tells you that that is the number one risk of computer security, which is as soon as this system that you thought just did the simple things you wanted it to do actually ends up being computation universal. So in a sense, it can do anything. And then once it can do anything, then it's, that becomes possible to have these exploits, and to box it in is sort of a whole Gödel's theorem type problem of, can you prove that it can't possibly do these things? Well, that's in a sense, infinitely hard for a computation universal system. So it's the trade-off of, you have the sophisticated algorithm, even an algorithm you don't think is that sophisticated, it will end up being computation universal, and then boxing it in can be very difficult.
So to follow up on that, I think we've seen before that even very simple network devices that follow very, very simple seeming protocols can be subverted to do all sorts of things because of exactly the issues you raise. So I think as professionals, we have really two sets of challenges. One, make something whose behavior you describe actually match the description of its behavior. And so build something that works. That's really hard. And then the second one, I think this is the stretch goal, is what I would say, is build something that doesn't do bad things. And I'm mostly, I think, at the moment focused on the former. It's very, very hard to build things that work, as we see all the time. And if I add in what you want to do, then it becomes really, really difficult, because reasoning about these behaviors is very tough. And but it's such a fascinating field. So yeah, it's very exciting.
All right, I think we had one last question here from Christian. Christian, do you want to ask your question?
Sure. Yes. So it's more a practical question. So do you know of any project actively using distributed consensus mechanisms to do like stuff in the real world, like in the physical world? Like, are there people, let's say, running an apartment complex using these kind of techniques or stuff like that?
What do you mean by that, Christian? What's an example of how you would use this? You mean with IoT devices or something like that, or? or what?
So let's say we have in my building, we have to take decisions in my building, and we have a committee for that. So I was wondering if there's a project that actually uses this technology to decide things in the.
You mean with voting of humans? You mean like
voting? Yeah, I guess voting is the first use case I can.
Well, I mean, you can pick if you've got a two-party political system, right? You can say, is the consensus to go with the red ones or the yellow ones, so to speak, and that's. I mean, supposedly there's a scheme, right, where you just count votes from pieces of paper or for a computer. But the question would be: is there a case where it's useful to do sort of a distributed version of that kind of consensus?
Right.
So Christian, yeah, I think the starting point was define physical world, right? So so let me give you some examples. There are lots and lots of IoT type devices connected to blockchains. For example, there is a company that's making vending machines connected to the Avalanche network, and so you could vend just by interacting, and you can make bottles pop out, you can purchase things, and so forth. That's the simplest kind of thing you could imagine. But we get into much more exciting territory when we start thinking about smart contracts. These are programs on a blockchain that execute free from interference according to preset rules, and they can direct money flows. On the Avalanche blockchain, there is a decentralized exchange that facilitates the transfer of assets, exchange of assets, and it has its own pool of assets to do this. It has liquidity pools it controls, and it is controlled by the voters of people who hold some of its tokens. And recently, maybe I think 2 weeks ago, it made a decision to employ some humans. So there is now at least one person who is getting his paycheck from this smart contract and working to maintain the smart contract. So I thought, that was an interesting twist of, man bites dog kind of a situation where suddenly we are working for the robots. And there are many other examples. They abound. It's a natural way to automate processes. But the biggest thing you see is automation of business processes. And because there is value involved here, the main thing that you see, it's inward oriented. So it's essentially a lot of the projects you see are all about automating and directing money flows. They're financial applications. They're not so much concerned with, most people are not so much concerned with manipulating the real world. But there are examples, as I mentioned, in the IoT space.
Yeah, one could imagine a situation where there are a bunch of earthquake sensors and they're in a distributed network. And the question is, when do you sound the alarm and evacuate Los Angeles? And you might not want to do that if just a few earthquake sensors fired, but you might want to do that if a majority of earthquake sensors fired. And that will be a case like that. One could imagine needing to use a distributed consensus algorithm. And I don't think that's that case, I know, I don't think that has come up because I don't think people have, that is a deployable thing. People know from smartphone accelerometers, they know things about, for example, earthquakes. And the question is, at what point did enough smartphone accelerometers fire? And can you figure that out in a distributed way? That would seem to me to be an interesting potential sort of real world application. And maybe there are other ones of this.
Yeah, I can add a few comments here. So Apple actually has kind of similar feature for the COVID detection. So the iOS device can kind of talk to each other if it finds out that a device is talking to another device that is kind of marked as like possible to be exposed or something. Then they know that the owner of that phone is also kind of vulnerable and can like alert him or report the data or something. So that's the first example. And the second example is something just like Wolfram said, but it's for like a chatting, a fire chat. It's kind of like a peer-to-peer chatting app that is using mesh network, not assuming any like Wi-Fi or like cellular data or something. It's for people who don't have internet access, assuming like thousands of people are in the same building, and they can use Bluetooth to form like a mesh network and talk to each other, do message passing. And probably another thing, just like Emin said, is like this kind of tiny IoT device. Well, actually, we are kind of doing this. Some of the work we are doing is to connecting those IoT devices with and let them talk to each other, or let them talk to your phone, or let them talk to your computer in a purely decentralized way. That's all possible because we have this kind of say-enabled consensus that powers the NKN blockchain to do the data transmission for it. Yeah, so that's like 3 examples that I can think of. That is pretty real world, I guess.
Oh, it's very interesting.
Yeah, very interesting. Yeah, thank you. Yeah, we can discuss later about what's the physical world. Yeah.
Yeah, but just one last sentence. I hope I'm allowed to say this. So I know that there are like many like talented people or like interested people doing research or engineering in this audience. So if we are really hiring, we really want to hire good people. If you are interested, no matter you're a researcher or like engineer or whatever, just contact us. We really want good people.
I think that's a fair thing for you to say. It's that clearly lots of very interesting problems, and it's really quite wonderful how a lot of these sort of very theoretical, mathematical theory of computation mixing with the real world, and I think through NKN and some of these other systems, it's really a cool thing when one gets to take a theoretical idea and immediately deploy it in the world. I mean, I know in my own work in building computational languages, that's one of the things that is most satisfying there, is to be able to take theoretical ideas and very quickly have a platform in which one can deploy them. And I think this is one of these unique times with distributed consensus and so on. It's a unique time when very elaborate theoretical ideas, somebody invents exactly the way to do this and can convince Yilun that it's the right thing to do for NKN, it'll get deployed on 100,000 machines, very rapidly thereafter. So that's a pretty exciting thing. All right, we should wrap up here, at least for our public audience, and thank everybody. Well, thank you to everybody who's participated here and speakers and so on, and thank you to our audience out in the world. And I hope you've had an interesting time hearing about distributed consensus for cellular automata and related systems. And I certainly have come away from today. I already thought this was an interesting problem. I now think it's an even more interesting problem. So that's a good sign. All right. Thank you all very much.
Thank you. Bye-bye, Steve.
Thank you.
Thank you.
Thank you.